where bk and bt are the creation and annihilation operators for the core. Sponding a n-tip, I-ticles with positive energy, so that we see and write y k z plus b t eikz equals l akek 276 ttwndwtdtdtmlt ers. In this way we avoid having particles with negative energy. Although the approach described above is M08T convenient for field theory, it must be emphasized that it is equivalent in all its results to the procedure adopted by Dirac, who originally worked with a purely p-article point of view. What he proposed was THAT in the vacuum, all the negative energy states were phi L led. Because the particles satisfy the exclusion principle, PLE, the transition of p-articles to the negative energy states co-ULDTH therefore never occur. However, when a particle went to a positive energy state, it would leave a hole that acted like an antiparticle. So in effect a p0 additive and negative pair while LDBE created in such a process, m or less as h happens. In a semiconductor where likewise a transition from one band to another creates a PAIR of positive and negative carriers. In order that the exclusion principle IPLE be satisfied, it is necessary that the wave function for all the particles be antisymmetry C. Once THIS condition is satisfied, then Dirac's approach and the usual approach in terms of fermionic operators are essentially equivalent. INDEED the two differ only by a unit a retransformation in which the AK underscore are replaced by B and the at by BK L underscore. It is important to start with the Dirac approach if we wish TOOBTAIN. An ontological interpretation OFTHE Dirac equation, because fermionic fields cannot be given an ontological interpretation in terms of BEables in the same way that it is possible with boson fields. For the fermionic field operators have only two possible states and cannot be PUT in correspondence with field beables that while LD change continuously. On the other hand, bosonic operators with THEIR infinity of states CA and BE represented in terms of continuous fields. All that we have to do then is to assume EAPOSI Zn for each fermionic particle and to make the total wave Fu NCT ion 1 Z1 Zn T antisymmetric. Then, as we HAVE already pointed out, PROVD at TH at we assume the vacuum corresponds to having all the negative energy states phi L led, we will be able to guarantee that there are no transitions to negative energy states. The interpretation we have given here will thus go through in a straightforward way. 12.4 Lorentz invariance of the many-body Dirac equation. Let us now go on to consider the question of whether the many-body Dirac equation is Lorentz invariant in spite of the phi.ct that it uses a common time for all the particles. To show that it is Lorentz invariant we shall begin by making use of the fundamental relationship that we have indicated in section 1-2. 3. Between the field theoretic formulation for fermions and the on the relativistic invariance of OURO ontological interpretation 277. Particle formulation for the case that the total number of particles is well defined. We make use of the fact that the field formulation H has been shown in standard treatments to be invariant not only to Lorentz transformations, but also to any change of the space-like surface on which the initial values of the wave function are given. F or detail see Schweber 3. From the equivalence of the field and particle formulatio NS, it will be seen to follow that the Dirac many-body equation is also Lorentz invariant nt. Let us begin by assuming that the fermionic field contains n particles. The B as IC orthonormal set can be formed from linear combinations of wave funcions 1215, where t/point2, xi, is the operator for the creation of a particle at the point x, and 1110 is the wave function representing the situation with no particle at any point nt. The general wave function can be written as a linear combination of this orthonormal set. 111 equals JFL_/J N X XN IP XI T/I X2 T/IJN XN 1 LLODX1 DXN 1216. Since THE operators Tj, T, Xj, anti-commute, it follows that the slash are anti-symmetric functions of the xj and the indices I1. Indeed, as is well known, Wn The/ RJUST ordinary antisymmetric wave functions for the n-particle system. In terms of the field approach, we can write the wave equation as 8111 Z at equals H111, 1217, where the H Hamiltonian is H equals JD I X T/ITA V IEA X TJ TJ O V plus IEA X T/IT 1218. This Hamiltonian operates ONTHE creation operators IN equation 1216. However, by integration by parts we can bring about an equivalent operation on the slash. It then follows that A 10 TLJ INX1 XN J NN. Since the operator formalism H has been demonstrated to be covariant, it follows that the above form of the Dirac equation can be obtained in 278 the undivided universe any frame. As is well known, the transformation between frames in field theory is unitary. From this it follows that at least as far as probabilities are concerned, The many-body Dirac equation is Lorentz invariant both in form and in quantity nt. 1 2. 5. The multiple time formalism. Although we have adequately proved the invariance of The Dirac many-body equation, it will be instructive to consider an alternative approach through the many-time formalism because the law TTER can provide further insight into meaning of this invariance. Let us begin by considering the Dirac equation for n particles, EACH of mass m, which is 12.20, where Hn equals A, Ea, Zn, T, plus Mfjn, 1221. When the equation is in this form we can only calculate probabilities for obtaining certain results, e.g. the values of the Zn, when measurements are made at the same time t. But suppose that we wish, for example, to measure the positions of the particles Z, at different times Tn. The multiple time formalism provides a way of calculating the probability of such results. To do this we begin by postulating the set of n-wave equations Ox Hi, F, equals Nx. Tn. 12.22. These equations will all be integrable provided the H Hamiltonians Hn and Hn all commute. But this will follow provided that the various points Z1 T1, Z2 R2, etc. are on a space-like surface, so that they are outside each other S-light cones. In this case one can start with x equals x, Z1, Zn, t. With t equals ti equals t2 equals tn, and d integrate the equations, 1 to 22, to obt in x equals x, z1, t1, z2, t2, zn, tn. Bloch has proposed an interpretation for the meaning of x, see went. Zel 4. This is that LXL 2 gives the net probability density for obtaining all these results together. It must be remembered however that Bloch is referring to the usual interpretation and D not to our interpretation. To see what Bloch's interpretation means, suppose that we consider an ordered series of times t1. If, for example, we measure on the relativistic invariance of OURONTOL logical interpretation 279. x1 at t1 then according to the theory given in chapter 2, which deals with the usual interpretation, the wave function after the measurement of the position of the first particle will see elapse 2, where cent. 1r, represents the wave function of the measuring apparatus, whose wave pa it centers at ir which corresponds to obtaining the value z1 equals ztr, w here ztr is the r1h possible result of the measurement. The important thing to notice HE is THAT after this measurement, there will be no interference with parts of the wave function initially corresponding to values of ZTR different from the result actually obtained. ZTR a similar description will hold for subsequent measurement of Z2, Z3, etc. and there. 4, as Bloch proposed, LXL 2 will give the probability that if Z1 equals ZTR in the result of the phi RST measurement, then Z2 equals Z2, will be the result of the seco ND measurement, and so on. The consistency of THIS formalism is further demonstrated by showing THAT propagation through a time FLT is the same as that obtained by prop agating EACH of THE individual equations, 1222, through FLT n equals FLT. Thus, we obtain for the total change of x. And this is just what we would obtain from the single time formalism. Let us now consider Lorentz invariant of THIS formalism. Each of the equations, 1222, is evidently Lorentz invariant. If we simply Lorentz transform EACH of THE equations from a wave function x in which all of the Tn are equated to a common time, t, we must then, in addition, consider each of the p particles at a common time t such that t plus vx tn equals, as shown in figure 1-2. L. It is evident from this THAT by suitable choices of tn. We see an always have a wave function considered at a common transformed time t. The Laurent.z invariance of the formalism is thus evident. 1-2. 60 NTHE quest I on OF Lorentz invariance OF the ontological interpretation of the Dirac equation. Let us now raise the question as to what extent the ontological interpretation of the many-body Dirac equation is invariant in content to a Lorentz. 280 The undivided universe constant x. Figure 1-2. 1. Space-time frames. Transformation. To simplify the discussion, let us consider a two-body SYS. Tem. Insofar A.S the wave function of the combined system can be written as a product ijj equals 4a. Z1, Ti, cent B, Z. 2. T2, it is clear THAT the velocities, 1210. OF the two particles will take THE form. And 1223. The density in configuration space will be PA, Zi, PB, Z2, where and Pb, Z 2 equals 4L, Z 2 cent B, Z2. The particles thus behave independently, and, from our previous discussion, Zion of the one-particle case. It follows THATTHIS system is Lorentz IN var IANT. If there is a Li near combination of wave functions 1 to 24, then, in gene RL, the two systems will cease to be independent. However, for the special case in which 4C, Z1, T, cent D, Z2, T, does not overlap for A, Z1, T, cent B, Z2, T. The interference terms WILL vanish and the net probability density in the configuration space of the two particles, LVJL2, WILL divide into two distinct. On THE relat 1v1st1cinvariance of OURO ontological interp RDATION 28-1. Channels of the general kind discussed in CH chapters 5 and 6. In this case the particles will be in one of the CH channels, WHIL the potent eoli active in 4. Machine in the OT-HER channel will have no actual effect. It is clear then that once again the two particles will be independent. More generally, however, there will be a non-local connection between the two particles, as can be seen, for example, from the expression for the probability density in configuration space. IWL2 IAL2L cent A, Z1, T, L21 cent B, Z2, T, L2 plus IB L2L cent C, Z1, T, L21 cent D, Z2, T, L2 plus AB cent Z1, T, cent Z2, T, cent C, Z1, T, cent D, Z2, T, plus C, C. 1 to 25. And for the current density of the first particle in configure T ion space. J1 EL 2 cent T, A, Z1, T, O, 1 cent A, Z1, T, L cent B, Z2, T, L2. Plus IBL 2 cent, Z1, T, O, 2 cent C, Z1, T, L cent D, Z2, T, L2. Plus AB cent Z1, T, O, 1 cent C, Z1, T, cent Z2, T, O, 2 cents D, Z2, T, plus C. C. 1 to 26. With a similar expression for the second p-article. It is clear from the above that the velocities v1 equals j1/p and v2 equals j2/p are no longer independent. Rather, the velocity of the phi rst particle, for example, will depend on the location of the second particle, which may in general be far away. And this, of QRSE, implies the non-local connection that we have mentioned above. When we go to the non-relativistic limit, this will lead, in the way explained in chapter 10, to the Pauli equation, and eventually in the limit in WHH the effects of SPIN can be neglected, we obtain the Sch-Rodinger equation. In the latter C as E, a non-local connection in the velocities of the particles implies a non-local quantum potential that accounts for the mutually related accelerations that are entailed by the GUIDANCE co-NDIT ions. In the limit in WHICH such non-local connect ions can be neglected, it follows from what we have said earlier in THIS section that THE theory will be Lorentz invariant. In this way we see that what we have in chapter 8. Cal led the manifest world, I e. The world of ordinary large-scale classically describable expanse will be invariant. It is in this world that quantum properties will have to manifest themselves, whether th-rough-me asurem ents, or through equivalent processes that occur Na2 rally, e.g. as an ion going through a cloud of gas in a natura LLY occurring electric field will produce large-scale cascades of charged particles in essentially the same way as H happens in ion ch ambers constructed by human beings. In order to agree with the experimental facts available, it is necessary to show that all statistical results of measurement manifestation processes are 282 the undivided universe Lorentz invariant. In doing this, it will be convenient first of all to point out how Lorentz invariance arises in the usual interpretation. What happens there is that the wave function undergoes a unitary transformation, u. When we go from one Lorentz frame to another, where u depends on the Hamiltonia n. Therefore operators such as z equals u z n u, 1 do not in general commute with z n, even though the z n all commute with each other, as do the z. In spite of this, however, because the wave equations are the same in every frame, measurement theory will go through in a covariant way. It has been shown Wn, however, that the ontological interpretation gives the same statistical results for all measurement manifestation processes as does the usual interpretation. This means that our interpretation will have a covariant content for all statistical consequences of the measurement manifestation process. But the only quantum experiments that can be performed thus far are of this statistical nature. So, in this domain, our ontological interpretation is also Lorentz invariant in content. In Chapter 14 we discuss the possibility of going beyond the present quantum mechanical statistical results. It is evident, however, that from the above discussion, it does not follow that the ontological interpretation for an individual system in terms of a particle with a well-defined trajectory is a Lorentz invariant concept. Indeed, it will be extremely surprising to obtain a Lorentz invariant theory of particles that were connected non-locally. To illustrate the typical difficulties involved in this notion, consider two separated particles, A and B, both at rest in the laboratory frame as shown in figure 1-2. If there is a non-local connection of the kind implied by our guidance conditio ns, then it follows that, for example, point A and point B instantaneously affect each other. But if the theory is covariant, there should be similar instantaneous connections in every Lorentz frame. Therefore A and B as well as B and A will also be in SUCH an immediate connection. It would then be possible for A acting at A to affect its own past A by affecting B. This would evidently imply a paradoxical situation, e.g. as in the case of a person who killed his own father before he was conceived and in doing so annihilated himself so that he was incapable of carrying out the assumed action. Of course, until we are able to carry out experiments on individual processes that are more accurate than the limits set by the uncertainty principle, it will not be possible to use quantum non-locality for the purpose of sending signals. For as shown in Chapter 7, in statistical measurements, the EPR correlations between distant particles do not make it possible for signals to be sent from one particle to another. More generally, any attempt to send a signal by influencing one of a pair of underscore particles under EPR correlation will encounter the difficulties arising from the irreducibly 284 the undivided un111 ERSE. X. Figure 1-2. 3. Trajectory intersection of hyperplane T equals constant. Participatory nature of all quantum processes. If for example we try to modulate the overall wave function so that it co-uld carry a sig NAL in a way similar to WHAT is done by a radio wave, we would phi n dThat the whole pattern of this wave would be so fragile that its order could change radically in a chaotic and complex way. As a result, no signal could be read. The non-invariance of the guidance relations for the case of non-local connection CANBE brought out more explicitly in terms of the multiple time form LISM. We begin in the laboratory frame, Z, T, in which it is legitimate to assume THAT all processes CANBE described correctly. As shown in figure 1-2. 3, we assume particles with coordinates z1, z2, and z3 moving on definite trajectories THAT intersect the T equals con st hyperplane at a 1, a 2, and a 3. If we determine the velocity of each particle independently by the multiple time equations, 1-22, the results would indeed be relativistically invariant. But as we have seen in the previous section, this will give us the statistical behavior of a system for which Z1h has been measured at T1, Z2, at a later time T2, and so on. Although our results were obtained from on The relativistic invariance of OUR ontological interpretation 285. Measurement theory in the usual interpretation, they will still follow in our interpretation. That is to say, after the measurement of Z1 is over and H has yielded a certain result Z1R, the subsequent behavior of Z2, Z3 etc. will no longer be affected by the parts of the wave function corresponding to ZL not equal to Z IR. That is for positions which are not realized in the actual individual process of interaction with the measuring apparatus. Therefore the wave function will not be the right one for calculating the guidance relations that actually operate on the particles when no measurements are made. For in this latter case the wave packets corresponding to all possible values of Z1R can come to interfere with the passage of time. Because of non-local connections of Z1 with Z2, Z3, etc. This will introduce further terms in the guidance relations not contained in the multiple time formalism. Therefore the multiple time formalism cannot get us out of the difficulties implied by non-local connection. Indeed it is clear that the entire calculation of the particle velocity will be ambiguous until we specify the frame in which the non-local connections are instantaneous. The concept of a particle guided in a non-local way will in general not be Lorentz invariant. As we have already pointed out, 1 has therefore to assume some definite frame in which the connections are to be described as instantaneous, while in other frames they are described as working either backwards or forwards in time, although still on a space-like surface, as shown in figure 1-2. If it turns out that the laboratory frame is not the one in which the connections are instantaneous, then it might seem at first sight as if the present could affect the past. But because the effect is only on a space like surface, it follows that THR will necessarily be a frame in which the non-local connections act only between points that are at the same time in this frame. Briefly, what this means is that there is always a unique frame in which the non-local connections operate instantaneously. In this frame, there is no intrinsic logical difficulty about having non-local connections. The behavior of these connections in other frames will then always be obtained by transforming these results from The special frame in which The connections are instantaneous From the above it follows that even though the underlying theory requires a preferred frame, all the statistical results of the quantum theory will still be covariant, as will of course, the manifest world of large scale experience. The basic idea behind this is that every measurement process is determined by an operator. The covariance of the wave equation implies that to any operator 0, THR is a corresponding operator, O, which is the Lorentz transformation of 0. In general, 0 and O do not commute, but this need not concern us since we are interested here only in measurement processes that are occurring in a particular Lorentz frame. The theory 286 the undivided universe OF measurement processes that WE have given, along with the demonstration THAT the probability distribution P equals P is covariant, then ensures that the statistical results of these measurement processes WILI have a Lorentz invariant content. Various AUTHORs have however tried to read IN covariance of the Underley ING theory by assuming non-low CAL connections that are Lorentz invariant NT. 4. XAMPLE, draws Vincent, 5, and Vigier, 6, suggested THAT for a two-particle system. One would assume THAT the non-local co-NNECT ions were instantaneous in their center of mass frame. Clearly this is a covariant N-ocean. BUT. The typical difficulty arises when WE consider THRO are more particles. AS. WE.OUTIN Chapter 11, Section 11. 2. WHRWE discussed p-article alternatives to the bosonic field theories, the center of mass frame of a pair of p-articles in a many-body system is ambiguous, because each particle may be considered in co-NNECtion with any one of the remaining p-articles defining such a frame. Even if we consider all THE p-articles of the given system regarded as classical, the concept is ambiguous because the latter may always interact with yet another system. Thus we do not feel THAT any overall theory of THISKINDCAN consistently define a cova RIN rela T on SHIP. OF p-articles that are non-LLY connected to some UP. Then, we have found that it is necessary to assume AB as I. Kali non-Lorentz invariant theory for the individual particule. Never THLS. This theory becomes Lorentz invariant where non-local connections can be neglected. From this we conclude TH at the manifest level of ordinary LARGE scale experience WILL be covariant in its behavior UR. We have also shown that the statistical LAWs of the quantum theory are covariant. We emphasize again THAT there is Lorentz invariant NCE in all of the domain S of particle theory that have thus far been investigated experimentally, but THSA do not necessarily invalidate our assumptions co-NCE running THEUND earlying level, in which the order of succession is UNIQUE. 1 2. 70 and the Lorentz Z invariance of THE onto logi CAL. Interpretation of boson field theories. The question of Lorentz invariance and the ontological interpretation of boson field theories is not B as I see ally different from that in Fermi and many particle theories. To bring out this essential similarity, we note that in the Fermion IC theory, THEBE-ables are p-article positions governed by guida NCE conditions determined by the wave function, see equation 123, while in BOS on the ORIs, the BEABLES are the fields whose movement is governed by guidance conditions determined from the wave functional, see equation on 113. The Similarity of the two theories can be made even more evident by using the on the relativistic invariance of ontological interpretation 287. Model D discussed in Chapter 1.1, Section 1.1.1, in which field variables are considered only at a set of discrete, but are either densely distributed points in space time. The field variables then correspond fairly closely to the particle variables. It is clear that as long as we stick to a certain Lorentz frame, THIS interpretation is coherent. But if we try to go from one Lorentz frame to another, we then encounter difficulties similar to those met in fermionic particle theories. For as we have already pointed out in Chapter 1.1, there will in general be non-local connections amongst the field variables. And as we have seen in THIS chapter, THIS means that a consistent discrete ption of these connections can be obtained only if we assume that there is a unique frame in which THEY are instantaneous. Also, if fermionic and bosonic systems are to enter a CT, it is clearly necessary THIS frame be the same for both TH of them. As was done with fermions, we can show that in the large-scale limit of ordinary experience, bosonic fields can approach a simple classical BE. HA-VIR in which non-local connections become negligible. We have indeed already shown in Chapter 1.1 THAT harmonic oscillators excited to HIGH quantum numbers can have wave functions, e.g. those corresponding to coherent states, in which the fractional fluctuation in the energy of excitation Be comes very small, so that THIS energy can be regarded as very nearly well defined. Nevertheless, at the same time the total spread in the number of quanta becomes very large. And as GLAUBER, 7 has SH own, for such a wave function one can define an approximate meaning to the pH as E of an oscillator. Therefore the oscillator can be regarded as moving very nearly in a classical orbit. If we then put together all the equivalent oscillators corresponding to the Fourier coefficients of the field, we obtain in the large scale limit of ordinary experience something THAT approximates to the behavior of a classical VLD. Because interactions that exchange a few quanta with the environment have no significant effect on the field as a whole, it follows that the latter can be regarded as independently existent. What THIS means is that one can ignore the basic quantum mechanical participation which is involved in a measurement, or more generally, in any manifestation in the large-scale world of ordinary experience, whether THIS takes place naturally or is induced by human beings. Chu and Stapp, 8 HAVE in fact given a more detailed treatment of this question for the case of massless fields. But they start from THE point of view of the 5 matrix rather THA and THE usual quantum mecha NICS. ASH happens with fermions, this approximately independent part of the field in the manifest world will also have a negligible contractibution from non-local quantum connections, essentially because the super QUANTUM potential is negligible for such HIGH quantum states. However, it must be E. 288 the undivided UNIVERSE. Recalled THAT-THIS will generally hold only for massless bosons. However, with mass IVE bosons THE energies required for such a classical situation are so HIGH THAT these do not play a significant role in the manifest world of or DINA re-experience. We can then go on to consider processes in which the quantum laws become important, e.g. scattering, ionization, etc., but as we have shown, THROUTHIS book, the statistical distribution of manifestat ions of these processes in the ordinary large scale world of experience will be the same in interpretation as the usual interpretations. Since the later is Lorentz var iant, it allows that our approach will also lead to Lorentz Z invariant. Result Ts for all statistical measurement manifestation processes. As with Fermio NS, it is only in the individual processes in which the quantum laws are important the theory ceases to be covariant and requires the assumption of a unique Lorentz frame. It is interest ingthat. Chu and Stapate, also have such a frame which is implied by their concept of a unique univ Ersel T.I.me. 1-2. 8 on the meaning of non-Lorentz invariance of processes involving individual variables. As we have seen in the previous section, our ontological interpretation leads to Lorentz invariant results in the manifest world of ordinary experience and also in the statistical predictions of quantum theory. These two fields cover all the experimental knowledge that wehave so far. It is only in connection with individual processes involving the variables that Lorentz invariance may break down. But as long as the quantum theory is valid, there is no way to demonstrate THIS non-Lorentz invariance experimentally. Nevertheless, it is understandable that there may be strong objections to giving up Lorentz invariance at the level of individual processes involve the variables. For relativity theory, both special and general, has had a very wide range of successful applications. Moreover, the beauty and symmetry of its mathematical form have not only been attractive to physicists, but have led them to have great confidence in the ultimate truth of the theory. We have to bec a refuel, however, not to assume that a theory has an absolute and unlimited validity just because it has agreed with a very wide range of experiments and because its form is aesthetically pleasing. From these reasons it does not follow that the theory of relativity is an absolute truth. In fact there is evidently no way to prove that any theory would ever is an absolute truth no matter how well verified it may be. Of course, as Popper 9 has pointed out, a good scientific theory should, on the relativistic invariance of ourontological interpretation 289, least in PR Inc. IPLE, be refutable and the theory of relativity clearly satisfies this requirement. But if we tacitly proceed in such a way as to take THIS theory as unchallengeable, we are, in effect, denying the applicability of Popper's requirement. However, such challenges may take many forms, not only those involving experimental tests, but also those involving theoretical criticisms of the consistency of the theory in question with itself and with other generally accepted theories. We could then say that our ontological interpretation helps bring out a fundamental inconsistency between relativity and quantum theory, centered on the question of non-locality. Recall. Here other interpretations of the quantum theory also imply non-local ity, though not in such a clear way, as shown in Chapter 7 and as we shall show in further detail in Chapter 1-3. What THIS suggests is that either WE accept non-locality, in WHICH case, relativity is not fully adequate in the quantum domain, or we reject non Locality, in which case quantum theory is not fully adequate in the relativistic domain. Of course, it is also possible that both theories may break down somewhere in the domain in which they meet. We are therefore led to consider the possibility that either relativity or the quantum theory, or both, may prove to be false when extended beyond certain domains. In Chapter 14 we shall discuss the possibility that it is the quantum theory that breaks down, though we shall not inquire specifically into whether the new theory would be compatible with relativity. In the present chapter we are investigating the possibility that it is special relativity that breaks down, while quantum mechanics remains valid. The most essential feature of special relativity is Lorentz invariance. We already know that Lorentz invariance must be limit at large dis ta nces where the effects of curvature are appreciable. We can also give an argument showing that Lorentz invariance sh be limited at short distance nces, probably at the order of the Planck length. To do this let us consider a vector, v, of ordinary length and regard it as made up of many smaller vectors, c5vf, which are on a straight line such that, suppose that we make a Lorentz transformation. Strictly speaking this cannot be defined without giving the metric tensor 9 v but at very short distances this tensor h as large quantum fluctuations and does not reduce to its simple diagonal form. The Lorentz transformation, Ca, I'll then give us 290 the undivided un over se. It is clear that was a simple line vector is transformed into a rather foggy distribution of constituent elements which are not well defined. So, the whole idea of a simple Lorentz transformation of one line into another breaks down. The idea of Lorentz invariance only becomes relevant over intermed IATEDI stances for which the fluctuations of G11 will aver a GE out to something relatively small, implying that 911 can be taken as effectively constant. All of this suggests that the Lorentz group may not be as fundamental as we have generally assumed. If it is not valid in the domain of very large stances and it is not valid in the domain of very small di stances, it may also cease to be valid in yet other domains. The analysis given in THIS chapter suggests that even at intermed IATEDIS it may cease to be valid for individual processes involving the variables wherever quantum non-local ity is important. We are THUSLED TOASUME something similar to a unique universal FRME. Or more accurately, to a universal order of succession. In certain ways, such a theory would be reminiscent of the Lorentz type ether theory within which there were large-scale objects with structures undergoing processes. THAT would change with velocity in such a way as to bring about Lorentz invariance in terms of frames defined through these structures. An explanation of THISKIND of theory is given in Bohm, 1-0. Here, one appeals to the notion that matter is constituted of atoms consisting of negatively CHA-ridged electrons and positively CHA-ridged nuclei. The forces between atoms, responsible for binding them into molecules, and ultimately into macroscopic solid objects, are assumed to originate in the attractive forces between electrons and the nuclei, and the repulsive forces between electron and electrons as well as between nuclei and nuclei. Consider, for example, a crystal lattice. The PLACES where the electrical forces come to a balance would then determine the di stance, d, between the neighboring atoms. Therefore, in the last analysis the size of such a crystal can tie ning. A specified number of atomic steps in any given direct ion is determined in this way. Lorentz assumed that the electrical forces were states of stress and strain. In The ether. From Ma Swell's equations, assume To hold in The reference. Frmeinwhich the ether was at rest, it was possible to calculate the electromagnetic field surrounding the charge particle. For a particle at rest in the ether, it followed that This field was derivable from a potential, cent, which was a spherically symmetric function of the distance r from the charge, I. E equals q/r, where q is the charge of The particle. When a similar calculation was performed for a charge moving through the ether, it was found that the force field was no longer spherically symmetric. Rather, its symmetry became that of an ellipsoid of revolution, having unchanged diameters in. On the relativistic invariance of our ontological interpretation 291. The directions perpendicular to the velocity, but shortened in the direction of motion by the factor Jl. v2/c2. This shortening ui evidently an effect of the movement of the electron through the ether. Because the electrical potential due to all the atoms in the crystal is just the sum of the potentials due to each particle out of which it is constituted, it follows that the whole pattern of equipotentials is contracted in the direction of motion and left unaltered in the perpendicular direction s. In JUST THE way as happens with a single electron. Now The equilibrium positions of the atoms are at points of minimum potential. It follows then that when the pattern of equipotentials is contracted in the direction of motion, there will be a corresponding contraction of the whole crystal in the same direction. A measuring ng rod made of such a crystal will therefore be shortened by the factor Jl, v2/c2. But if the rod is perpendicular to the direction of motion, its length will not be altered. In the reference given above, it is also shown that because the field intensity is increased by the contraction, it follows that the electromagnetic inertia of a charged particle is also increased. The net result is that any physical process involving the crystal, e.g. vibrations, is slowed down by the factor Jl, v2/c2. Therefore, if oscillatory processes are used to measure time, we obtain the well-known formula T 2 Jl, v2/c2, where 2 is the period for a crystal at rest in the ether and T is the period for a crystal in motion through the ether. Final ly it can be shown that two such processes equivalent to clocks will get out of phase when they are separated. When all three of THSA effects are put together, we obtain the Lorentz transformation between length and time as measured by a moving system, and those measured by a system at rest in the ether. It follows from THIS sort of argument that Lorentz invariance is perfectly compatible with the assumption of an absolute frame such as that of the ether. Therefore there is no way from the experimental facts alone to prove there is no absolute frame determining a universal order of succession. However, for various reasons which were mainly either aesthetic or philosophical, such a notion of a universal time order was rejected early in the 20th century. For example, the ether theories of Bly at the time as summed very complex and implausible mechanisms to explain the behavior of fields, and physicists found these assumptions unattractive. In addition, the ether theory in the form presented by Lorentz was such that it was Impossible to detect its presence by any experiments that could be contemplated at that time. Therefore at the very least such theories were Lt. 292 the UNDI 11-ided UNIVERSE. Not to be very relevant WHILE by many they were regarded as violating a PHIL ASAF ICAL principle that was widely accepted in the POSITIV stickatmo sphere of the TIME, i.e. that all concepts conta INED in any theory ought to be observable. Nevertheless physics developed in such a way that some features of the ether theory were retained. Thus Einstein, 1 in his general the attribute properties to empty space in the form of the gravitational tensor 9v. Einstein therefore later came to say THIS field theories were the rise of a relativistic ether that did not involve detailed descriptions of any mechanisms. It w as essential for Einstein that such theories should be local. And thus he was able to reta in Lorentz invariants, at least in regions that were not too large, strictly speaking only in infinitesimal domains desk ri bed. By tangent spaces. But now we have additional reasons to limit Lorentz invariance implying that it does not hold even in the SMALL and non-local. ITY further suggests that even in intermediate domains, Lorentz invariance no longer holds for individual processes involving the beables, but is valid only in the manifest domain and in statistical applications of the quantum theory. The notion of having a domain in which all phenomena become essentially independent of the preferred frame is one that is act ually quite familiar in other contexts. For example, consider a cubiccr is still which evidently determines a p-referred frame, yetlarge scale properties such as sound waves of long wavelength are isotropic and show essentially no trace of the frame. Similarly we may get Lorentz invariance for long waves even when THR is a structure determining a preferred frame. We have used the ether theory to illustrate how it is possible to retain an absolute time order and yet reta in Lorentz invariance. But the same result can be obtained in a much more general way without detailed and implausible assumptions about a material space-filling substratum of the kind to which Einstein objected. For example, one could suppose that in add diti onto the known types of field THR was a new kind of field which would determine a space like surface along which non-local effects would be propagated inst and taneously. At present we see ansay very little about this field, but one could surmise that this space like surface would be close to a hyperplane of constant time as determined in a certain Lorentz frame. A good CNDIDATE for such a FRME could be obtained by considering at EACH point in space time, the line connecting it to the presumed origin of the universe. This would determine a unique time order for the neighborhood of that point around which one would expect isotropic properties in space. We may plausibly conjecture that this frame would be the one in which the 3K background radiation in space has an isotropic distribution. This unique frame would not only make possible a coherent account of on the relativistic invariance of OURONTOLogical interpretation 293. Non-local connectio NS, BUT could also be significant in other ways. For X ample in THIS frame there will evidently be no limit to the possible speed of the particles. Thus, in the stochastic form of the ontological interpretation of the Dirac equation it is possible as we have seen in connection with equation 127, to have random movements that are faster than light. In The unique frame THATWEHAVE introduced, there evidently is no reason why such movements shall not take place. Recall however that a non-Lorentz in variant process OFTHISKINDCAN give a Lorentz invariant equilibrium distribution J equals L slash Tm. J0 equals L slash TL slash. This brings us to the second objection, i.e. that the absolute frame is unobservable. Certainly if we restrict ourselves to the assumptions that have been made thus far, this will be a valid criticism. However, in terms of our ontological approach, it is possible to alter these assumptions. In such a way that the absolute frame would be observable, while negligible changes would be produced in the domain of experiments that have been possible thus far. A great many such assumptions are possible, but we shall limit ourselves here to a simple illustration. Our ontological approach allows us, for example, to consider the possibility that the current quantum mechanics is an approximation to a deeper theory, as we shall explain in more detail in Chapter 1.4. Let us assume and that long-range connections OF distant systems are not truly non-local, as is implied by the quantum theory, but that they are actually carried in the preferred frame at a speed that is finite, but very much greater than that of light. For measurements made at levels of accuracy thus far available, the results will be very close to those predicted by the present quantum theory. But if we see and make me as Riemanns in periods shorter than those required for the transmission of quantum connect ions between particles, the correlations predicted by quantum theory will vanish. In effect, we would thus be explaining quantum non-local ity as an outcome of a deeper kind of non-Lorentz invariant locality. This, however, is relevant only in a domain beyond that in which current quantum theory is adequate. If we consider such modifications of the theory, it then becomes possible to contemplate an experimental test that would reveal the preferred frame. In essence, this test would consist of doing an EPR experiment in which the relative time of detection of the two particles was extremely accurately determined. In principle, the Bell inequality would then no longer be violated, for there would be no time for the disturbance of one particle to propagate to the other before the measurement was made on it. And from this, it follows that the latter particle would no longer go into a corresponding state of close correlation with the phi rst1. Of course, this will require a measurement of extremely high accuracy because the speed of transmission on 294 the undivided universe of the quantum connection is assumed to be very much greater than that of light. It is clear that the accuracy required is far beyond that of the aspect experiment. 1-2. In certain ways this test is reminiscent of the Michelson-Morley experiment, but it differs in the crucial respect that what is at issue here is not the measurement of the speed of flow IGHT, but RATHER a measurement of the immensely greater speed of propagation of our SUM-ed quantum connection of distant particles. Nevertheless, as in the Michelson-Morley experiment, we would have to take into account the speed of the Earth relative to the preferred frame. Thus one would have to make measurements in differ and directions and at different times. If one detected a change between these measurements, one would be able to demonstrate the existence of a preferred frame, thus making the latter in principle observable. However, if such changes were foo and d, this would indicate a failure of both quantum mechanics and relativity, which would be much more significant than the mere observation of the speed of the preferred frame. The meaning of such a result would be that we can eliminate quant non-local ity provided that we assume a deeper level of reality in which the basic laws are neither thos of quantum theory nor of relativity, which later come out as suitable limiting cases and approximations. OFQRSE, we cannot at present say any more about what THSA experiments are that could falsify quantum mechanics and relativity. To say more, we would have to develop our ideas in greater detail. We may give here the analogy of the atomic theory which was originally proposed in ancient Greece by Democritus about 2,500 years ago. At that time there was very little to go into assumptions about the atoms, e.g. it was proposed that THEY were held together by HOOKS and that THR were atoms of all sorts, such as atoms of intelligence, etc. In any case it turns out that the experiments available at the time were much too crude to have given any significant information about atoms. It took 2,000 years for ideas and experiments to develop far enough to permit some progress in this regard. Nevertheless, the idea of atoms was relevant during all this time. What they indicated was that continuity at the large scale could be regarded as an appearance, underlying which was the assumed discrete atomic reality. In any domain in which the notion of continuity was adequate, atoms could not be observed. However, it was not assumed that atoms were intrinsically unobservable. Indeed, the very notion of the atomic theory helped people to be alert to the fa.ct that THR might be observable consequences on the large scale which could be explained through these atoms and some of which would not be compatible with the assumption of continuity. Such consequences would provide observable evidence of the atomic constitution of matter. Similarly, with regard to the special frame implied by non-local quantum, on the relativistic envar of ourontological interp retation 295 connections and the deeper fields that would propagate these connections. Locally, we do not propose that these are intrinsically unobservable. We merely say that in the statistical and manifest domain in which the current quantum theory and relativity are valid, these new properties cannot be observed. Just as the observation of atoms became possible where continuity broke to Wn, so the observation of the new properties would become possible where quantum theory and relativity break to Wn. But of course it may take some time before we are able to pursue this matter experimentally. And hope fully fewer than 2,000 years. 1 2. 9 references. L. W. J. Layer and J. L. Pa RK, J. Mat H. Physical 1-8, 1235 to 1240, 1977. 2. C. Fennick and J. P. Vigier, Cr. ACAD. SC. Paris 293, 249 to 252, 1981. 3. S. S. Schweber, An int Rodution T Relativ istic Quantum field de Ori, H. Arper and Rho W, New Year K, 1961. 4. G. Wenzel, Quantum Theory of Fields, Interscience, NEW K, 1949. 138152. 5. P. Draws Vincent, Physics. Revelation 19d, 702 to 706, 1979. 6. J.P. Vigier, and on local quantum potential interpretations of relativis. Tick action at a distance in many body s, in open questions. In QUANTUM Physics, ed. G. Taras INA van der Meru E. Riedel. Dordrecht T. 1985. 7. R.J. GLOBR, Physics. Revelation 130 2529, and 131 2766, 1963. 8. G. Chu N H. P. Stapp, Fu N.D. Physical 800, and 9-83 1, 1988. 9. K. R. Popper, The Logic of Scientific Discovery, Hutchinson, London. 1968. 10. D. Bohm, The Special Theory of Relativity, Addison Wesley, NEWYORK. 1989. 11. A. Einstein INSCIENTIFIC Papers PRESENTED2M. BORNONHIS RETI. Mant, Oliver, and Boydie, London, 1953. 12. A. Aspect T, J. Dalibard and G. Roger, Physics. Rev. Let. 44, 1804-1807. 1982. CHAPTER. 13. ONTHE Many Worlds INTERPRETATION. 13. 1 Introduction. Over a period of time there have developed a number of other ontological interpretations of the quantum theory. In the next chapter we shall discuss some of these, but here we shall give a more detailed account of one of THSA, which generally goes by the name of the many worlds interpretation. We are giving this interpretation special attention because it has come to be fairly widely accepted, a special ly by thos who work in general relativity and cosmology and who therefore feel ed to regard the universe as existing in itself whether observed or not. We must emphasize from the very outset, however, that THR is no sin. GLE genera ly accepted version of the many worlds interpretation. Indeed, THIS interpretation has been constantly developing as a result of attempts to clarify its meaning and to remove WHAT are perceived as its inadequacies. In this process a great New York ideas have been explored which do not fully agree with each other, and it seems THAT, as yet, THR is no final version of THIS interpreted on THAT is accepted by all of its protagonists. For a comprehensive account of THIS development see Bendov 1. Further to TALD is Cuscience WILL be found in Ballantyne 2, Bell 3, Cooper and Van Vechten 4, D. Espinat 5, Primus 6, Stapp 7, Zay 8. The key difficulty stems from the fact THAT, as we shall see, the two and protagonists of this interpretation, Everett 9 and DeWitt 10, differ significantly in their basic formulations, and from this difference further divisions arise from those who have adopted various approaches to deal with the difficulties. At these two did not resolve. On the MANY, WORLDSINTERPRETATION 297. 13. 2 Everett T.'s approach to THE many worlds interpretation. We shall begin with a discussion of Everett's approach to the many worlds interpretation 9, which emphasizes the inclusion of observers as purely physical systems within the theory. It seems THAT in doing THIS Everett intends to deny dualistic notions in which mind, for example, might be regarded as a kind of spiritual reality beyond THAT of the material universe, and separate from it. This denial would also include Win-ER's notion of a collapse of the wave function as produced by the interaction between matter and such a mind 1-1. Everett effectively assumes THAT the universe as a whole including all OB servers exists subjectively and is described completely by a vector in Hilbert space. Within THIS universe he wants to attribute subjective states to THE observers which are in perfect correspondence with some aspects of the material universe and therefore of Hilbert space. This sort of idea has been widely called psycho-parallelism. He feels THAT it will suffice. For his purposes THAT observers possess memories, i.e. parts of a relatively permanent nature whose states are in correspondence with the past experiences of the observer 1-2. WHATTHIS means is THAT, as in a computer, whose memories are contained in the state of a DISC, some aspect of the physical state of the observer, presumably within HIS brain, serves as the basis of his memories. Deductions can then in principle be made about THE subjective experience of the observer by examining the contents of THE memory. Everett proposes THAT we can extend THIS model of an observer by considering him to behave like an automatic machine possessing sensory APPA. Ratus co-UPL to registering devices capable of recording past sensory data, as well as machine configurations. He further supposes THE present actions of the machine are determined, not only by its present sensory data, but by the content of its memory as well. Such a machine will be capable of performing a sequence of observations, measurements, and furthermore, it will be able to determine its future behavior on THE basis of past results. Everett feels THAT for such a machine we are justified in using phrases such as the machine has perceived a or the machine is aware of a if the occurrence of a is recorded in its memory. We see a and further illustrate Everett's ideas in terms of the example of the measurement of THE spin of a particle. In treating THIS question, Everett makes use of the von Neumann theory of measurement which is, of course, also what we have used in our own approach. If THE initial wave function of the spin is Tj equals AT slash plus S plus BTJ underscore S 131 298 the undivided universe, and the initial wave function of the point ER of the apparatus is a wave packet sent 0, 11, then after the measurement interaction is over, the combined system is left with the wave function Tpj equals etc slash I plus T1 1 slash J plus S plus slash J sent I underscore Y T slash J S 132 WHERE sent plus TI ANDCP Y R wave PA its corresponding respectively TOPOS. Positive and negative results of the spin measurement. The essential further step of Everett is to introduce wave functions x plus, m, and x, m, where x plus and x represent states of the brain, or computer, that correspond respectively to memories of positive and negative results of this measurement. The overall wave function is then equals x plus, m, sent I plus, t1, 1 slash j plus, s, plus slash 3x, m, cp, t1, 1 slash, s. 133. In equation 132, we hadaq untum state in which the spin and the observing apparas were entangled in the sense suggested by Schr Oedinger. Similarly, equation 133 describes a state in which the memory within the observer has further been entangled in a similar way. Therefore, in a fu and a mental sense, the observer does not have a definite memory of what is the outcome of the measurement, unless either a or f3 is 0. In order to give the memory a definite state, we would have to have another observation in which the content of this memory was observed. But this would introduce yet another memory of the second observer, and the same difficulty would be repeated at one stage removed d. It is clear, therefore, that if we add no further concepts to the quantum theory, e.g., such as well-defined particle positions as we have done, and if we do not allow collapse, then there is no way in whatever it has said thus far, to describe the fact that a definite result is actually obtained in each case. In order to proceed further, some additional assumptions are evidently needed. Everett does not state these assumptions clearly, and indeed puts them in such a tacit way that one can readily fail to notice them. However, his essential assumption is implicit in the statement given on page 68 of reference 1-2. We shall give here a paraphrase of this statement which we feel brings out more directly what we think that Everett wants to say. In order to avoid the need for arguing about a definite result for the measurement by means of a collapse of the wave function in equation 133, Everett assumes that each part of this wave function corresponds to a definite state of awareness of the content of the observer's memory. He says that in one sense, there is only one total awareness belonging to such an observer. Nevertheless, he says that, for the case of spin measurement, this single total awareness simultaneously can be regarded as 2fold, and that on the MANY, WORLDS INTERP RETATION 299. Each OF the two partial awarenesses is not aware of the other, N or OF course of the wholly. It is evident THAT in a series of measurements, THE number of PARTIAL awarenesses must multiply indefinitely. There are correspondingly many possible BRNs consisting of such sequences of PARTIAL awarenesses. He ASUMESTHATONE of these branches represents the experience of a PARTICULAR person. The other branches do not represent merely POSSIBLE experiences. THAT this person might have HAD, as THEYWOULD, for example, in a COR. Responding TREATM and in terms of our own interpretation. Rather THEY represent distinctly different sequences of experiments which are actually recorded in other awarenesses similar to, but different from, this particular one. We emphasize again that all these different sequences of awareness are not aware of each other, nor of the whole. EVERETT assumes THAT the whole universe including all observers exists objectively and is described, as we have already pointed out, completely and perfectly by a VECT or INH Hilbert space. One may explain WHAT this means loosely by saying THAT in some sense THE universe is regarded as a multi-dimensional reality. But whatever it is doing, is to make a THE or a THAT. Relates the universe to various points of view. THAT are contained within it. WHATWE experience of THE universe is a single subsequence of THSA points of VIU. Or, as Squires 1-3 has put it, what we are dealing with is not a many universe theory, but a theory of one university ERSE with many viewpoints. Each point of view establishes a relationship between a state of awareness and the state of some other part of the universe containing the observing instrument and the observed object. The existence of this sort of relationship has been described by Everett as a relative state of the system corresponding to a particular state of the observer, or more accurately, to the state of his awareness. Everett and those who follow him seem to regard this notion of relative state as a fu and a mentally new concept comparably perhaps to unsaint ins regarding the meaning of a position coordinate as being relative to some material system, which serves as a frame of reference. Thus in Everett's language we see and say that any part of the total vector in Hilbert space has a perceptible meaning only in relations hip to frames constituted of the memory of the observer. As there are many permissible coordinate frames in relativity, so there are many observer frames in quantum theory. As an example of Everett's interpretation, let us consider a GAIN equation. 133. In THIS case, the wave function of a partial awareness corresponding to a state of memory of spin plus t will be multiplied by wave functions describing the state of the apparatus and of the spin itself also corresponding to spin plus t. From there on, this memory will develop further awarenesses, which phi tin with this state. It will however not be aware of the development of other components of the Hilbert space vector corresponding to the observing instrument A and the observed objet CT. SOONONE branch the awareness is as if the spin HAD collapsed to EV. It gives some arguments aim ing to show the consistency of THIS approach. For example, if a second observer interacts with THIS system, after the phi RST observation, the overall wave function will become x plus m2, x plus m1, cent plus y1, cent plus y2, slash I plus s plus slash 3x m2 x me cent I underscore y1 cent I underscore y2 t phi underscore s, where y1 and y2 represent the coordinates of the first and second apparatus respectively. WHILE M1 and M2 represent the memories of the corresponding observers. From Everett's assumption, it follows THAT the MEM ories of the two observers, the states of their apparatuses, and the value of the spin are completely correlated. Therefore if, for example, the phi RST observer remembers spin plus I, this means not only THAT the spin will act as if it were plus I in all HIS subsequent experiences, but THAT the second OB server will also remember the spin was plus and experience it as such from then on. In TH's way Everett explains how different observers can come to agree about the implications of their observations. Everett gives further arguments aiming to show in more detail how all the observed results of the quantum theory would follow from analyses of THIS NATU re. It is implicit in Everett's approach, and as we shall see, this is made explicit in DeWitt's approach 1.0, that the main purpose of THIS interpretation is to introduce the minimum number of concepts into THE ori. For example, Everett would regard our notion of particle variables as further assumptions THAT are not needed. It seems to be especially important for Everett to put all the concepts in H's theory into correspondence with the basic mathematical structure of the quantum theory, i.e. in terms of Hilbert space. Thus he not only assumes that the physical universe can be described completely in terms of Hilbert space, but he seems to imply that the same is true for mind, which he regards as being in essence just awareness and memory as he has defined THM. It must be emphasized however that THISIN itself is a HIGHLY. Speculative assumption with very little evidence behind it. Everyone agrees that we know very little about mind or conscious awareness, but many would claim THAT it must include much more than just memory. Even if we accept the as yet unproven assumption that memory can be explained in the way THAT Everett does, it does not follow THAT could be done. For the whole of mind which includes attentio and sensitivity to incoherence. All sorts of subtle feeling and thoughts and creative imagination as well as much more. We will discuss this in more detail in chapter 1.5, where we, too, consider the possibility of including the observer in our overall view of the universe. However, we feel that the entire framework of current quantum theory is too limited to do this properly, and we propose extensions of the theory that might make a more coherent account of observer possible. Perhaps we could put Everett's hypothesis about mind into a more favorable light by regarding it as just a convenient simplifying assumption that makes it possible for him to get on with the interpretation of quantum theory. But even if we do this, we find that there is a further speculative hypothesis of a more physical nature. This is that it is possible to put some quality, such as awareness, into a precise and accurate correspondence with some part or component of the total vector in Hilbert space. Thus, for example, returning to equation 133, it will be consists. Tend to say THAT the memory is defined when either A equals 0 or J equals 0. For in these cases, THE memory would be determined by an eigenvector of what may be called a memory operator. Otherwise the memory has to be E. Ambiguous, just as other properties, such as momentum and position, have. To be ambiguous when the Hilbert space vector representing the state of THE system is not an eigenvector of THE corresponding operators. But Everett is further assuming that there is a property called awareness, which he regards as essentially physical, that can be put into a rate correspondence with some part of THE total Hilbert space vector, even when the latter is not an eigenvector of the memory. If a similar statement were made about an ordinary physical quantity, this will imply a violation of the uncertainty principle. Or to put it differently, Everett is assuming THAT the mind can be aware of its own state of memory without measuring the latter, therefore without disturbing the latter, and hence without introducing any ambiguity. It is clear then that Everett has assumed a kind of property going far beyond what is allowed in the ordinary quantum mechanic, and in effect has introduced a basically speculative theory of me and d, along withan equally speculative theory as to how this can be related to a component of a total vector in Hilbert space. Everett's approach may be interesting to pursue further, but it should not be presented as having a smaller number of hypotheses than other interpretations. Even if we do not object to the assumption of a large number of awarenesses undetectable to us or to each other, we must still notice that we are introducing large and unverifiable assumptions about mind and attributing new properties to Hilbert space which go beyond those which follow from ordinary quantum mechanics. If we accept Everett's approach in the above sphere it, we see ANTH and go on to ask whether it is consistent in full detail and whether it deals adequately with all THE problems raised in such an APPROACH. We shall in the subsequent sections outline briefly what are the MA-IN questions involved in DWHATR. In this section we shall develop DeWitt's approach to the MA New York worlds in interpretation and compare it with that of Everett. In doing THIS we shall see THAT. There are some very important differences between these two AP PROCHES. However, the fact that these differences exist appears not to be widely known or recognized, and indeed many authors including DeWitt himself essentially identify the two. The fact that BOTH are commonly given the same NAME, though Everett did not use the term many worlds, helps further to draw attention away from the importance of these differences. DeWitt's motivation for his approach is clearly stated in his paper, 10. He felt dissatisfied with all the metaphysical assumptions contained in previously available interpretations. He then proposed that we forget all these and begin afresh. 14. In part TCULAR his intent were stated as the following. 1. To take the mathematical formalism of quantum mechanics as it stands without adding anything to it. 2. To deny the existence of a separate classical reality. 3. To assert that the state vector never collapses. He then asserts that it is possible to achieve these intentions and that this was proved by Everett, 9. With the encouragement of Wheeler 1-5 and THAT. This has subsequently been elaborated by Graham, 1-6. As with Everett, DeWitt starts with the assumption that the mathematical concept of Hilbert space provides the whole of the basic conceptual structure underlying quantum theory. He says that only one additional postulate is needed to give meaning to the mathematics, namely, the postulate of complexity. The world must be sufficiently complicated it can be decomposed into systems and apparatuses. 14. From THIS it follows that the mathematical formalism of the quantum theory is capable of yielding its own interpretation, and all THIS without external metaphysics or mathematics. DeWitt evidently agrees with the implication of Everett's approach in assuming THAT the universe is faithfully represented by a vector in Hilbert space. But of course, as he pointed out, this vector must be immensely more complex than the sort that appears in equation 1.3.3. DeWitt then asserts THNT the universe itself is splitting into a stupendous number of branches, all resulting from the measurement-like interactions between its myriads of components. Such interactions take place, not only in measurement, but also in natural processes of all kinds which likewise bring about a continual splitting of the universe. Here we encounter a serious difficulty. For DeWitt clearly attributes his theory to Everett in a number of places. Yet as we have seen there is no mention of splitting universes in Everett's work. Rather there is one universe with many awarenesses that are not aware of each other. To be sure, Everett includes memory, which is the content of THSA awarenesses, as part of the total universe. Nevertheless he specifies CALLY requires TH at THR. Be relatively permanent memories without which he could not formulate HIS notion of awareness. Of course, memory implies a very complex structure. But not every complex structure is a memory. So at the very least, DeWitt should have SAIDTHATEV or it requires a kind of complexity THAT would provide THE basis of memory, e.g. a BRA-IN or at least a supercomputer, as indeed we have seen from Everett T.'s comparison of awareness to the function of such a machine. But even THIS would not be enough, Everett T also says THAT no very signify CANT change takes place when an observer becomes aware of a certain result T. It is not THE universe THAT splits, but it is just awareness as a whole. THAT divides into many parts. THAT are not aware of each other. We repeat again what Squires 1.3 has said, it is not a theory of many universes, but a theory of many viewpoints of one universe. Everett's aim is thus not mainly to expla in THE universe, but rather to explain our perceptions of the universe. Everett revealed his attitude to this question in commenting on some views on the quantum theory expressed by Einstein, 1.7. In the von Neumann interpretation, observation induces a collapse of the wave function. THAT may affect THE whole universe. Einstein objected to THAT as implausible and unsatisfactory. At another time Einstein put THIS being colorfully by saying that he could not believe THAT a mouse could bring about drastic changes in the universe bysimply looking at it. In answer to THIS, Everett 1.8 says that from the standpoint of his theory, it is not so much the system THAT is affected by an observation as it is the observer who becomes correlated to the system. Further along he states THAT observer VATION simply correlates the observer to the system. Furthermore he adds only the observer's state H has changed, to become correlated with the system. The mouse does not affect the universe, only the mouse is affected. 1.9. It is clear from THE above that Everett did not contemplate the split ting of the universe. It follows then that there is a fundamental difference between the basic assumptions held by the two leading protagonists of the many worlds approach. Indeed, Everett's view should not even be called the many worlds interpretation, but rather, as Albert and Lower 20 have suggested, the many minds interpretation, a view which we discuss lat The key difference between DUITT's approach and THAT of Everett is. THATDE with S theory is purely objective, WHILEEV or its THE depends crucially on the inclusion of the subjective experiences of the observer. WHICHRHO Weaver explain it objectively as being in correspondence with parts of the total HILBERTSPACE vector R. For DUITT, the universe actu LISPL its as might happen to material objects. This assumption creates a number of problems. Firstly, we can ask just when does it split? Thus, for XAMPLE, while the spin is interacting with the measuring APPA radius. As described in equation N, 133, the wave PA it's corresponding to THE2. Possible results begin by overlapping. In principle some overlap may persist for a long way even though THIS may be small l. What is it THAT determines? When two overlap PPING wave PA its origin ALLY in one universe, sud ENLY. Become two non-overlap PPING wave PA its in separate universes? Indeed. UNLS the measuring APPA radius is complex enough to make possible a TINCT classical like result T, the universes show ULD never split, as the two-wave PA its co-ULD again come to interfere in the way we HAVE described in Chap. Ter 6 and 7. But once the universe has split, it seems THATSUCH interference CES. Would no low NGERBPOSSIBLE. In the usual approach to the quant the ORI, as well as in our approach, it is always, in principle, possible for SUCH interference to occur again. ONEUSULLYFEALS to some feature SUCH as the complex enchait IC. PHASE relations OF the wave function to make SUCH interference CEUN likely. To HAVE significant effects, FOR example see bohm 21. From DeWitt S. Emphasis on C complexity, one might suppose THAT he assumes THAT when the wave fun CT ion reaches a certain degree of complication, the universe begins to split. But he does not define complexity, though some authors, notably Leggett 22, are now exploring HOWSUCH a definition may be made. But in a different context from THAT of the many worlds interpretation. WHAT wow LDB required for an adequate formulation of DeWitt's approach. In THIS regard would be to come up with a good quantitative definition of complexity and to assume some further equations determining how the spliting of universes is related to THIS feature of complexity. But if HE were to succeed in doing THIS, he would clearly HAVE introduce new concepts as as new equations, and could not hope to claim that the mathematics of the current quantum THEORY determines its own interpretation. Related to THIS difficulty is the fact that DeWitt wants to do without a SEPA RATE class ICL level, and yet he does not suggest anything THAT could take its place. Nevertheless, in describing what he means by an observing apparatus, he tacitlysumes all sorts of properties that are suggested by classical physics, such as the possibility of distinct results which are stable and do not vanish in the quantum uncertainties of the Hilbert space. Perhaps he could also deal with THIS problem in terms of the notion of complexity if he could show THAT, WITH a sufficient degree of THELATTER. Something like a classical War ID would emerge in a certain limit as we have shown in terms of the quant potential, see Chapter 8. But in the absence of such a demonstration, we have to say that this key part of his B as IC intention H has not been reali said, as H has indeed been po int out by Gel. Man and H Arirdle 2-3. 1-3. 4 probabilities INTHE many worlds interpretation. Whether we adopt the approach of Everett or THAT of DeWitt, we are still faced with the question of what is to be meant by probability in THIS general point of view. If we see LAM THAT the whole universe is completely described by a certain vector in Hilbert space, then this is unique and does not allow for a statistical theory, based for example on an ensemble of similar UNI versus HOWTHN. Are we to relate the many worlds approach to the usual probabilities of quantum mechanics? Everett and DeWitt adopt what is B as equally the same idea. They consider a long sequence of n measurements on similar systems, initially in the same quantum state. Their aim is then to prove, without any extraneous assumptions about probability, THAT as n plus 00 the relative frequency of a given result will be equal to the usual quantum mechanical probability. For simplicity, let us take the system to be a p-article with spin. The relevant initial wave function is then 1/Jo equals AL/J++ n 134 We now consider the whole set OF systems as forming a single combined system whose initial wave foo nct ion is xo equals 1/jo, l/jo, 2. 1/jo, n, 135. WH air THE numeral indicates THE particle in question. This can be written as xo equals ETL/J plus L plus /.11/J L ETL/J plus 2 plus /11/J 2 AL/J plus N plus 11/J underscore N 136. We now suppose that THE spins OF. Each OF these P radicals is measured by a separate PIEs of apparatus whose relevant coordinate is yn. If cent O, yn represents the initial wave function of the N1H apparatus, the total initial wave function is 13.7. 306. The undivided univer SE. It is clear THATTHIS wave function 1's a sum of two n terms. A typical term would be Sn, S, T, equals cent O, J11, cent O, TH, cent O, J1n, N5/3n, SITIP plus ITT/J underscore, 138. WH air D5 tri plus is a product of a certain number, S, of particle wave functions, with spin plus n, S. Tp represents the product for the n, S remaining particles with spin. After the measurement process is over, THEN, in accordance with the von Neumann THE or THAT we HAVE given in Chapter 2, Section 2. 4, the term 13.8 becomes Sn, S. Ts1 equals N5I3n, S at P, Yi, Tp, 139. Where cent plus, Yi, represents the wave function of the pointer of the I1HAPPA. Ratus indicating spin plus and cent underscore, Yd represents the wave function of the pointer of the APPARATUS indicating spin. Each of the above terms may be said to represent a branch of the total wave function, which L adder is 1310. It is the object of the proofs given by Everett and DeWitt to show THAT. Except FORASET of measure 0, all branches will yield a F-oration in 124. Spin plus NL/312 for spin, as THE number of branches becomes infinite. To do this, Everett and DeWitt begin by assuming a measure associated with each vector in H Hilbert space which is equal to the quantum mechanical probability THAT is usually associated with that branch of the wave function. In STANDARD quantum THE ori. For example, if the wave function is nt/++11/ the measure of 1/I plus is LNL2 and THAT of TP is L/312. But they do not begin by assuming THIS is a probability. Rather, they take it to be a purely abstract quantity which they HAVE called measure E. They then show THAT in an infinite sequence of measurements the measure of branches in which the proportion of spin plus d differs from LNL2 and that of spin, from L/312, is 0. As yet, HOVR, nothing follows from THIS about actual relative frequency size. To make a connection they HAVE to introduce a further assumption. This is a sentia LLYTHAT branches of measure 0 never occur. From TH is it follows, of course, THAT in an infinite sequence, we will get the right relative frequencies. But this proof has been criticized by D.E. Spagnat 24 and others, c. Deutsch 25. There is no intrinsic reason why branches of measure 0 should never occur, if measure is nothing more than a purely abstract mathematical quantity. Moreover, we would fail to obtain an additional result of standard probability theory which is necessary for its consistency, i.e. THAT. Sequences of small measure must occur correspondingly rarely. The TRE meant of Everett and DeWitt would in any case apply only to an infinite sequence, but the theory must apply to finite sequences that can be carried out in actual XPE rem ENTS. Indeed, current probability theory implies THAT. Finite sequences of small measure must occur sometimes if the distribute ion is random. In other words, we cannot guarantee THAT air will neverb. Large fluctuatio ns. The proof given by Everett and DeWitt contains no way of obtaining such a result, except perhaps by adding further arbitrary assumptions. It is only if we suppose that the mathematical measure COR responds to a relative frequency in a random ensemble THAT we can deal with THSA questions adequately. In any case, a more careful analysis of this situation is made by B. Allen Tyne, 26, who shows THAT the relative frequencies do not actually approach LAL2 and LBL2 for the case of spin. Rather, the distribution B. Allen Tyne obtains is HALF and HALF. One can understand this by noting THAT the only way of bringing probability into this situation is to suppose equi of the discrete alternatives, which will, of course, inevitably bring about AHALF distribute ion. It is clear then THAT the many worlds interpretations of Everett and DeWitt have not succeeded in providing an adequate account of probability. To deal with this, Deutsch 25 assumes further modificat ions of the Ori. Rather than supposing with DeWitt that the whole of existence is continually bifurcating into more and more universes, he postulates that there is always an infinite and essentially constant number of actual universes. For example, in the case of spin that we have treated earlier in terms of equation 1311, each of the whole set of universes initially H as spin T, and THE corresponding apparatus is in its initial state. After the measurement process, the universes are partitioned among the states indicated by 1313. The essential assumption of Deutsch is THAT there is a random distribution of THSA universes with probabilities corresponding to the usual quantum mechanical probabilities for the associated results. In a measurement, we begin with an initial distribution of universes in which all of them had the same initial spin state given by 1/j equals 0.1/j ++/31/j underscore, while all the apparatuses are in the same state. After the measurement is over, this distribute ion is changed into one in which the probability that S particles in the sequence HAVE wave function 1/j plus, while the remainder HAVE wave function T/j underscore, is JUST. IAI 251BL2, NS. This is, of course, JUST the usual quantum mechanical probability for such a sequence. And from this expression it follows THAT. As the sequence approaches an infinite number, THE relative frequency OF spin plus L will be ELO 12 and spin will be 131 2. It is CLEAR then THAT Deutsch succeeds in ACHI-eving the aim THAT Everett. And DeWitt failed TOACHI-EV. However, there are a number of serious questions THAT Deutsch has not yet answered. The most obvious of THSA is that he has chosen a certain basis for the interpretation, in THIS case. THE1INWHICH. The spin in the z direction is diagonal. Of course it is clear that this b as is corresponds to the orientation of THE APA RATUS. But recall THAT. One of the basic aims of the many world interpreted ions is to get everything out of the formalism without further assumptio ns. Deutsch has not show wny it is just. These pieces of operat usthat will partition the universes in the way he has assumed. If he stops here hewl be ina. Position similar to THAT of von Neumann, who likewise distinguished between the APPARATUS and THE rest of the universe without deducing this distinction from the formalism. Presumably THE apparatus is distinct INTHAT. It behaves apparently classically as part of the large-scale world of common experience. Deutsch does call attention to this point, but like Everett and DeWitt he DOESNOT offer ANY proofs THATSUCH. A classical basis must emerge from the formation itself. We shall discuss THE question in more detail in the next section. A yet more serious question THAT we shall discuss here is concerned with THE significance of THERANDOM ensemble of universes THAT. Deutsch HAD2. Assume in order to give meaning to the concept of probability. In a given branch of the wave foo NCT ion, after the measurement process is over, the quantum state of the whole set of particles will be well defined. But once such a quantum state is given, no FURTHER differences WITHIN are possible. At least according to the usually accepted form of THE quantum theory itself, which asserts THAT the wave function gives all possible physical information about the system. How THN do the many universes INTHE same quant STATE differ? Deutsch does not make this clear. It is difficult to see how one could avoid the further postulate that there is an additional randomly distributed parameter or set of parameters not present in the ordinary quantum theory. WHICH would describe THEIR differences. But to do THIS is to eliminate the key advantage claimed for THE many worlds interpretation, i.e., that it introduces no b as ICALLY new physical concepts or equations or parameters. Indeed, our own interpretation has been criticized just because it does introduce p-article variables as new parameters. At the very least, we could claim THAT/THSA variables are relatively easy to understand, whereas with Deutsch's random distribution of universes it is not clear how such parameters are to be understood. Deutsch's approach has been applied THUS FAR to the DeWitt interpretation, in which it is supposed that a multiplicity of universes actually exists. Whether THIS approach can also be applied to the Evera TTINTERpretation is not clear. Let us recall that for Everett there is only one total universe with many points off by EW, each of which corresponds to a particular memory or awareness. THAT is within its total universe. What seems to be called for is a random distribution of awarenesses over various quantum states with relative frequencies equal to the usual quantum mechanical probabilities for the associated results. To put this notion more precisely, let us represent the total wave function of the universe by 1311, where cent represents the I1H state of awareness and 1/j represents the state of the rest of the universe. T hat corresponds to IT. The assumption analogous to THAT of Deutsch wow LDB that IC 1, 2 represents the relative freq NCY. of awarenesses of state I corresponding to the I1H component of the total Hilbert space vector IL. However, there appear to be difficult ties with THIS suggestion. Consider, for example, a situation in which some fraction of the observers while dBE killed in a catastrophic event so that their memories would vanish. How would the statistics be formulated to take care of such a possibility? To some UPTHN, it does not seem that there is as yet an adequate treatment of probability within the Everett interpretation, while even WITHIN. The DeWitt I interpretation, Deutsch's further assumptions seem to be able to provide THs only by foregoing the CLAIM THAT no new basic prink IPLESR needed beyond those of the current quantium THE ORI. 13. 50 and THE preferred basis and THE classical limit. One of the key remaining ambiguities in the basic formulation of the MA New York world's interpretation is the question of how the classical limit is to be treated. As we HAVESEEN, DeWitt's expressed intention was to avoid the assumption of a classical limit. Everett W is less clear on this point, but the general tenor of his approach suggests a similar attitude. However, if we accept this, then we are required either to show that something like a classical limit is contained implicitly in the many worlds interpreted on, or else to show THAT such a limit is not needed. Yet nothing like THISH as BEEN done so far in an adequate way. ASWHAVEPO int OUT, DeWitt appeals to an as yet vague notion of complexity, and he SEEMS to imply THAT-THIS would take care of yielding the relatively well-defined and stable kinds of results that are usually comprehended in terms of a classical limit. On THE other HAND Everett explicitly denies that any such property of complexity is needed. Thus Everett, 27 writes, "We impose no restrictions on the complexity and number of degrees of freedom of measuring APPARATUS or observers, and if any of these processes are present, such as heat reservoirs etc., then THSA systems are TOBE simply INCLUDED as PART of the APPARATUS or observe ER. THISLACKOF explanation of why the actual world of common experience corresponds to some kind of CLSICAL limit H has indeed been noted by Deutsch 25. As we HAVE already pointed out in the previous SECT ion, he acknowledged guess THAT there is some SUCH favored B as is for interpretation. Nevertheless it is CLEARTHAT the basis must be ESUCH as to somehow bring about the correct CLSICAL limit. But Deutsch does not provide an answer to the question of how this basis is related to the CLSICAL limit. We know THAT, in DeWitt's version of THE many worlds interpretation, it is also necessary to HAVE the sort of preferred basis as has indeed been pointed out by MA New York authors, B. A. Lentine 2, Bell 3, Cooper and Van Vechten 4, D. Espinat 5, and P. R. Imas 6. To bring out what is required, we know THAT this basis determines THE. Elements THAT correspond to the many worlds INTO which a particular UNI. Verse MAY further split. Some authors HAVE suggested further MA thematical assumptions THAT they hope might lead to determination of THIS basis. For example, ZA28 suggests THAT there is a unique analysis of the total wave function into relative states, called the SCHMIT DE composition, and THAT. This would deal with such question as but without further concepts and Assumptions 1 can easily see THAT such a treatment while D still be M. Big UOUS. THUS consider an atom in some linear combination OFP states. Where 7, underscore, 1, 0 and 1 slash, plus represent wave functions in which the Z component of the angular AR momentum is respectively, h, 0 and h. Clearly DeWitt S. Splitting of universes CANNOT goes so far as to imply THAT such an atom by itself would split I into 3 copies with angular momentum WELL defined. I in the Z direction. I indeed if THIS were to HA pen, the theory while D fail to agree with experiment in a domain THAT is well tested. We would not expect this sort of thing to HA pen even with medium-sized molecules. But as we approach the LARGE scale world of common experience, the MA New York world's interpretation forces us to assume THAT at some point the universe does begin to split in THIS way. JUST where does this HA pen? As we have remarked earlier, it is necessary in DeWitt's approach to develop some new parameters such as complexity and new equations that will determine where THE split will occur. But as we have seen, if we do this, the basic claim of the many worlds interpretation that it does not introduce new assumptions and principles will again fail. A similar problem can be seen to arise in Everett's interpretation, but. Here it involves a certain ambiguity as to what is to be meant by awareness, memory or mind. Thus, for example, Everett's concept of relative state could be applied to a single hydrogen atom whose wave function may take the form IL equals LC, 1b, Z, / I, Y, where Z is the coordinate of the nucleus and YTHAT of the electron. If we were to apply Everett's theory at this left EL, we would have to say that THE electron is aware of the proton and that the proton is aware of the electron. It would indeed follow that the overall awareness associated with THE hydrogen atom as a whole would split into many correlated states of mu. Mutual awareness of the electron and the proton, which states are, however, not aware of each other. This would imply that everything was aware of everything else and that human awareness, or indeed machine awareness, were only special C as ES of TS. It is certainly not clear what such a theory could mean. If it were Everett's intention to propose THIS sort of theory, it would have up to him to go into what he means by universal awareness of everything by everything. For such a notion is evidently far more radical than anything that arises in the commonly accepted views of the many worlds interpretation. In the absence of any discussion of this point by Everett or by those who follow him, we must assume that such a radical version of his interpretation was not his intention. But then this immediately raises the question of JUSTWHAT determines the conditions for awareness to exist. As we have seen, Everett expressly denies that the notion of complexity is basically relevant to his theory. Yet it seems evident because of his referring to computers and memories that he has tacitly in mind some kind of complexity, as well as stability, as a basis for awareness. This means THAT he faces essentially the same difficulty as DeWitt. He will have to introduce some new assumptions as to what constitutes the conditions for awareness and new LAWs determining just when these conditions are satisfied. Recently these questions have been re-examined by Stapp 29 and by Albert and Lower 20 in what is called the many minds eye interpretation. The key step here is to assume that awareness or consciousness is not b as I cali a physical property, but rather a property of mind which is supposed TO be entirely different from matter. THUS the theory, UN like Everett S. assumes a dualism between mind and matter along LINESSI Myler TO that proposed much earlier by Descartes. The advantage of this approach is THAT we do not need to assume THAT matter H as properties given TO it by awareness, i.e. THAT physical meaning can be given in the quantum theory to all branches of a linear superposition of wave functions without contradisting apira NCES. It thus makes possible a more consistent way of separating one doma in, M at that satisfies the superposition principle of quantum theory and another domain, MIND, that does not. Such a dualist approach is in certain ways reminiscent of Wigner's Sug. Gest ions 1-1, but must be remembered that in the latter, mind and matter are supposed to interact in a two-way process. In the many minds interpretation however there is no such interaction. RATHER mind is assumed to be capable of becoming conscious of certain aspects of the state of matter, with OUT influencing THE latter in any way at all. The many minds interpretation SHA residential with Everett the assumption that physical reality corresponds to the total wave function of the universe. Likewise along with Everett, it assumes THAT on the large-scale stable configurations of matter exist which make possible not only measuring instruments, but also a reliable memory of what the results of measurement are. We call INTHEEV Everett theory that the wave function describing relevant parts of the spin measuring apparatus and the memory is given by equation 133 equals O, x plus, m, cent plus, y, tp plus, s, plus f3x, m, cent, y, t slash j, s. The basic new assumption relative to Everett SIS that each PER sun H as a total me and DTHAT can split into many subminds that are not aware of each other. Each me and DCAN be aware of a particular broad IN state corresponding to a memory of a particular experimental result that is stable and distinct from other memories corresponding to different possible results of the experiment. Let these minds be represented by plus and underscore. If the me and D were in the domain of quantum mechanics, the wave function would then be in a linear superposition. F equals O plus X plus M, cent plus, Y, TP plus, S, plus F3X, M, Y, T slash J, S. But here is where a break is made with the basic principles of quantum mechanics by assuming that plus and underscore do not superpose. We further assume a random process in which the original mind M has split I into two distinct new minds, plus and underscore. The mind plus is aware of the physical situation whose wave function is x plus, m, cent plus, y, tp plus, s, and mind underscore is aware of the physical state corresponding to the wave function with the minus sign. Neither plus nor underscore are aware of each other. In the further development of this process, there will be additional splits in the mind. For example, if some physical property corresponding to a wave function n is measured and remembered, there will then be a total of 2 n minds aware of the n physical states, n, corresponding to measurements and memories of both the spin and the new property. In the random process in which the mind split S, we assume THAT-THE. Probability of a particular mind being associated WITH the N1 physical state and a particular spin variable plus is proportional to ln 1 2. As time goes on there will be a constant process of further splitting of the min D. ALL of this is very close to the treatment given by Everett and differs. Only in that we have further assumed a unique last stage, i.e. mind, in which the linear superposition fails, whereas Everett says nothing about THIS question. By thus defining this unique last stage as a splitting of the mind and relating THIS split to the linear superposition of memories in THE brain through random processes, THE many minds interpretation avoids difficulties of specifying the B as IS in which linear superposition breaks down. And the other HAND, THIS advantage H has been gained at the expense of not only bringing INDUALI tie of mind and matter, but also of having to assume special properties of mind which are difficult to understand, i.e. the ability to be aware of matter with any interaction and the ability to split in a random way into many minds, each of which is associated to a particular physical state. It show ULDBPO without HERE that the many minds interpretation does not imply non-locality. This comes about because reality is assumed to be in perfect correspondence with the total wave function of the universe, and because the whole of this reality is covered completely by THE perceptions of the many minds which have no effect on the wave function. Because Schrödinger's equation contains only local interactions, its development is entirely local even though it has to be expressed in configuration SPACE. Each mind becomes aware of only one facet of THIS multidimensional reality. The perceived classical world is then a result of the fact that each me and D is only aware of a small part of THE whole. THE perceived classical world is in a sense an illusion. What is illusory is that this part is the whole. If it were seen to be merely a facet, then there would be no illusion. To conclude, the many minds interpretation does remove many of THE difficulties with THE interpretations of Everett and DeWitt, BUTREQUIRES, making a theory of mind basically to account for the phenomena of physics. At present we have no foundations for such a theory. Indeed, even to consider the mere possibility of this sort of assumption, we have further to suppose that there are new kinds of LAWS uniquely relating real physical properties such as awareness, to parts or components of the total vector in Hilbert space. As we have point out in section 1.3. 2. This is equivalent to assuming that the state of awareness is not limited by any hing like THE uncertainty principle, clearly a gigantic step beyond present day physics. Thus even if we succeed in developing such a theory, it is clear that we will require new principles, new concepts and new equations. This means, once again, that THECL aim of the many worlds interpretation to avoid the addition of speculative new assumptions will fail. 1.3. 6. Comparison between our interpretation and that of the many worlds. One of the first objections that tends to arise against the many worlds interpretation is that its assumption of an infinity of universes or minds, almost all of them being unobservable, violates the principle of OCCAMS razor, i.e. that we should not introduce a multiplicity of unnecessary assumptions. H.O. Weaver, the proponents of THISI interpretation, answer such objections by saying, e.g. with D.E. Spignat 5, that multiplication of worlds entitles one to economize on principles. Or as Primus 6 has said, the evirit in interpretation is superior in logical economy. As we have already indicated. They would criticize our interpretation by saying that in addition to postulating the reality of the wave function, it brings in the further concept of particles with their equations of motion. It is thus clear that they feel that the many worlds interpreted T-ion is superior because it does not do this sort of thing. Leaving as IDE this question for the moment, it shall be said that our interpreted T-ion accomplishes a number of things which cannot be done in the MA New York world's view. Firstly, as we have seen in Chapter 8, it gives a simple and coherent account of why the large-scale world of common experience should be essentially classical. This is demonstrated by showing that the quantum theory implies a relatively autonomous domain in which the quantum potent IAI can be neglected, so THAT an approximately classical behavior will result. The physical structures of observers are also manifest in this domain. As pointed out in Chapter 8, it is a well-known fact that our sensory information comes from this level. From this it follows that we are directly aware of the particle aspect of the universe through the senses, and that the more subtle wave function aspect is INFER read by THOT about our sensory experience in the domain that is manifest to the senses. We are therefore not basing our approach on the assumption that we are aware only of particles. Rather, we are simply making use of the fact that, at least in science as we know it thus far, all information comes ultimately through the manifest level, our echoing. That it comes not only through the particles, but also through the classical limit of electromagnetic field beables. The second advantage of our interpretation is that we do not have to assume the relation P equals 1 yen 1 to ab initio, but that we are able to arrive at this on the MANY WORLDS int ERP re TATION 315 as an equilibrium distribution resulting from chaotic processes. Finally, we cite WHAT we regard as the main advantage, which is THAT. It gives an intelligible and intuitively understandable account of how quantum processes take PLAs. It is clear at the many worlds interpretation cannot do any of these things. As we have seen earlier, it does not provide an adequate account of the large-scale behavior at the classical limit. Moreover, it is compelled to assume the relation P equals L2, e.g. as was done by Deutsch. And it gives no intuitively intelligible account of how quantum processes take place. With regard to the latter point, it defies the imagination to grasp into itively how the universe could split, and even more as to how it could be doing so in a stupendous number of ways. It equally defies the imagination to grasp intuitively how awareness could split into many parts THAT are not aware of each other, and even more so how awareness could be, in EFFECT, identified with some part of a vector in H. Hilbert space. Let us then consider once again the claim that the many worlds interpretation is THE1. THAT is most economic in concepts and principles. We have seen, however, THAT in order to introduce probability in a consistent way, Deutsch had to assume an infinity of universes in the same quantum state, and in effect to imply a random distribution of these universes over an undefined parameter whose nature is completely unspecified. As we have pointed out earlier, he has thus in essence said the new particle variables by a new parameter that LD distinguish the various universes. So there is no advantage in the number of hypotheses. Moreover, there is the disadvantage that his new parameters are far less clear in meaning than others. If we adopt DeWitt's approach, then, as we havesen, it is necessary to supplement this with some further principles in VOLVING, perhaps an as yet unavailable definition of complexity and further equations determining Just how this would determine the splitting of univ versus O and the other. Ha and D, if we adopt Everett's approach or indeed THAT of THE many minds. Interpretation, we have to do something similar with regard to THE splitting of awareness. In this connection, a complete and consistent expression of these interpretations would, as we HAVESEEN, require new principles and assumptions of a speculative nature going beyond the current Chu-antum THE and beyond our present knowledge of awareness and its possible relationship to Hilbert space. In view of all these unresolved problems, we have been led to ask WHYTHE. Many worlds interpretation seems to be so attractive to some physicists. Of course WE realize that THE Hilbert space formulation of quantum mecha NICS has a great deal of symmetry and may therefore be felt to possess great BEAUTY. Hence it is understandable THAT there may be great reluctance to give it UP or to go beyond it. On THIS basis one can see that THE greatest advantage of the MA New York W-World's interpretation for ITS proponents is THAT it. Provides an ontological formulation which relates all its basic concepts only to Hilbert space. In effect it says THAT everything CANBPUT in some correspondence with Hilbert SPACE. The phi RST priority is thus to maintain the notion THAT all basic structures of concepts HAVE to be expressed in terms of Hilbert SPACE. As long as THISCAN be done, it is felt THAT all sorts of further assumptions are possible, and THAT these do not count heavily as new principles. For example, THE assumption THAT the mind can be PUT in correspondence with a component of a vector in Hilbert space is considered to be of minor importance compared with maintaining the universal validity of the cons PT of Hilbert space itself. Similarly with regard to all the other assumptions THAT we HAVE out L inter E. We see AN however as K whether symmetry and BEODR al WAYS assure. Sign THAT we HAVE reached an ultimate truth THAT can never be altered. THRU further inky RY. Indeed in our approach, WHH we shall explain in more detail in THE next CH after, WE argue THAT there is no reason to assume ultimate TRUTHOFANYPA reticular feet UREOF no WL edge, however. BEAUT ifl we may feel it to be over from our discussion of the MA New York World's interpretation, WHICH shows THAT it H has not yet fulfilled its claims to economy of principles. It does not seem to be justified to dismiss THE assumption of new concepts in OUR interpreted TION, SUCHSPA radical var IA bless. THAT go beyond DWHATCANBE accommodated in terms of Hilbert SPACE. As we have already remarked earlier, we feel THAT many worlds in interpretation H as interesting possibilities, BUTTHAT its presentation while DB greatly clarified it if were frankly admitted that some of its basic hypotheses are of a highly speculative nature. Indeed the MA in motivation behind the many worlds interpretation is, in our VIU, not really the minimization of principles and hypotheses, but RATHER it is to retain Hilbert SPACE as THE ground for THEB as I sequence PTUAL structure SOTHATEVERYTHING in the THE ORI can be formulated in terms of Hilbert space. It could be valuable to develop such a theory, but it has to be said THAT before THIS is actually done in an adequate way, many as yet unresolved difficulties have to be dealt with. We shall go into THIS question further in the succeeding chapters. Ch. Chapter 1.4. Extension of ontologic althe beyond the domain of quantum mechanics. 1.4. 1. Introduction. Thus far our discussion has centered on various interpretations of the CUR rant. Qua entum the ori. But one of the implications of an ontological approach is that within its conceptual framework it is possible to contemplate certain modifications and extensions of the mathematical laws that go beyond the domain of the current quantum theory. In this chapter we discuss a number of suggestions along this line made by various authors, and in THELST section 146, WESHALL also include some of our own proposals for doing this. 1.4. 2. Our general worldview, including our attitude to physical and mathematical aspects of basic concepts. Before going on to a detailed discussion of our proposals for the extension of quantum mechanics in new ways, we would like to give the outlines of our general worldview. This will help make more clear what our motivation is in developing our theories. In addition, it should help to clarify certain differences between our attitude towards basic physical and mathematical concepts and THAT, which seems to be behind most of the other approaches. We shall begin by discussing the latter question first. Thus WEHAVESEEN. In the previous chapter, for example, that the basic attitude in THEMA New York world's interpretation is to take the present general mathematical formula of quantum mechanics as the essential truth and to try to derive the physical interpretation as something that is implicit in the mathematics. Many speculative new assumptions have been made within this mathematical framework, but the first priority has been to redefine this framework as the 3. GROUNDFORTHE general CONCEPTUAL structure. Some OFTHE proponents OFTHE MA New York worlds interpretation, for example, DUTSCHL as WELL as Gelman. And HARTL 2, WHOSE work will be discussed further on INTHIS chapter, are even ready, at least in principle, to consider extending their theories be yon the current QUANTUM mecha NICS. In addition, the same may be ESAID of Girardi, Rimini and Weber 3, whose work we will also consider later in THIS chapter. However, even these authors are in essential agreement THAT. WHAT should not change is the requirement THAT the Hilbert space, and its natural extension to an infinity of dimensions, while dbe the basic structure. In terms of WHICH all other concepts must be expressed. This attitude towards the mathematics H has not always been dominant in physics. Indeed, until the pre-20th century, the physical concepts were, for the most part, considered as primary, while mathematical equations were regarded as providing a more detailed and precise way of talking about THSA. Physical concepts. H.O. Weaver, during the 20th century WITH the advent of quantum theory, and to a lesser extent, relativate Y, the mathematics. BECAME much more HIGHLY developed and physical interpretation much more abstract and indirect as well as much less clear. As a result THE was a constantly increasing focus on the mathematics, while the PHYSICAL ideas were given less and less importance. Thus during the 1920s Sir James Jeans said THATGOD must be a mathematician, I'm plying by this THAT the UNIV was constructed on a mathematical plan and THAT its essence is best grasped. In terms of the mathematics itself lat Heisenberg went much further. Allo ng these lines and SAID very explicitly THAT the S and TIAL truth W as in the mathematics. THIS view has become the common one among most of the modern theoretical physicists who now regard the equations as providing their most immediate CONT with NA THE experiments only confirming or refuting the correctness of this contact. So without an equation THR is really nothing to talk about. On the other hand, in the past we began talking about our concept of physical reality and used the equations to TALK. About THEM. 10F the reasons THATOUR interpretation of the quantum theory may not have been so well understood is perhaps THAT it is not commonly realized that we have different attitude to the mathematics. Our approach is not simply a return to the notion that the mathematics merely enables us to talk about the physcal concepts more precisely. Rather we feel THAT. These two kinds of concepts represent extremes and THAT it is necessary to be in a process of inking that moves between THSA extremes in such a way that they complement each other. We fully accept that progress can be made from the mathematical side alone, but we feel that to stick indefinitely to this approach is too limited. For example, starting with Schrödinger's equation expressed in The Extension of Ontological Theories 321. H. A. Milton J. Akabai. 4. We were led in Chapter 3 to a new physical concept of a particle which one's affected by a quantum field in a way that depends only on the form of the latter and not on its amplitude. With the aid of the concept of active information implied by this behavior, we can first of all obtain a coherent explanation of the quantum process which gives us new MS1GHTSMTO the quantum theory and enables us to understand it in a different way. But we do not regard these physical concepts as mere imaginative displays of the meaning of our equations. In Saint Ad, as we shall see in this chapter, we can then move to the other side of this process of thought and take our physical concepts as a guide for the development of new equations. In this way we are engaged in at least the beginning of a kind of thinking in which the clue for a creative new approach may come from either side and may flow indefinitely back and forth between the two sides. It should be clear from the above that we do not expect to come to the end of this process of discovery, for example, in a form that is currently called the theory of everything. Rather our view is that nature in its total reality is unlimited, not merely quantitatively, but also qualitatively. In its depth and subtlety of laws and processes, cd bohm 4. R. K. Knowledge at any stage is an abstraction from this total reality and therefore cannot be expected to hold indefinitely when extended into new domains. In any case it is evident that THR is no way to prove that any particular aspect of our knowledge is absolutely correct. Indeed, no matter how long it may have demonstrated its validity, it is always possible that later it may be found to have limits. For example, Newtonian physics, which held sway for several centuries, was found to be limited and gave way to quantum theory and relativity. Yet just before TH's revolution took place at the end of the 19th century, Lord Kelvin, one of the leading physicists at the time, advised young people not to go into physics because it was finished, and only subject to refinement in the next decimal places. Nevertheless, he did point to two small clouds on the horizon, the negative results of the Michelson-Morley experiment and the problems of black body radiation. It must be admitted that he chose his clouds correctly, though he totally underestimated THEIR importance. Nowadays physicists are similarly talking about an ultimate unified theory including the four forces and perhaps strings, supersymmetry, etc. that would explain everything. However, it can hardly be said that the clouds in this picture are only two and restricted to being small. Our notion of the qualitative infinity of nature can usefully be brought out by considering the role of the atomic hypothesis of Democritus WHH. We have already discussed in chapter 1-2, section 1-2. 8. Not only did this hypothesis show the importance of speculative new concepts going far b. 322 undivided universe. Yon WHAT could be demonstrated at the time of its proposal, but it also exhibit at a further key fature that we would like to emphasize here. This is THAT. Deeper explanations often imply the limited validity of what were previously accepted as basic concepts, which later are then recovered only as approximate ions or limited ngc as es. This relationship of concepts is indeed typical of the whole of our experience. For example, as we go round a circular table, WHAT we see immediately is an ever-changing elliptical shape. But we have learned to regard this changing shape as a mere appear ance, while the essence the true being, is considered to be a rigid circular object. This latter is known first in thought, but later this though UGHT is projected into our immediate TE experience. So THAT the TABLEVEN appears to be circular. But further investigation shows that THIS object is not solid and even twilly discloses an atomic structure. The solid object now reverts in our thought to the category of an appearance, while the SNE is the set of atoms out of which it is constituted. However, deeper studies THN showed THAT even the atom is an appearance and that the essence is a nucleus surrounded by moving planeta Ry electrons. And later still even THESEPA radicals were seen to be appearance S, WHILE. The essence was a set of yet more Fu and Da mental particles such as quarks, gluons, preons, or else sets of excitat ions of string S, etc. But, in all of this development of our knowledge, it seems whatever we have thought of as matter is turning more and more into empty space with an ever more tenuous structure of moving element S. This tendency is read further by quantum field theory, which treats particles as quantized states of a field that extends over the whole of space. WHAT has been constant in this overall historical development is a pattern in which at each stage, certain features are regarded as appearance. WHILE others are regarded as of an essence which explains the appearance on a qualitatively different basis. But what is taken as essence at any stage is seen to be appearance of a still more fundamental essence ultimately. Everything plays both the role of appearance and that of essence. If, as we are suggesting, this pattern never comes to an end, and ultimately all of our thought can be regarded as appearance, not to the senses, but to the mind. What science is aiming for is THAT these appearances be correct, i.e. that the actions flowing from them, such as experiments, be coherent with what the appearances would imply. Incorrect appearances are thus either mistaken or illusory. The progress of science then implies the elimination of mistakes and illusions and the development of new sets of related appearances at various levels. Thus with the table to have the appearance of an elliptical object is correct only in a very limited sense. By bringing in the thought that the object is a rigid circle, we obtain a more nearly COR extension of ontological theories 323. Rect overall set of appearances. The thought of the atomic structure then makes the whole set still more nearly correct and so on. Thus what we are doing is constantly extending the appearances with the aid of thought. The ultimate reality is unlimited and unknown, but its successive appearances serve as an ever more accurate guide to coherent action in relation to this reality. Another way of looking at the notion of appearances is to note that appearances basically are what arise in our perception of the world. As we have seen, the appearances in sense perception give rise to inferences about an sence that might be their origin, but this essence, which is seen in thought, turns out to be yet another appearance and therefore still part of our overall perception. No matter how far we go, we are therefore involved basically in PE reception. Our theories are not primarily forms of knowledge about the world, but rather, they are forms of insight that arise in our attempts to obtain a perception of a deeper nature of reality as a whole. As such, we do not expect their development ever to come to an end, any more than we would look forward to a final sense PE reception. This view of theory as PE reception can be found in Bohm 5. At any stage in the development of perception as described above, there is always further room for new concepts which serve as ways of looking at reality. Such concepts may, in our approach, be either physical or mathematical or both. Thus we do not suppose that physical concepts are merely something to be put in correspondence with the basic mathematical concepts. Nor do we suppose that the mathematical concepts are necessarily subordinate to basic physical concepts. Rather, both of these are appearances, and their relationships may provide a yet more comprehensive appearances which guides our action towards the unlimited and unknown reality. The imaginative qualitative concept is therefore, in the long run, just as key a feature of THIS overall appearance as is the precise and abstract mathematical concept. The two together not only present a more comprehensive appearance than either one alone could do, but each can serve as a clue for further development in the other. In all scientific theory may even go so far as to throw some light on the observer, to whom all appearances are supposed to be taking place. But as with everything else, even such theories are only further extensions of appearances, so to speak, which give the observer a mental mirror in which he or she is reflected. There will therefore be no final theory of the observer. The ultimate nature of awareness is unlimited and unknown, like that of the universe as a whole of which it is a part. In the next chapter, we will make further suggestions as to how the universe can include observers, which are along the lines described above. It may be readily seen that this general approach implies a certainkInd. 324 undivided of limit to determinism. Forinit, each theory is evidently an abstraction from a totality that is inherently unlimited, both qualitatively and quantitatively. As such, it evidently cannot be entirely self-determined, because it always depend dsi and various ways on whath as ben left out. So thenecessit of its self-determination is only relative and not absolute. Even here this self-determination may include unstable Chow tic orders, which approximate randomness. However, even the chaotic or stochastic character may be contingent and determined by condit ions in domains not covered by the particular theory in question. For example, random variations in the traject theory of a Brownian particle may be partially or even totally determined by atomic motions at a deeper level. So ultimately our overall worldview is neither absolutely deterministic, nor absolutely indeterministic tic. Rather it implies that these two extremes. Our abstractions which constitute different views or aspects of the overall set of appearances. Which view is appropriate in a given CSE will depend both on theUNKNOW totality and on our particular mode of contact with it, e.g. THEKINDSOF experiments WERABLE to do. So as the situation changes, different views are constantly CALLED for. But the unknown and unlimited essence is not restricted to any of these views. Rather it may be thought of as somewhere between them and ultimately beyond them, as indeed it is beyond WHAT can be CA-ordered in THOG-HT, which is always limited to some abstraction from the totality. For a more detailed discussion of this approach, see Bohm 5. The above is a special case of how even our basic concepts and categories of thought are ultimately appearances. If THIS is so, WHATTHN is the point of making an ontological interpretation of the quantum theory? 2. Answer THIS, we FIRST point out once again that every theory is not only a mere appear ANCE, BUTTHAT it is more, in the sense THATIT's basic concepts must be said in some sense to reflect reality within its own domain. In other ontological theories suggested thus far in physics, it is either implied or asserted that such basic concepts correspond to independently existent realities, for example, not dependent on context or deeper levels of being. In our approach, however, the basic concept of a given theory may reflect a reality THAT is inherently dependent either on context or on deeper levels or on BOTH. For example, the elliptical appearances of a circular object may be seen as realized by considering the light coming from the object to the eye, and the eye makes an elliptical image which is in some way read BACKIN to the brain. This we may consider to be an essential part of the reality corresponding to the elliptical appearance. Clearly THIS reality is not independently existent but depends on a context including the whole process that we have mentioned, as well as much more and particularly on the circular object TWHICH is taken to be the essential meaning of the elliptic. XTENSION of ontological theories 325. Calipia RANCES. But then the circular object is found to be dependent for its existence on a wide range of contextual parameters, e.g. temperature, and a spec IALLY on the atomic constituents WHH are considered to be its essence. We find a similar behavior as we go through a series of deeper SENCES and Apira NCES. In particular, as we come into the quantum domain, we find DTHAT it is Necessary to state the relationship between essence and appearance explicitly by considering a totality which includes THE measuring and G instruments as well as WHAT is measured. In this case, the appearances SH out TH themselves. In the instrument, WHILE the essence is the whole quantum ontology of quantum fields and particles. The reason why the totality must explicitly include the appearances is that there is an irreducible participation of object and observing apparatus in each other in the quantum domain, while in THE domains treated by previous theories, THE relation between essence and appearance can be neglected or else taken as only implicit. Because SENCE and appearance HADTH us to be considered as a totality. This created a serious problem for THE extension of the traditional approach into the domain of the and theory. When THE quantum theory was first developed, people did not see how this question could be approached onto logically. Instead THR was developed a basically epistemological approach of Bohr 6, Heisenberg and von Neumann and in which the fundamental concepts of the QUA entum THE were taken as representing only KN knowledge. The feeling THAT any other approach was impossible seems to have been grew and ed in the assumption THAT any ontological approach would have to have a phi nalsence that was not dependent on an ything else at all, so THAT it would never be necessary to consider essence and appearance as a totality, as we have done. To some although each form of thought of the essence is an prance, it also reflects a reality that is however always dependent for its existence as well as for its qualities and properties on broader contexts and deeper levels. This is one of the senses in which the theory is ontological. In spite of the fact that all thought gives appearances. In addition, our approach provides a reflection of reality that is in the form of a totality, including the measuring instruments along with everything else. This does not mean, of course, THAT it tells us everything about the universe or THAT. It gives a phi NAL picture. Rather, as we shall bring out in more detail in the next chapter, one may here use the analogy of a hologram, in which any part of the record gives us information about THE whole object rather THAN a part of it. This feature of our ontological approach is evidently especially important in cosmology, and it is also important if it is ever our intention to understand the relation between the observer and THE observed. In addition to all of this, our particular ontological interpretation as THE fu are their advantage THATITCAN be grasped more readily in an intuitive and imaginative way than is possible with a basically epistemological interpretation such as, for example, THAT of Bohr. Besides, as we shallcin. Section 1460 it makes possible certain kindsof extensions of the basic equations which would not be possible in a purely epistemological approach. Thus it opens the mind to exploration of new domains which would not be discern iblew without the ontological concepts. It is not that we want to dismiss the epistemological approach totally, but rather that we feel THATBOTH approaches HAVE to be pursued and perhaps ultimately brought into relationship. Finally the view that our THEORs constitute appearances does not deny the independent reality of the universe as a whole. Rather it implies that even the appearances are part of this overall reality and make a contribution to it. What we emphasize is, however, that the content of the theory is not by itself the reality, nor can it be E and P effect correspondence with the whole of this reality, which is infinite and un no wn, but which contains even the processes that make theoretical knowledge possible. It is our view that this approach provides a more coherent understanding of the relationship of theory to the reality towards which at GUIDUS, than do other approaches. THAT are currently available. As we indicated in the introduction, a number of new ontological approaches, in principle going beyond the current quantum theory have been suggested. WHICH in common that they aim to preserve the notion that Hilbert space, with its natural extension to an infinity of dimensions, is the basis of the entire conceptual structure. One of the most interesting of these is the undivided dynamics for microscopic and macroscopic systems of Girardi, Rimini and Weber, GRW, 3. We give here a simplified treatment due to Bell 7. The wave fund CT ion JR1, R2, Rn, T, is assumed to evolve according to Schrödinger's equation. However, there is a further process which reduces the spread of the wave function over EACHP article coordinate, Rn, to something of the order of a new universal constant A. This is in a certain way similar to the process of collapse in the von Neumann interpretation, but the differences are that 1. THIS is happening in GENRL and not JUST in a measurement process. And, 2. This process constitutes a well-defined extension of THE quantum mechanical LAWS of the development of the wave function. At first sight T might seem that IFAIS chosen small enough to bring about the kind of localization needed for a classical object, then this might extension of ontological theories 327. Contra DICT the quantum mechanical predictions of interference over fairly largedi stances. F or a more detailed account of this point see Shimony 8. And we INBERG 9. HOWER, it should be recalled that quantum mechanical interference properties over long distances have been extensively tested for the C as E of a single p article 10, 1, 1, and at most for a few p articles 1, 2. We can avoid this difficulty by supposing that the rate of decay, A, depends on the number of p articles, n, involved. Thus we can write A equals n/r, where T is a characteristic time which is a new constant of nature. R can be chosen such that the rate of decay of the original wave function is negligible for a system of a few particles and quite rapid for systems with ma New York p articles, e.g. of the order of 1020. To simplify the discussion, we assume a process in which the spread of the wave function is reduced to summit hing of the order of a around a center. ZWHICH is distribute at random. For the n1p article this process can be regarded as transforming the original wave foo n-cation 1/j, r1, r2, r, n, t, into a new wave function. 141. The factor f, z, is normaliste accord ding to 142. GRW suggested that f, z, be a Gaussian, for example, f, z, equals IEXP. Dash 2. 2. 2. 143. 144. The center z is distribute at random with probability 1 rn. Z, L. 2. We are assuming that each p article is undergoing this process of NAR. rowing down the range of the wave function so that after a time t/n, the wave function will be reduced more or less to something having arange a for each particle. Interference will then be negligible beyond THIS range. But WILLBE as predicted by quantum mechanics within this range, provided, of course, that we are considering times appreciably longer than t/n. It show ULDBE clear that the above assumptions will enable us to satisfy our requirements. THATLARGE scale systems, such as the observing apparatus, will be fairly localized, while systems of a few particles need not be localized. 328 The undivided universe. It is possible show how THEGRW approach allows a consistent treatment of the measurement process as a SPECIALCASE of the general PRO. SES-INWHICH the wave fun CT-ion of a system of many particles n arrows dow n to a fairly WELL defined region, as shown in Chapter 2, Section 2. 4. The wave function after the interaction between apparatus and the observed system. IS 145 n. WHERZ represents the coordinates of the observed system, of WHICH there are only a phi W, while Y1, year represent all the internal coordinates of the APPA radius, Y represents the center of mass coordinate of the APA. Ra thus WHICH is directly observed at an essentially classical left e.g., the pointer position, after the interaction is over the n do not overlap in. The coordinatey, but as pointed out in Chapter 2, Section 2. 4, there is still potentiality for interference as long as we haveali near superposition of THIS kind, however, if we bring in the GRW process of n arrowing down the wave function to something WITHARANGE of a, and if THE separation in the center of mass coordinate y of neighboring wave PA its is considerably greater than a, then THIS possibility of interference will be destroyed. To see how THIS happens, we note that if we consider an ensemble of experiments, we will find that in some cases the wave function, 1 4, 5, will collapse to one packet and in other cases to another, so THAT we will be left with a random distribution of well-defined results. It is easily shown THAT the probability of the M1H result ISIC M1. 2. In agreement with the usual quantum mechanics. It is still necessary, however, to be sure that the GRW modification of the dynamics of microscopic constituents does not imply physical LYUNAC. Acceptable consequences for the dynamics of the whole system, GRW go into this question in some considerable detail, and show that no such acceptable consequences will arise. In doing this, they are led to suggest values for the universal constants. Extension of ontological theories 329. A10. 5. cm. T10. 16. SEC. Objects containing many particles will THN be localized to within 10. 5. EMS. A one-particle system will not be localized in less than summit HING of the order of 10.9 years. But a system of 10.20 particles will be localized in 10.4 SECS. In comparison, our own approach introduces a random distribution of particle positio ns, C with a probability density equal to LIP, OL2. Whether one regards the GRW approach as having a greater or lesser economy of assumptions depends primarily on whether or not we give phi-rst priority to retaining HILBERT space as the basic mode of expression of all concepts. However, we can add that thus far our approach is well defined and thoroughly worked out, whereas the assumptions of GRWH have evidently a great deal of arbitrariness in THM. Of course one might adopt the attitude that THIS arbitrariness may eventually be read UC ed BYTHE development of further new ideas. But here one should note THAT it seems DIFFICULT to include the GRW approach in a relativistic context. For it H as all the non-locality of or DINA requantum theory and possibly some additional ones. Therefore, it seems likely that fu RT her new developments of this approach may lead to the need to assume a deeper non-relativistic level, rather as we HAVEHAD. To DOIN our own interpretation as explained in Chapter 1-2, Section 1-2. 8. Leggett, 1-3H as yet another approach which is in considerable sympathy with that of GRW. As we HAVE already indicate in a previous chapter. HE wants to introduce a new concept of complexity in the form of WHAT. He calls DIS connectivity. In a macroscopic object it is to be expected that this DIS connectivity is very large and he will anticipate that in such cases Schrodinger's equation should change significantly in such a way as to remove interference between macroscopically different states. However, H has not yet proposed a more definite form FORSUCHA theory because HE wants to find some experimental evidence FORA BRAKD on OFQUA entum mechanics in the macro domain to guide his suggestions. 1-4. 4-step suggestions for regarding quantum theories. Describing an actual process. A rather different approach to an ontological theory of quantum mecha NICS. H has been suggested by STAP. 1-4. STAP bases HIS approach on 5-matrix theory, but there seems to be no inherent necessity for doing so. HIS aim is to develop a theory in which quantum mechanics will describe an actual 330 the UNDI11-ided UNIVERZ process TAKINGPLACEW without any necessary reference to human observers. In doing this HE is inspired by the ideas of Whitehead concerning NATURE as process. Whitehead 1-5 works in terms of the B as IC concept of an actual ACAS SION, or as STAPP might call IT, an ACTUAL event. In POT RT Kula R, THAT. WHH's act UAL is represented, not by an infinitely thin space-like surface. Advanc ing through the space-time continuum, but rather by a sequence of actual processes, EACH of which refers to a bounded space-time region. In such a process a given event, n, is represented by a restriction on the set of classical fields allowed in the bounded space-time region Rn. The basic concept is therefore neither BE coming in 3-dimensional space nor BEING in the 4-dimensional world, but RATHER it is becoming in the 4-dimensional world. We HAVE referred to regions of space-time Rn, but ultimately STAP wants to derive even these from the QUANTUM theory. He suggests this may be achieved in a manner mentioned in the previous chapter, section 1.3.6. He has shown 1.6 THAT the soft photons emitted by matter HAVE well defined CL as sickle pot RTS described by coherent states. As we HAVE already said in a previous chapter, ch chapter 8, THIS shows that the quantum THE ori may contain in a classical domain WITHINIT. Such a classical domain is what makes it possible to define the regions Rn in a physical way. It remains to define WHAT is to be meant by an event WITHIN the process. ASUMED by Step 1-4. HE considers process to consist of a well-ordered sequence of actual events. Just prior to event n, there are several possible ITIES of what MAYBE act UALISED. Let these possibilities be labeled by the SETN. Only one of these events WILLBE come actualised. Let IT be called an. For EACHN, there is a correspond ing region Rn. Moreover, for each possible event n, THE is a projection operator Pn, n, which restricts the classical field inside the region Rn to some subset of the set of all conceivable classical fields in Rn. Let S, n, be the S matrix subject to the co-NDITI on that classical fields. Be limited to those allowed by the product of projection operators. Let DIN be the initial density matrix and let D, En, be the density matrix. Transformed in the process of development described by the quantum the ori. This I'll give D, N, equals S, En, D, Ns plus, En. Then the probability for the event N is assumed to be E. TRD, En. 1, TR. D, E. It is CLEARTHAT. STAP's basic idea also defines everything within the framework of HILBERT space. A basic new assumed ion INHIS approach is extension of ontological theories 33-1. THAT certain KINDS of actual events, EN, correspond to specifiable projection. Operators P, En, and THAT statistical of a guess of any P a particular KIND of SE. Sequence of such events will be determined in the way described above by averaging these operators with D, N, the initial density matrix of the uni. Very. The assumption that events correspond to projection operators, even though these are not measure ED, is evidently something new, not contained in the current quantum theory. In contrast, in our interpretation we as some E, as we have already pointed out earlier, a particle position E with a probability density 1 1 2. As with the GRW approach, THE decision as to WH each of these THE oris has a smaller number of hypotheses depends on WH either or not. We give a very high priority to TA King H Hilbert space as the basic concept. One of the principal difficulties with STAPP's proposal is that the concept of an event has not been very thoroughly developed. First of all, STAPP has not provided a general criterion for the kinds of projection operators THAT could represent events, especially of how fine-grained is THE analysis THAT. He will allow at this event leave L. We shall discuss this question further in another context in the next section. Next, it seems THAT the classical PARTS of quantum mechanics SH old BE. Described in terms of THE movement OF fermionic particles as well as bosons. The classical context should also include large-scale systems and PERHAPS. Even large molecules as well as a THE ori of soft gravitons which would be needed to establish the notion of metric as contributing to events. It is conceivable, as Stap H himself hopes, THAT further new IDEAS might meet at least some of THSA requirements. Asterisk indeed in the next SECT on we shall discuss certain proposals of Gelman and H. Aertel which do start along THSA lines and go some way to developing a theory so as to deal with questions of this kind. 14.5 The cosmological approach of Gell-Mann and H. A. Rittel. Gell-Mann and H. A. Rittel too have independently suggested a theory along lines similar to that discussed in the previous section, which aims to provide an interpretation that covers the whole cosmological context. These authors criticize traditional approaches in a way similar to THATIN, which we do. In addition, they especially emphasize the question of making an interpretation that is adequate for cosmology. In such a cosmological approach, they say that there can be no fundamental division into observer. TAP 17 made further suggestions along these lines, in which the event I ultimately defined in consciousness. 332 The undivided universe and observed BESIDES, THERE is no reason to assume ACL world as fundamental or outside the B as I see quantum theory. They regard Everett 18 as the FIRST1 who suggested how to generate the conventional interpretation so as to apply quantum mechanics to cosmology. HEDIDTHIS by S showing how an observer can be considered as part of THE system and how the observer's activities of measuring, recording and calculating probabilities could be described in quantum mechanics. Along lines THAT we HAVED discussed in the previous CHAPTER. However, in agreement with what we HAVE said there, THEY regard the Everett analysis as incomplete. Gell-Mann and HARTLE feel THAT it does not add EQUA telex PLA in THE existence of the classical world or the meaning of the B branching. THAT replaces measurement in assigning probabilities. It was, they say, a theory of MA New York worlds, but did not explain sufficiently how they were defined or how THEYAROSE. In ASHORTPAPERTHEY briefly sketched THEIR extension of the conventional formulation of quantum mechanics, which they claim meets these criticisms too. They regard IT''RILY as an attempt at extension, CLARI, fixation, and completion of the Everett interpretation. They admit THE research is far from complete, but they regard THEIRPAPER as a sketch of how ITMAYBEC so. We SHALL here give a summary of their general approach. 14.5. L histo-RIES. The theory of Gell-Mann and H. A. Rittel too has to be understood, from the very outset, as DEALING with nothing less than the entire HI story of the universe. From the beginning to the end. However, to get on with the exposition, they allow themselves in this paper to ignore the first few moments and to start at a point at WHHSPACE, time and ordinary resorts of field variabler. Definably in their usual way. The initial quantum state of this universe is described by some density matrix P. Mathematical elements describe ing more. Specific in formation are represented by operators 0, t. They argue that it is sufficient to focus O and projection operators p, t, representing properties THAT at the time t are either present or not. In this, their position is similar to that of STAP 14, DISCUS said in the previous IUS section, who also introduced projection operators, p, en, inasi Myler role. Like STAP, Gell-Mann and H. A. Rittel consider time and CES of such projection operators, averaged over the unitialden matrix of the universe. And like step p, they suggest a ns of using THSA sequences to define a classical domain within the structure of Hilbert space. The main difference is that they develop their views more extensively and systematically, and show in more detail how such objectives might be realized. Extension of ontological theories 333. STAP used projection operators corresponding to the quasi-classical coherent states of a field oscillator in order to represent possible sequences of WHAT he called ACTUAL events. GEL MANN use a DIFF errant kind of projection operator for essentially the same purpose. What THEY do is to consider any one of the fields THAT are supposed to be basic in physics, e.g. as with STAPP, the electromagnetic. Their essential step is to obta in a classically adequate description of these fields represented by generalist coordinate test chi, t, not by using coherent states, but rather, by simply coarse-grained the field variables defined, for example, at any point in SPACE and TIME. Such coarse grained only restricts their field values to a certain range, and says nothing about the further details within this range. To THIS and they introduce sets of projection operators P, T, to which are unity in a given range of field variables, 6, and 0 outside, where a denotes the range under consideration and k the p-article are set. These projection operators are expressed in terms of a square wave function of chi, t, which is 0 outside the range 6 and unity inside. We denote THIS by B, Qi. The corresponding matrix representation of the projection operator is then the WH whole set of projection operators is PT, T, P2K, T, P, T. If the total set of ranges, A, covers all possible values of the field variables, THEY. Call THIS set exhaustive. An exhaustive set evidently need not be a complete set of operators, indeed it may involve few of them. They then go on to define sets of alternative HI stories. These consist of TIME sequences of exhaustive sets of alternative ranges. Such sequences provide coarse-grained descriptions of a set of possible HIS stories with coarse graining of each actual event represented by 6 and WITH. THE whole set given BY. ASETOF alter native HI stories is then obtained BY allowing a 1 LLN to vary over all possible value S. The extreme C as EOF such a description is a compel ETELY fin E-grained HIS story which is specified by giving a complete set of operators at all times. This sort of high story is used in Feynman's treatment of quantum mechanics. In terms of a sum over histories, which begins by specifying the amplitude in terms of a particular basis of generalist coordinates. Gelman and 334 the undivided universe. Artel suggest FORTHISB as IS, the set of all fundamental field variables at all points of SPA CE. This amplitude is EXP, is chi, t, / h. WHERES is the action fund CTI on WH is determined by the H. A. Milton ENH. Or alternatively by the Lagrangian L. 145. December 2nd OHERing HISTORIES. It is essential THAT completely phi ne grained HI stories as defined in THE previous I. A section cannot consistently be assigned probabilities. The reason is THAT. To do THIS would be incompatible with fundamental quantum mechanical properties such as two-slit interference. It is the B as I see claim of gel MNN. And THAT by suitably defining coarse-grained histories they can OB. TA in a consistent attribution of probabilities. The condition on THAT2PR ejection operators can represent two distinct possibilities for actual events is not only THAT they commute, but THAT. THEIRPRODUCTP1. P2 equals 0. Thus we might require for alternate HI stories. P01. P0 equals 0. But if we start from THIS requirement TA can rigorously, we CAN never hope to achieve WHAT gel MANN and HARTL set out to do B. Cause THIS set of operators is much too restricted. Their essential starting point is to know THAT. All THAT is required is to satisfy THIS condition for the actual initial STATE of the universe. Since by defy NITI on the universe cannot be in a state other THAN its ACTUAL1, we are not required to satisfy THIS condition for ANY other state. A sufficient condition for the decoherence of two alternative HIS stories O and O, may then be obtained by integrating THE projection operators P01, P0 with the density matrix of the universe. This will yield what we may call THE decoherent CE functional D010. Duo D, PA1, PA, TRP, TN, P, TI, PP, TI, P, TN, N, IIN. 146. When the above is 0, THE2 sets OFHIS stories represented BYOANDO. WLTHN correspond to two possible alternatives. GELLMAN and HARTL argue however THAT even WHND010-F0, BUT is small, it ISSTIL possibly, consistently, to regard O, and O as alternate TIVE. History ES. BUT if we do THIS, then THE probability rules will only be approximate. I'm ately satisfied and the measure of the failure of the approximate ion will be indicated by THE size of THE off diagonal elements. For example, in an arbitrary, but convenient way, we could define this measure more precisely as TRID, DDL2. WHR DDISTHE diagonal part of D010A and DTHE matrices. EXTE enzyme of ONTOL logical theories 335. Should be thought of as on THE space of very fine-grained HI stories. A set of coarse-grained histories can then be said to decohere to a certain degree of approximation when the off-diagonal elements of DA are sufficiently small l, I, e. When TRID, DDL2 : 0. A further their assumption is THAT under the above conditions the diagonal elements of DA are approximately equal to THE probabilities P, P0, of the correspond INGHI stories, or for each PA in a set of approximate alternative HI stories. To sum up THEN, the smallness of the off-diagonal elements is assumed D to be the condition for a consistent assignment OF approximate probabilities, while the diagonal elements are assumed to give their approximate values. 14530NTHEMEANING of DACO HERENCE. Gel MANN and HARTL state that the IN general approximately decohere and HI stories are what we may discuss in giving a meaning to quantum Mechanics. As they further say, decoherence thus generalizes and replaces the notion of MEA. Surement. Decoherence is a more precise, more objective, more observer-independent idea. We may assign probabilities to various values of reasonable scale density fluctuations in the early undivideds, whether or not anything like a measurement was carried out on them, and certainly whether or not there was an observer to do it. Measurements will then have to be seen as special C as ES of the universal process in which there is a measurement citation such that certain objective and observer-independent events in a given HIST or are correlated to others in a different history, taking place in what we somewhat convention call a measuring apparatus. We shall return to this question later, but for the present we re-emphasize that measurements and observations play no fundamental role in the formulation of this theory. However, if this approach is to be carried out consistently, it is necessary to deal with a number of points that require clarification. To begin with, in principle, any set of projection operators might be thought of as suitable for defining decoherent sets of alternative HI stories. Indeed, if the subsets are exactly orthogonal, one can exhibit sets of HI stories that are exactly decoherent, which, among all these sets, are the ones that correspond to a sequence of actual events. It is important that we do not assume sets of 336 undivided univrs. Act UALEV ents THAT wow LD imply a contradiction WITH entum theory. In any domain in WH it is KN own to apply. But if we see AN actually find a set of decoherent operators P, T, that define reasonable HI stories, then it is clear that WITHI and the approximations THAT are being used, no STATIST. CAL results of THE theory will be contradicted by the assumption THAT the P, T, represent alternative possibilities of sequences of ACTUAL events. 4. Such a contradiction would arise only if there were sine phi cant interference. PR operti SB between these sequences, and these would imply coherence. This, however, is the question of whether we can show THE theory. ACTUALLY implies sets of decoherent HI stories of THE kind that we require. The decoherence foo and setional dep and ds, as has been seen, on the initial density M matrix of THEUNIVers, P, BUT in ADDITION. It depends on the Hamiltonian H. For we HAVE to follow the time evolution of the operator P, T, I and the Heisenberg representation BACK to the time of the origin of the univers. Using the formula P, T, equals E, IH, TP, O, EIHT, where P, T, is THE projection operator AT, the time T, and PO, is the COR. Respond ing operator at the time t0. In effect, the above procedure suggests a possible answer to the basic question that was raised in the MA New York World's interpretation, i.e. WHAT determines the preferred B as IS for the various branches that are to be realized in the process of proliferation of the many universes. The new idea here is THAT. It is the evolution of the universe from its initial conditions which should provide this determination, and that this would remove an important ambiguity in the many worlds approach. It is clear that we see a not in THE foreseeable future hope to carry out for the universe a calculation of all decoherent sets of alternative HI stories. WHAT gel MANN and HARTL do IS to investigate specific illustrative exam. please, of decoherence in more restrictive circumstances, referring to the works of Joos and Zay 19, Zurek 20 and Caldera and Leggett 21, as well as Feynman and Vernon 22. These authors investigate WHAT is called dy. Anamic decoherence, i.e. that WHHIS brought about through the dynamic evolution of the quantum state. All of them deal with simplified systems, such as a single harmonic oscillator with coordinates x coupled to a Large set of oscillators constituting an environment. The general result is THAT2. Hi stories corresponding to different trajectories, x, t, and x, t, will decohere. In very short TIMES for typical situations such as having the environmental oscillators in an initial state of thermal equilibrium. Gel MANN and HARTL that these illustrative examples made it very plausible THAT decoherence will be widespread in the universe for the Fermi LIAR. See Lassical variables. For example, this while dxpla in Y we do not see the extension of ontological theories 337. Track of APR ejectile spreading out IN to quantum superpositions IN its or BIT. 14.54 The quasi-classical world. Ordinarily when we use coarse graining, we are introducing something dependent on a context related either to our sensory perceptions or to our instruments, comuni cations or records, all of which are characterized by some kind of ignorance resulting in some incomplete specification of the SYSTEM. Yet as Gel MANN and HARTL say, we have the impression that the universe exhibits a finer grained, presumably objective and observer independent set of decohering Hi stories. These should make possible the definition of WHAT they call a quasi-classical world governed approximately by classical laws. This may be compared with our manifest world discussed in ch chapter 8. GELLMANN and HARTL feel that this quasi-classical world should follow from the INITELCO and DIT ions of the universe and the Hamiltonian, with the aid of the projection operators that we have been discussing in the previous sections. To show THIS, they would like to find a way to make the question of the existence of a quasi-classical domain into a calculable question in quantum cosmology. For this they need criteria to measure how close a set of Hi stories comes to constituting a quasi-classical domain. As they state in their article, they have not solved this problem to their satisfaction, but THEYD is CUSS some IDES THAT hope may contribute towards its solution. To explain WHAT Gel MANN and HARTL have done in THIS regard, we note THAT their IDEA of a quasi-classical Hi story is closely related to that of a broad wave packet in ordinary quantum mechanics. As is well known, the center of such a packet follows the LAWS of classical physics, while the packet spreads out very slowly, so THAT it resembles somewhat a classical particle moving through space, at least for some time. However, Gel MANN and HARTL describe TH's process differently by means of a set of projection operators P, T1, P, T2. For the simple case of a free particle, for example, it is easy to show THAT product P, Ti, P, T2, is large only when P, T2 represents a coarse-grained region whose center is displaced relative to THAT, corresponding to P, Ti, by P, T2. T1/m, W here P/m is The mean velocity. of the wave packet as determined by the wave function of the system and ultimately by the density matrix of the universe. It is clear then THAT products LIKEP, T1, P, T2 will be large only for histories in which the centers of THE regions concerned are low CATED more or less along the C loss SICAL trajectories implied by the initial wave packet. What HSBEN gained by this procedure is that we HAVE the POSSIBILI of obtaining a definite sequence of actual events, defined within the range LL, in spite of the spread of the wave packets. However, what we in fact get is a 338 the undivided universe whole set OFPOSIBLE sequences OFACTUAL events INWHICHTHE probabilitywill be large only for THOSE sequences THATRCLOs to the classical TRA-JECT ORIs. It is along THESE lines THAT gel MANN and HARDLWILD like to show. THAT1CAN construction UCTAWHOLE quasi-classical world correspond DING to such HI stories. But there are certain problems THAT must be faced in order to do THIS. FIRST of all, as we HAVE already remarked, ITIS necessary not to make the HI story so fine GRAIN add THAT the assumption of their existence would sig. NIFICANTLY disagree WITH the PREDICtions of the CUR rent QUA entum mechanics. IN the domain THAT the later H as found to be VALID. This CANBE achieved by going to extremely coarse-grained projection operators, because, as is well known WN, such CORs graining will in general make off diagonal elements of M matrices such as duosm all. On the other HAND, we must not HAVEA. Gray NING so CORs THATIT does not defy any the CL-esical domain to any sig. NIFICANT ext. That is to say it must rema in fine-grained enough to allow for a CL-a-CCAL description THAT would not be lost in total ambiguity. So we HAVE to assume THAT the degree of CORs GRAINING is somehow objectively determinate at least WITHIN an order of magnitude as lying somewhere between the two extremes INDICATED above. This may NS, of course THAT it is. Being assumed THAT quantum mechanics does break down when we reach this quasi-class ICALCORs grained left EL. But we further assume THAT the point of breakdown is such THAT qua NTUM CHANICS holds for all PRACTICAL. PURPOSES. Gel MANN and HARDL are not SATIs phi WITHSM INGTHAT there is a simple UNIVERSAL coarse graining THAT is fixed, the same for all circumstances. We CANSEE reason FORTHIS, FOR example, BYCO considering THAT systems. At HIGH temperature can be given a much more fine-grained descript ion. THAN is possible for systems at low temperatures without introduce ing any practically observable deviations from the quantum laws. Gel MANN and HARDL HAVE therefore tried to find a universal fu NCTION to express their criterion INSUCHA way THATIT could adapt to all CHANGINGCIRCUMST THAT co-ULD arise on VARIUS bra NCHES of the possible HIST ORIs of the universe. To this end they considered various information theoretic measures of WHAT. They call the C-LASIC ITY of a given DOMA IN, WHICH the HOPE will ultimately yield the precise definition of a quasi-classical world as a WHOLE. H.O. Weaver, as we HAVE already pointed out, they do not feel THAT, as yet. They have solved this problem to their satisfaction. But even if THEY could solve it, IT would still require a basic new assumption and their approach going beyond current quantum theory. For no matter how subtle and variable their criterion for class ICITY may turn out to be, IT will still HAVE to HAVE. Some kind of scale factor THAT determines the ACTUAL degree of objective coarse graining of the class ICAL world under any given set of circumstances. This world corresponds in some rough way to a similar assumption that H has been made by GRW. For they too have to assume that quantum mechanics breaks down at some level, but in a way that is important for all practical purposes. This sort of requirement is also characteristic of all forms of the many worlds interpretation, as Deutsch one has indeed suggested. For inism ing a prferd b as is in which the universe actually splits, or in which the awareness of the observer similarly splits, they are inevitably implying a break down of the quantum theory, though this may be unimportant for all practical purposes. 1.4-5. 5 Mies Urementandobservation. As WEHAVEP pointed out earlier, GEL MANN and HARDL regard measurement as a special case of a general process in the universe. When a correlation exists between the ranges of values of two operators of a quasi-classical world, there is what they call a measurement situation. If the correlation has probability near unity, th and the range of values of the one can be deduced from that of the other. All of this is, of course, objective and independent of the observer. The above however discusses only measurements in the quasi-classical world. What about measurements of essentially quantum mechanical operators such as spin? Of course the spin states will not cohere by themselves. But in a measurement situation the different spin states are correlated with different classical histories. And these latter, of course, do decohere. The decoherence of the overall state will thus bring about the decoherence of the spin states that have been measured. This is very similar to WHAT happens in our own interpretation, in which the non-overlap of the apparatus wave functions guarantees that there will be no interference between the spin states. In both C as ES the usual rules for probability will be recovered. In the theory of Gell-Mann and Hartle, the observer is discussed in much the same way as was done in the Everett interpretation, except that all is now treated in a cosmological context. The observer's memory, awareness, etc. should, in principle, be included in the density matrix of the universe. And it should also have some representation in terms of operators in the quasi-classical world. However, it is not enough to consider what happens at a given moment or period of history. It is necessary to consider how a set of observers might have evolved from the initial state of the universe. To discuss this question, Gell-Mann and Hartle refer to an observer as an information gathering and utilizing system, IGUS. They aim THATSUCH. A system can principle be treated in terms of quantum mechanics as these authors have formulated it. That is to say, in some form of approximate imation. No matter how crude an IGUS is said to employ this form of quantum mechanics in a self-referential way. The possibility of this is based on the assumption that memory contain T and THAT to WHICHIT ref RS, are correlated by the laws of quantum theory as applied in this cosmological context. It is further assumed by the AUTH ors. THAT-THSA laws provide for the evolut ion of IGUSS in such a way THAT. These latter can make predictions and draw further inferences about the probabilities of coarse-grained HI stories. It is argued THAT this capacity was maintained and developed because IT was favorable to their survival. The reason why JGUSS focus on decohering variables is THAT, at least. Within this theory, these are the ONL Y variables for which predictions can be made. In addition, THEY focus on the histories of a quasi-classical world. Because these present enough regularity over time to permit prediction by relatively rudimentary algorithms THAT are easily evolved. GELLMANN and HARDL thus effectively EXTENDDARUINISM and propose a possible basis for IT in the LAWS of QUANTM-CHANICS. If there are many significantly different quasi-classical worlds, as seems to be suggested in the many UNI versus POINT of view, one should better say THAT the IGUS evolves to exploit a particular quasi-classical world or a set OFSUCH world S. This implies, of course, THAT the IGUS include INGTHE human. BEING, occupies no special PLACE and plays no preferred role in THE laws of physics. This approach is in some sense closely related to certain forms of the anthropicprinc IPL 23. BRINGING in THE evolution OFTHEIGUS plays a key part in how THE ori of gel MN and HARDL deals with measurement situations. For example, they consider the MUT-ULI exclusive character of simultaneous POSIT ion and moment TUM measurements. What this means in their point of view is THAT the H is T ori IN which an observer, as part of the UNIVers, sets UPA measurement correlation to the moment TUM, P, and 1 in WHH he does. This for the position, Q, are represented by two sets of decohering operators. WHICHR, however, mu TUALLY exclusive ALTERNatives. The decoherence is established by interacting with a thermal bath or with the 3 degrees J, background. RADIAT ion or with something similar. Since these are mutually exclusive alternative possibilities for the universe as a whole, only one of them can be realized at a time in the development of the universe. Or more precisely, only one of them can arise on a particular branch of the evolut ion of THE universe as a whole. They say however THAT choice OF branch may ultimately be traceable to a quantum fluctuation THAT sets in motion a chain of events leading to one measurement situate ion or the other. Some HAVE even suggested THAT the human subjective impression of free will may be traceable to statistical or quantum fluctuations. To present these ideas more vividly, we may say THAT, according to this theory, THE universe evolved first to give RISE to matter, then to life, and ultimately to human beings along with their societies, sciences, measuring instruments etc. Event UALLY in this evolution there appeared a physicist who set up a momentum measuring device and established a correlation between the subsequent HI story of THIS process and the momentum of a quantum system at THE time ET. It seems inescapable that the pH is assists. Impression THAT he freely choose to set this measuring instrument upward. HAVEHAD to be illusory at least in terms of this theory. For in this theory, no THINGWH atsoever CANHA pen unless it is PART of the evolution of a suitable branch of the history of the universe as a whole. Therefore we see no reason why the authors HAVE attributed this kind of conclusion to some, and HAVE not STA THIRD-WHAT they themselves believe in this regard. SIMELAR considerations may be applied to the EPR, TEP of experiment. For example, at some PART of the evolution of the universe, there may arise a molecule of spin 0, constituted of two atoms of spin H/2, along with a physicist who sets up an instrument designed to disintegrate the molecule, and to measure suitable components of He spins of the two atoms. The fact, for example, THATHEH as apparently CHOS and to measure the Z component of one of THM was somehow implicit from the very early phases of the UNIVERSE. Once THIS choice began to unfold from THE primeval explosion, then THR could never be any question of what would HA pen if the universe HAD developed in such a way as to bring about a measurement of some other component of THE spin. ReCall however THAT the paradoxical features of the EPR experiment arose BECAUS one assumed THAT before the measurement took place. It was always possible for the observer to choose an arbitrary component of THE spin, CHA-PTER2. If this choice has no meaning THE and all the conclusions commonly drawn from the EPR experiment will not follow. For example, the same quantum fluctuation from which emerged the physicist's choice to measure the Z component of the spin of one of the atoms, will also HAVE given rise to the choice to measure a certain component of the spin of the second p-article along with the correlation of the results of the two measurements. Or as Bell has put it, there is a complete rapport established at the very beginning of the universe between the net results and the total measurement situation including the physicists who set the experiment up, and CARRY at OUT. Some people HAVECALL at this sort of situation the denial of THE counterfactual 24. But what the theory of Gell-Mann and HARTL adds is an explanation showing why THIS denial follows necessarily from their model of the universe. There are certain important similarities between RAPPROCH and THAT of Gell-Mann and HARTL, as well as, of course, important differences. One of THE key similarities is THAT both APPROCHs agree THAT the wave foo NCT ion, or the density matrix, is not a complete description of reality. Thus we bring. In WHAT we HAVECALLED variables, which are either precisely defined particle trajectories or precisely defined motions of the field variables. Gell-Mann and HARTL bring in their course GRAIN ed projection operators OUT of which they construct sets of alternative HI stories. Let us recall THAT most of THE unsatisfactory features of THE conventional interpretation, WHICH requires the complete linearity of the wave equation, ARISE from the assumption THAT. The wave function, or the density matrix, provides a complete discrete PT ion of reality. It is THIS assumption THAT, in the context of linearity, requires US to postulate the collapse of the wave function with all its at NDANT. Paradoxical features, THATHAVEBEND discussed throughout THE book. of course, if the wave equation is nonlinear, as in THE approach of GRW. Paradox is avoided and the C-elapse is explained in another way. A second key similarity in the two approaches is THAT, in both each of them. The classical world is explained as part of the overall quantum world rather. THAN simply assumed. Without such a possibility, we have to suppose the universe is split into two qualitatively distinct parts even if we also tacitly assume that somehow the properties of the classical world are determined in principle from the quantumlaws to the classical level. As flowing out of the quantum laws is clearly necessary if we are to consider the universe as a single whole. For such a theory requires THAT properties of matter at the classical level SHALLBE implicit in the basic general LAWS. WHICHRACTUALLY quantum mechanical. In particular, such an approach is evidently needed if we are to include the process of measurement itself, WITHI and the THE ORI in a coherent way. The main difference in THE2 points of view is THAT we bring in THE concept of actual beables, E.G. Particles A and D fields, while gel MANNA and D. Hartle introduced THEIR coarse-grained projection operators. A key point here is that although their projection operators are NEW concepts relative to the quantum theory in its current generally accepted form, they are never THLess, as we have indicated earlier, still expressible as operators defined on AHILBERT SPAC E. On the other HAND, are particle and field variables are not expressed as such operators in Hilbert space. Rather they are new concepts going outside THIS framework of Hilbert space altogether. In our approach once we have assumed particle and field beables, no fur. Their fundamental assumptions are needed, nor as we have seen, are there serious problems involving the basic principles please. Indeed even the probability assumption may be derived, as in chapter 9, either from The chaotic character of trajectories in the many-body system or from a stochastic process. The quasi-classical world, which in chapter 8 we have called the manifest world, comes out simply and naturally as that domain in which the quantum potential can be neglected. There is no sharp break between the quantum world and The classical world, but only a continual increase in the elasticity of the behavior, as we approach the domains in which the quantum potential becomes less and less important. ONTHE other HAND in the approach of Gell MNN and Hartle, the simple assumption THAT sequences of projection operators correspond to actual HI stories is not enough. In addition, as we have seen, one has to assume an objective limit to the degree of fine-grainedness of these operators. And besides, THR is still the unresolved problem for finding a functional form. For THIS limit THAT is suitable for all circumstances. A further conceptual unclarity of their approach is that the reality status of the wave function or the density matrix is, at best, highly ambiguous. It would seem from WHAT the have written that everything that is actual and real is contained in the quasi-classical world. This seems strange because all the basic physical properties do in fact come out of the wave functions or the density matrix. Should not this therefore be regarded as a key factor of reality, as indeed it is in our interpretation? THIS ambiguity in the reality status of the wave function, or density mat RIX, is in a way a residue of the separation of the quantum world of the wave function and the classical world of the measuring instrument THAT. Was originally assumed by von Neumann, SEE Chapter 2. The basic role of the observing instrument is now replaced by a similar role of the coarse grained projection operators. Of course, the ambiguity and the cut between the measuring instrument and what is observed has been removed because the latter H has been given a universal significance, i.e. the universe contains a set of coarse-grained projection operators that in effect are constantly carrying out measurements in a unique and objective way. Nevertheless, there still remains the fundamental split between the two kinds of reality, which many while feel to be undesirable. A further key point which we emphasize once again here, is THATR approach has the advantage of being much more capable of being grasped intuitively and imaginatively than is that of GEL MANN and HARTL. As we pointed out in Chapter 1.3, Section 1.3. 2, the VIUSHR'd by most of the protagonists of the many worlds point of view is TH at THEY make no further serious assumptions. This view seems to be as ed on the extremely high priority THAT they give to retaining Hilbert space as THE basic set of terms for the expression of LL concepts. As a result, all the other assumptions that we have detailed in the previous chapter and in this section of the present chapter, do not seem to be very important. We acknowledge THE possible value OFB as INGATHE or E solely ONHILBERT space concepts ANDL. Though we shall indeed explore SUCHATHE or E in the next chapter, we still do not feel THATHILBERT SPACE has such advantages, e.g. BEAUT if UL symmetries, as to imply THE necessity of giving this con CEPT so overriding a value. It is in our view very important to keep the options open to allow THEEXPLANation of all approaches, as long as these have certain specific advantages such as those THATHAVEBEEN outlined here in the exposition of our interpretation. In addition its old be kept in mind THAT such new approaches allow new forms of idea to be explored, some of which we shall discuss in the next section, as well as in the next chapter. Finally, we would like to see attention to a more subtle difference between our approach and THAT of GEL MANN and HARTL. In our interpretation, it is always, in principle, possible THAT-THR-MAYBE modification coming from outside the total framework THAT we consider. For example, in THEEPR experiment we SUPPO said THE observe ER could ARBITRarily choose to reorientate the APARATUS while the atoms were separate TING. Let us re-see ALL. THAT it is THIS assumption which originally made the EPR experiment seem paradoxical and which ultimately led to the conclusion THAT-THR-HAD to be a non-local connection between the ATOMS I and the C as E. The modification MIGHTHAVE been due to WHAT has been CALLED the FREEWILL of THE experiment ER. BUT more generally, the central question here is not THAT of free will, but rather THAT of whether anything is possible THATH as asserta ININDE. Pendants of THEQUANTUMMECH anical framework which we are discussing. The assumption of free will would imply such a C as E of INDEPE endance. But of co-URSE, THR could be all kinds of new levels of law, not only in physics, but also, perhaps WHEREVER life, mind, society etc. are involved. In other words, as we have are ought out in section 1.4. 2. There is no valid reason for assuming THAT all exist NCECA be reduced to the LAWS of the qua NTUM. THE ori. O and the other HAND, in the I interpretation of gel MANN and HA is, as we have seen, impossible for anything to happen THAT could not in principle be covered by some kind of extension of this theory be as ed on the concept of Hilbert space plus the notion of the evolution of the universe THAT proposed. From this it follows that everything that could happen would, in principle, be implicit from the earliest phases of the universe. It is this Phyto rethat leads to the conclusion that nothing independent of the whole scheme can come in to alter the course of cosmic evolution, which latter leads even to the determination of the orientation of a piece of apparatus as something THAT was implicit in the quantum fluctuations of the EARLY universe. As we have seen, it is this feature THAT removes non-locality, but the cost is a closure of our thinking, which, in our VIU, has no ground in fact, and which may limit the development of our ideas in a counterproductive way. 1.4. 6. Extension of our approach beyond the domain of current quantum theory. Thus far we have discussed a number of suggestions for ontological interpretations THAT go beyond the current quantum theory, at least conceptually. But nevertheless recover the later as summit THAT will be valid for all practical purposes. In THIS section we shall discuss some suggestions of our own. In WHICH we show how our proposals can also be extended beyond the current quantum theory. However, these extensions are not just purely conceptual, but we show how in principle they can lead in new domains to qualitatively new theories and correspondingly new experimental implications. The chief difficulty in carrying out THIS sort of extension of our approach is THAT is such a wealth of possibilities and such a dearth of experimental clues THAT might narrow them down. For example, in our basic equations for a trajectory of a particle dp, dt, p, v, v plus q, vs, it will be possible to bring in arbitrary forces, F, to obtain dp equals v, v, plus q, plus f, dt, as well as arbitrary additions, A, to The guidance relations to yield. Any such changes could in principle fundamentally alter the consequences of the The ori. Even though THEY might be chosen so THAT under conditions thus far investigated, the changes would be negligible for all practical purposes. The possibility would still be open THAT under new conditions. These changes could no longer be neglected. Her changes of the sort that might be considered would be to make the Schrödinger wave equation nonlinear and to introduce terms that will relate The Schrödinger wave function to The particle positio ns. Again in such a way that significantly new results would follow only in new domains not yet investigated. 346. The undivided universe. One way to make Schrödinger's equation dependent on The particle positions, so THAT would be a two-way relationship between wave and particle, can be seen by considering equation 141. In THIS equation, we can regard Rn as the actual position of the N1H particle. From the same arguments as apply to THEGRW appro CH, it would follow THAT the overall wave function would tend to co-LLAPSE towards the ACTUAL particle positions. So THAT, in a large-scale system, the empty wave PATs of our inter-PRETA. Shenhua LD tend to DISA pair. With OUT some kind of experimental clue, we are at a loss in TH's sort of situation as to how to proceed. How EVER, THRHAVE been a number of cases. In the history of physics in WHICH theoretical questions provided useful clues. Long before experimental physics was able to do so. A case in point is just the atomic theory of Democritus, which we discussed earlier in Chapter 2. Section 2. 8, as well as SECTI on 1.4. 2 of this chapter. The idea of Democritus W as inspired by a consideration of APHIL Asaf. IC al paradox INTHE very notion of movement, which was shown by Zeno and other members of the Eliot-IC school. They demonstrated logical inconsistencies, not only in the idea of movement itself, but also in the idea of an empty space in which movement could take place. From their demon Stratians THEY concluded THAT only being is and that non-being is not, from WHICH it followed that the concepts of becoming along WITH those of move meant an empty space had no meaning. Through contemplation of THIS paradox, Democritus was led to a resolution. He proposed THAT being was DIS continuous in THE form of distinct. And separated atoms, EACH of WHICH was an indivisible and eternal being. Democritus thus retained, in a certain restricted way, the Eleatic concept of being. But he postulated that there was an empty space in which THSA atomic beings could move in such a way that the collective aspect of their motion then explained the LARGE scale properties of apparently continuous matter with its continuous Chang es. On the other hand, if we suppose THAT matter was truly continuous rather than only apparently so, THEN, as the Eleatics showed, there was no way in which its movement and transformation could have meaning. One could, in principle, have seen at THAT time that the experimental detection of atoms depended basically on two related ways in WHH. The LAWS of continuous matter could fail, phi RSTLY because atoms had a definite size, and secondly because they had some non-zero free path between their successive collisions. These were, in FACT, actually the ways in WHH. The atomic theory was eventually verified experimentally. OUR proposed ontological explanation of the quantum theory H as we have seen, also led to a certain paradox. For IT implies non-locality. And THISWOULD seem to contradict relativity, which is regarded as a THE ori. EXTEN Zion of ontological theories 347. That is equally as fundamental as quantum theory. But, as we have seen in Chapter 12, Section 12.7, it is possible to propose a deeper theory of the individual quantum process which is not relativistically invariant and which nevertheless leads to Lorentz invariant consequences for all statistical results, as well as for the LARGE scale manifest war LD. In this theory there is a PRF-aired coordinate frame in which the instantaneous transmission of impulses is in principle possible, so that there is no contradiction with non-locality for individual quantum processes. In other words, we say that on the earlying THE level in which relativity is valid there is a subrelativistic level in WHICH it is not valid even though relativity is recovered in a suitable statistical approximation as well as in the LARGE scale manifest world. In our discussion of this idea we have already suggested one way in which the theory might imply new experimental consequences. Thus, although there is no inherent limitation to the speed of transmission of impulses in this subrelativistic level, it is quite possible that quantum non-local connect ions might be propagated, not at infinite speeds, but at speeds very much greater than that of light. In this case, as explained in chapter 1-2, we could expect observable deviate ions from the predictions of The current quantum theory, e.g. by means of a kind of extension of the aspect type experiment. It would seem then that already in this case a subrelativistic level would simultaneously be one that goes beyond the current quantum theory. But the notion of a general subquantum mechanical level would have TOGOBE beyond the current quantum theory in a much more thoroughgoing way. To explore such a possibility it is useful to consider once again the stochastic form of our ontological approach. We recall that in this approach a particle follows a trajectory which is random, but which is modified by a suitable osmotic velocity along with the action of the quantum potential. The level of Brownian motion of atoms, for example, similar random trajectories, are regarded as approximations to actual trajectories in which this randomness does not prevail at indefinitely short distances. Rather there exists a characteristic length, the mean free path, below which simple causal laws begin to have a dominant effect. This free path reveals itself in many experiments, e.g. those of diffusion, conductivity of heat, etc. Similarly we may propose that in our theory there is a minimum free path below which the trajectory ceases to be random, as the atomic free path is the first sign of a subcontinuous domain in which the laws of continuous matter will break down. SOTHE free path in OUR trajectories would be the phi RST sign of a subquantum domain in which the laws of quantum theory would break down. It is implied of course that this would begin to occur for wavelengths of the order of the FRE path. The next sign of a breakdown of the quantum THE would be THE 348 the undivided univeru. Discovery of some yet smaller dimension whose role might be analogous to the dimensions of an atom in the atomic explanation of continuous matter. We do not as yet know what this dimension is, but it seems reasonable to propose that it could be of the order of the Planck length, where, in any case, we can expect that our current ideas of space-time and quantum theory might well break down. The free path would then be some multiple of this length. At present further progress only seems to be possible through the use of the imagination to suggest new concepts. THAT might permit a more precise formulation of these ideas. In this regard the situation is not very different from what it is in string theory, which is at present guided by speculative use of mathematical concepts that also have little or no contact with experimenti. As we have pointed out in section 1-8 of chapter 1-2, it took over 2,000 years before the atomic theory of Democritus could achieve a more precise formulation. But we may reasonably hope that with the more rapid progress of science in the present era, it will take considerably less time. Chapter 1-5. Quantum theory and the implicate order. 1-5. 1 Introduction. Throughout this book we have far been concerned with showing that a consistent ontological interpretation of the quantum theory as it now stands is possible. In the previous chapter, however, where A is the question of going beyond the current quantum theory, and in the last section we sketched certain more definite purposes for doing THIS. These purposes, however, still involve introducing the concept of a particle, in addition to that of the wave function. As we pointed out there, THIS implies that we go outside the notion of expressing all basic concepts in terms of Hilbert space. In the present chapter we shall begin by exploring a new way of understanding the quantum theory and going beyond it, which does not go out of Hilbert space. Nevertheless, it does not set aside the work that we have done thus far, but rather it also includes the description of the particle trajectory within the framework of Hilbert space. The basic idea is to introduce a new concept of order, which we call the implicate order or the unfolded order. 1. This is to be contrasted with our current concepts of order, which are based on the ideas of Descartes, who introduced coordinate systems precisely for the purpose of describing and representing order in physical process. The Cartesian grid, ended to curvilinear coordinates, which describes what is essentially a local order, has been the one constant feature of physics in all the fundamental changes THAVE happened over the past few centuries in the quantum domain. However, this order shows its inadequacy, because physical properties cannot be attributed unambiguously to well-defined structures and processes in space-time while remaining within Hilbert space. THUS, for example, THE uncertainty principle implies that it is not in general possible to give a definite space-time order to the motion of a particle in its trajectory. The fact that we nevertheless still use Cartesian coordinates, then, leads to 350. And certain difficulty in thinking clearly about the subject. As we pointed out in the previous chapter, this is generally avoided by sticking to the mathematical equations and by saying that, in theoretical physics, these latter are basically what we are talking about, so that unclarity in physical concepts need not disturb us. WHAT we are prop 011ing here is THAT. This D is spot RIT between physical concepts, e.g. particle, wave, POSIT ion, momentum, and the IMP cations of the ma Ti cal equa Ti ions arises because the physical concepts are inseparably involve EED with the Cartesian notion of order, and this violate and the essential content of quantum mechanics. What we need is a notion of order for all our concepts, both physical and mathematical, which coheres with this content. In this chapter we shall explore how such coherence may be realized with the aid of the notion of the implicate order, which will be developed here. In some ways this step is similar to that taken in the development of relativity, which likewise introduce new notions of order, e.g. with regard to simultaneity and also with regard to curvilinear coordinates. In relative it, however, strict continuity and locality are still maintained. But in the implicate order even these will have to be recovered as approximations and limiting cases. 1.5. 2. Relativity and quantum theory as indicators of a new order for physics. It is generally agreed that neither special relativity nor general relativity have been united with quantum theory in a fully consistent way. To be sure, we do have relativistic quantum field theory, and with the aid of renormalization techniques, this gives a wide range of correct predictions. Nevertheless, the fact remains that strictly speaking the present theory implies various kinds of infinities, and that the removal of these infinities by René normalization algorithms is, logically considered, an arbitrary modification of the original B as IC principles. No new principles have been suggested up to the present that would lead to finite results. It is also very clear that General Rel ATI6 TI introduces still further problems of PRINCIPLE-WHICHHHAVE not yet been resolved. An important light can be thrown on these difficulties by noting that the basic orders implied in relativity theory and in quantum theory are qualitatively in complete contradiction. Thus relativity requires strict continuity, strict causality, and strict locality in the order of the movement of particles and fields. And as we have seen throughout this book, in essence, quantum mechanics implies the opposite e. This kind of contradiction in basic concepts is reminiscent of the paradoxes, e.g. Zeno's paradox, through which Democritus was led to the concept of the atom as explained in the previous chapter. Would it not be possible that the present contradiction between the basic concepts of relativity and quantum theory could similarly lead to a qualitatively new idea that would open the way to resolve all these difficulties? As a clue to what this new idea might be, we could begin by asking not what are the key differences between these concepts, but rather what they have in common. What they have in common is actually a quality of unbroken wholens. To see what this means, let us first consider relativity. As is well known, the concept of a permanently existent particle is not consistent with this theory, but rather it is the point event in spacetime that is the basic concept. In principle, all structures have to be understood as forms in a generalist field which is a function of all the spacetime points. In this sort of theory, a particle has to be treated either as a singularity in the field, or as a stable pulse of finite extent. The field from each center decreases with the distance, but it never goes to zero. Therefore ultimately the fields of all the particles will merge to form a single structure that is an unbroken whole. The notion of unbroken wholeness is, however, still of limited applicability in the theory of relativity, because the basic concept is that of a point event which is distinct and separate from all other point events. In quantum theory, however, there is a much more thoroughgoing kind of unbroken wholeness. Thus even in the conventional interpretations, one talks of indivisible quantum processes that link different systems in an unanalyzable way. In principle these links should extend to the whole universe, but for practical purposes their effects can be neglected on the large scale, so that in some suitable classical approximation we can use a simplified picture of the world as made up of separate parts in interaction. But in our interpretation, there is also the fact that because the quantum potential represents active information, there is a non-local connection which can, in principle, make even distant objects into a single system which has an objective quality of unbroken wholeness. In such a single system, the idea of separate point events clearly has no place. Yet as we have pointed out, there is a certain residue of this notion still implicitly present in the fact that ultimately all fields are defined in terms of space-time points. These points are put in order by means of a Cartesian grid, extended where necessary to curvilinear coordinates, and it is this order that makes it possible to define key concepts such as local interaction between fields and different IAL operators. WHICH play an essential role in expressing the movements of these fields. To sum up then, relativity and quantum theory share the notion of unbroken wholeness, even though they achieve this in very different ways. As we have already explained in the previous section, we need a new notion of order that will encompass these different kinds of unbroken wholeness, which could open the way for new physical content that includes relativity and quantum theory but has the possibility of going beyond both. 15.3 Qualitative Introduction to the Implicate Order. Our notions of order in physics have generally been tacit rather than explicit and have been manifested in particular forms which have developed gradually over the centuries in a somewhat fortuitous way. These latter have, in turn, come out of intuitive forms and common experience. For example, there is the order of numbers, which is in correspondence to that of points on a line, the order of successive positions in the motion of objects, various kinds of intensive orders such as pressure, temperature, color, etc. Then there are more subtle orders such as the order of language, the order of logic, the order in music, the order of sensations and thought, etc. Indeed, the notion of order as a whole is not only vast, but it is also probably incapable of complete definition, if only because some kind of order is presupposed in everything we do, including, for example, the very act of defining order. How then can we proceed? The suggestion is that we can proceed as in fact has always been done, by beginning with our common intuitive notions and general experience of order and by letting these develop so as to extend into new domains and fields of application. Our suggested next step is to explore how an order appropriate to wholeness can be found in our intuition and general experience. We begin by noting that the ordinary Cartesian order applying to separate points finds one of its strongest supports in the Fu engine of a lens. What a lens does is to produce an approximate correspondence of points on an object to points on its image. The perception of this correspondence strongly brings our attention to the separate points. But as is well known, there is a new instrument used for making images called the hologram, which does not do this. Rather, each region of the hologram makes P06 Cybele an image of the whole object. When we put all these regions together, we still obtain an image of the whole object, but one that is more sharply defined, as well as containing more points of view. The hologram does not look like the object at all, but gives rise to an image only when it is suitably illuminated. The hologram seems, on cursory inspection, to have no significant order in it, and yet there must somehow be in it an order that determines the order of points that will appear in the image when it is illuminated. We may call this order implicit, but the basic root of the word implicit means enfolded. So in some sense, the whole object is enfolded in each part of the hologram rather than being in point-to-point correspondence. We may therefore say that each part of the hologram contains an enfolded order essentially similar to that of the object and yet obviously different in form. As we develop this idea, we shall see that this notion of enfoldment is not merely a metaphor, but that it has to be taken fairly literally. To emphasize this point, we shall therefore say that the order in the hologram is implicate. The order in the object, as well as in the image, will then be unfolded, and we shall call it explicate. The process, in this C as E wave movement T, in which this order is conveyed from the object to the hologram, will be called enfoldment or implication. The process in which the order in the hologram becomes manifest to the viewer in an image will be called unfoldment or explication. Enfoldment and unfoldment are actually encountered quite commonly in ordinary experience. For example, whenever one stands in a room, the order of the whole room is enfolded into each small region of space, and This includes the pupil of an eye which may happen to be there. This latter order is unfolded onto the retina and into the brain and nervous system, so as to give rise somehow to a conscious awareness of the order of the whole room. Similarly, the order of the whole universe is enfolded into each region and may be picked up in various instruments, such as telescopes, from which they are ultimately unfolded to a conscious awareness of this order. The fact that light and other such processes are constantly enfolding and unfolding the whole is crucial for our ability to learn about any part of the universe of space and time, no matter where and when our observations may take place. These notions of enfoldment and unfoldment can be understood in terms of the Cartesian order as being only particular cases of movements of fields, not having THEKIND of general necessity that we would attribute, for example, to laws of nature. Rather, what is significant for such laws of physics is considered to be the order of separate points. What we are proposing here is to turn this notion upside down and say that the implicate order will have the kind of general necessity that is suitable for expressing the basic laws of physics, while the explicate order will be important within this approach only as a particular case of the general order. How can we justify such a radical change in our point of view? First of all, we note that basically all the laws of movement in quantum mechanics do correspond to enfoldment and unfoldment. In particular are, the relation between the wave function at one time 1/j, z, t, and its form at another time, 1/j, z, t, is determined by the propagator or the green fun ct ion k, z, z, t, t, through the equation tf, z, t, equals j, k, z, z, t, t, slash, z, t, dz. 151. The value of the wave function at z, t is the sum of contributions from the whole of z at the earlier time t weighted with the factor k, z, z, t, t. And so we may say that the region near z enfolds contributions from all over space at other times. Vice versa, it follows that each region near z will unfold into the whole space z, with the weighting factor k, z, z, t, t. A simple picture of the movement is that waves from the whole space enfold into each region and that waves from each region unfold back into the whole space. Of course, the green's function has been derived ultimately from the Cartesian order by solving differential equations. But if we are questioning that this order holds fundamentally, especially at short distance s, we may well adopt the point of view that the green's function is more basic than the differential equation, which latter will only be an approximation. In this case, the order of enfoldment and unfoldment will be fundamental, while the Cartesian order will have a relatively limited kind of significance. The process of enfoldment and unfoldment was already well known implicitly in the Huygens construction. Waves from each point unfold, but at the same time waves from many points are enfolding to give rise to a new wave front. So in the totality, the one process includes both enfoldment and unfoldment. It is only when we focus on a part that we are led to talk of these as distinct. The Huygens construction is actually the basis of the Feynman graphs, which are widely used. To explain the connection, consider waves which start at a point P and arrive at a point Q, see figure 151. In the first interval of time, d.t, a possible path h is from P to P, and in the second interval, from P to P and so on. Extending this construction, the path eventually arrives at Q. The Huygens construction implies that the waves that arrive at Q from P are built up of contributions from every possible path. These paths are the starting point of the well-known Feynman diagrams. Originally Feynman too wanted to regard these paths as representing the actual trajectories of particles. But this would not be consistent, because contributions from various paths can interfere destructively as well as constructively. RATHER, each path represents a contribution to the final field amplitude as implied by the Huygens construction. And together the whole set of paths describes a process of unfoldment of waves towards Q. Or alternatively THE unfoldment OF waves from P. Since all matter is now analyzed in terms of quant fields, A and D, since the movements of all these fields are expressed in terms of propagators, it 356 the undivided universe. Figure 1.5. 1. Huygens construction and classical paths. Is implied by current physics that THE implicate order is universal. These fields, which are now being treated as the GRU and D of all existence, have to be understood as being essentially in movement. This is because the field cannot be said to be an entity which would persist, as a particle for example does, in a certain form over a period of time. Thus, for example, consider a field variable 1/j, z, t, defined at the space time point z, t. This has at most a purely momentary existence and may be said to vanish at the very moment at which it would come into being. Something with persistent identity would require a unique relation between 1/j, z, t, and the field at other times. If, for example, we try to relate 1/j, z, t, at0 in figure 1.5. 2to1/j, z, t plus t5t, ata and thus define a persistent form of existence, we find that this leads to something quite arbitrary. 4. We could equally well have considered the same field point, 0, in another Lorentz frame, z, t, and then related a 1/j, z, t, to 1/j, z, t plus 6t, at b. This would evidently have defined a different entity. With the particle, the path is unique and we do not have this sort of arbitrariness. What this means is that the field itself cannot be regarded as having an identity. Or, to put it differently, WECAN never have same field point twice. Nor is there a unique form within the field that persists. Therefore all proper TIES that are attributed to the field have to be understood as relationships in its movement. 0. QWNTWM Chlodo dot, nil that amlicat on Elper 367. Figure 1.5. 2. Non-uniqueness of fields in different Lorentz frames. We may suppose THAT the universe, which includes the whole of Exus 10 CE, contains not only all THE fields THAT are now known, but also an indefinitely large set of further fields THAT are unknown and indeed may never be known in THEIR totality. Recalling that the essential qualities of fields exist only in THEIR movement, we propose to call this ground the HOLO MOVEMENT. It follows THAT ultimately everything in the explicate order of common experience arises from THE hollow movement. Whatever persists with a constant form is sustained as the unfoldment of a recurrent and stable pattern which is constantly being renewed by unfoldment and dissolved by unfoldment. When THE renewal ceases, the form vanishes. The notion of a permanently extant NTITYWITH given identity, WH ether, this be a particle or anything else, is therefore at best an approximation, holding only in suitable limiting cases. 1.5. For further illustrative example of the implicate order, we shall now give a further illustrative example involving a different form of the implicate order, which helps us to focus our attention on general relationships that define such an order in more detail. This illustration is carried out with the aid of a device THATWSHALL now describe 358ly THRD-WORLDISM undivided. This device consists of two concentric glass cylinders. The outer cylinder is fixed, while the inner one is made to rotate slowly about its axis. In between the cylinders there is a viscous fluid, such as glycerin, and into this fluid is inserted a droplet of insoluble ink. 3. Let us now consider what happens to a small element of fluid as its inner radius moves faster than its outer radius. This element is slowly drawn out into a finer and finer thread. If there is ink in this element, it will move with the fluid and will be drawn out together with it. What actually happens is that eventually the thread becomes so fine that the ink becomes invisible. However, if the inner cylinder is turned in the reverse direction, the parts of this thread will retrace their step s. Because the viscosity is so high, diffusion can be neglected. Eventually the whole thread comes together to reform the ink droplet, and the latter suddenly emerges into view. If we continue to turn the cylinder in the same direction, it will be drawn out and become invisible. Once again, when the ink droplet is drawn out, one is able to see no visible order in the fluid. Yet evidently there must be some order there, since an arbitrary distribution of ink particles would not come back to a droplet. One can say that in some sense the ink droplet has been enfolded into the glycerin, from which it unfolds when the movement of the cylinder is reversed. Of course, if one were to analyze the movements of the ink particles in full detail, one would always see them following trajectories, and therefore one could say that fundamentally the movement is described in an explicate order. Nevertheless, within the context under discussion, in which our perception does not follow the particles, we may say this device gives us an illustrative example of the implicate order. And from this we may be able to obtain some insight into how this order could be defined and developed. Our next step is then to consider the unfoldment of a series of ink droplets. Suppose that the first ink droplet is unfolded by n turns, and that the second droplet is then inserted at the same point to be unfolded an additional n turns. In this way we unfold a series of n droplets. In this series, the droplets will be unfolded n, 2n, 3n, n and times respectively. Suppose then that the motion of the cylinder is reversed. These droplets will unfold and re-unfold one after another. If the cylinder is turned rapidly, T viscosity being high enough to prevent diffusion, it will appear that there is a single persistent droplet at the point in question. Nevertheless, the droplet is as it were being constantly recreated and dissolved from a distribution of ink that is in some sense spread out over a whole range of fluid. We thus obtain an example of how forms that persist in the explicate order can arise from the whole background and be sustained dynamically by a movement of unfoldment and unfoldment. If we suppose that these successive ink droplets are inserted at slightly Q11 and MTL and EORI and TLNE implicate order 359 different positions, then we will obtain what appears to be a moving ink droplet. The different rates of motion correspond to different unfolded distributions of ink in the whole fluid. In a sense, the movement of the ink droplet is guided by a general field of unfoldment belonging to the whole fluid. The attribution of this guidance to the particular place where the droplet emerges is not appropriate. Rather, its behavior is paradoxically Global in origin. This dearly can be proposed as a model of a quantum particle which might be assumed to underlie the sort of particles that we have postulated in our interpretation of the quantum theory. Of course, this model is rather crude and simple, but later on we shall propose a similar one that we see and take more seriously. For the present, however, let us continue with this model. Suppose that we consider two particles initially at different positions, one represented by red ink and the other by blue ink. As we unfold these into the fluid, red ink particles and blue ink particles will eventually intermingle, so that in a given region we could not say that the ink droplets were really separate. Nevertheless, when the cylinder was TURNEDBACK, red and blue ink particles would begin to separate to form respectively red and blue droplets. It is dear that the ground of the particular behavior of the visible droplets is global, and that disturbances in this ground can lead to correlated changes in TH's behavior. In our model, the AP pairance in perception of what seems to be a pair of separate ink droplets can therefore be deceiving. Actually, these apparently separate ink droplets are internally related to each other. On the other hand, as conceived in the explicate order, such droplets would only be externally related. This is one of the most important new features of the implicate order. What may be suggested is that this feat may give further insight into the meaning of quantum properties such as mutual participation and non-locality. Another instructive illustration of the implicate order can be obtained by phi-rst considering the successive unfoldment of n droplets with the cylinder turning in a certain direction and successive droplets at a constant distance from each other. After these n droplets are unfolded, the movement of the cylinder is reversed to unfold additional s droplets at the same distance from each other as in the first set. After that we turn the cylinder in the original direction and then unfold an indefinite number of further droplets in a similar way. When the cylinder is turned backwards, we will then find a droplet moving as before. But as shown in figure 1.5.3, at the point PTH will suddenly appear a pair of particles moving in opposite directions, and one of these will proceed to meet the original part ICLE at the point Q. They then appear to annihilate each other and nothing is left of THM thereafter. However, the other member of THE original PAIRWILL pre-or onwards. It seems that we have here a simple model of pair production and an NIHI-LA-T-ion. But unlike the represented T-ion given in Feynman diagrams, we do not say that anything moves backward in the T-I-me. Rather, it is clear that what is significant here is the order in the degree of implication. To bring out what this means, let us define an implication parameter, T. OFADR opal T, which is proportional to the number OFTIMES the cylinder H as BEENTURNED, since that dr oplet was inserted. This implication parameter takes negative values when the cylinder is turned in the opposite direction. What happens in this example is that the implicate T-ion parameter H as a part THAT increases, another part in which it decreases, and a third part in which IT increases AGAIN. The entire pattern is present at each instant in the whole fluid with varying degrees of implication. All that happens with the passage of time is a change in the implication parameter, which may be positive or negative. What THIS suggests is THAT, what is called the time coordinate in THE. Feynman's approach may actually be the degree of implication in THIS. Interpretation: Phi-NM and diagrams would not refer to actual processes but Rather TO structures in the implicate or DR. The mea ningoft would have to be something different from T but nevertheless related to it. We have thus far used the distinction between implicate and explicate orders rather loosely. We shall now discuss T11D distinction in a more precise way. To begin with, we might consider a form whose elements were made of ink droplets of various colors. A simple form might be a line defined by droplets at its endpoints, or a triangle defined by droplets at its vertices. Alternatively, we could represent this line by a smooth thread of ink and a point by a droplet, or various other representations could be adopted. What is characteristic of an explicate structure is that all its basic parts are separate and distinct and outside of each other, although they may be in well-defined relationships. For example, consider a two-dimensional square grid made up of points and the lines which connect them. The points are on the boundaries of the lines. Moreover, each point has a definite set of 4 neighbors. It is clear that these requirements define the basic order of the grid, which is clearly explicate in the sense defined above. However, it is not necessary that an explicate order be equivalent to a square lattice. Indeed, in section 1510 we give a more precise mathematical definition of an explicate order through what we call a contact matrix C, J, which enables us to consider not only arbitrary lattices but also irregular structures such as dislocated crystals and glasses. Let us now return to our example of the grid. We may imagine that this grid is enfolded by a certain movement of the cylinder. Nevertheless, when the cylinder is reversed, all the parts will unfold in such a way that they come out all together again in the same explicate structure E. This follows because all the parts have the same implication parameter. What this means is that this whole set of parts retains this potential for being explicate together even when it has been enfolded. Therefore, within the implicate order, there can be structures that are essentially explicate, even though they are still enfolded. On the other hand, there may be structures that are intrinsically implicate in the sense that the whole cannot be unfolded together in one single explicate order. The C as E of the enfoldment of successive droplets is an example of this. For only one of the droplets can be unfolded at a time. The general case is one in which there is a succession of explicate structures enfolded to make up what is basically an intrinsically implicate order. However, this latter contains explicate suborders as aspects which are particular cases of the general notion of the implicate order. In this way we clarify our earlier statement that the implicate order is general and while explicate orders are particular and contingent C as ES of THIS. What then is THE relationship between the notion of explicate order and that of the manifest world discussed in Chapter 8, Section 8? 6. Clearly, the manifest world of common sense experience refined where necessary, with the aid of the concepts and laws of classical physics, is basically in an explicate order. But the motion of particles at the quantum level is evidently also in an explicate order. However, as we have suggested in Chapter 8, this latter order is not always at the manifest level because it is profoundly affected by the active information represented by the quantum potential. This latter operates in a subtle way, and according to what has been said in Th's chapter, this operation is in an implicate order. Therefore, the particle movement is not understood fully as self-determined in the explicate order in which it is described. Rather, this explicate order reveals the deeper implicate order underlying its behavior. The movement of the beables becomes manifest only at the large scale level under conditions in which the quantum potential can be neglected. In This case the movement is not only describable in an explicate way, but it can be approximated as self-determinate in the same explicate order that we use to describe it. Therefore it is essentially independent of the implicate order and can be abstracted as existing on its own. It is therefore capable of being grasped in the HAND without fundamental alteration, whereas at the micro level, the movement of particles is not. Nevertheless, as we have seen in Chapter 8, the implicate order is still revealed in the manifest world in some of the more subtle relationships that arise in experiments at a quantum level of accuracy, e.g. interference experiment S. At this point we need to develop a more general notion of what is to be meant by ORDR, at least within the context UNDER discussion. To illustrate the notion that we are suggesting, we begin with the straight line divided into equal segment S. What characterizes the order of this line is that the differences of successive segments remain similar, and indeed equal throughout the whole line. The difference is just that each line is displaced by its own length relative to the one before. We may extend this suggestion to discuss the order of curves. For example, if we approximate a circle by a polygon of many sides, we see the differences of successive sides is that not only are they displaced relative to each other, but that they have different angles. It is clear, however, that the successive differences are similar and that this is what makes the curve a circle. If successive elements also turned into a third dimension, we would then get a helix resulting from the similar differences. And more generally, one could complicate this construction to produce curves of arbitrary complexity, see bohm and P4. The next step is to consider the differences that are P088able between such similarities. For example, we may arrange a set of lines in parallel. Each of these has a set of similar differences, but then each line is determined by a different set of such similar differences. If the lines are equidistant, these differences in the similarities in turn constitute a higher order of similar differences. If we then consider an additional set of such lines perpendicular to the first, the entire arrangement would have a set of similarities that were different from those in the first set. If we go on to consider a series of such sets of lines, each having a small angle relative to the preceding one, we obtain a set of similar differences of the similarities in each set, and clearly this defines an order of orientations of all these successive arrangements. It is clear from all this that one can have an indefinitely extending hierarchy of similar differences and different similarities of these differences, constituting what may be called an order of orders. If these orders have points of contact, e.g. as there are between perpendicular sets of lines in a grid, we may say they begin to form a structure. This treatment of order in terms of similar differences and different similarities appears to be broad enough not only to cover all the orders found thus far in physics, but it seems to be valid in much broader areas of experience. For example, an order of colors can be expressed as similar differences, as can an order of musical tones. The musical theme can clearly be seen in terms of similar differences and different similarities in patterns of notes, going on all the way up to the order that can be found in highly organized compositions. Similar, but different, orders can also be seen in thoughts, which often develop in patterns of similar differences and different similarities. 1.5.7 The algebra of the implicate order. The implicate order finds a natural mathematical expression in terms of certain kinds of algebra. We shall first illustrate this in terms of the Inc. droplet model and then go on to extend our treatment to the algebras of quantum mechanics. If we start from any initial distribution of ink represented by some density function P0, e.g. such as an ink droplet, Thn after The cylinder has been turned a certain number of times, we will obtain a distribution P1 equals TPO, 152. Where T is an operator that represents the transformation brought about T. 364 the undivided universe. By this process, if we apply a similar transformation again, we obtain F2 equals T2 Po, and if we apply it n times, we obtain Pn equals T Po. 153. The above makes possible a simple mathematical description of the implicate order because it embodies the feature that the differences of successive elements, i.e. the transformation T, remain similar. If we now consider the whole succession of droplets, we have to add up the contributions corresponding to the different values of n. We obtain nn 15.4. But in principle we could have put in each droplet with a different density, a 0. This would have given us P equals ln T Po. 155. n. In this way we obtain an algebra of transformative ions because each term in the algebra, T equals I, a 0 T, can be added to any other term and because clearly transformation can be multiplied. It is evident that by setting n equals 0, we obtain the unit element T. 0. Which simply represents no transformation. At LL. Let us now go on to discuss the quantum theory. We have already seen that the basic notion in the quantum theory expressed through GRN's functions can be understood as a form of the implicate order. Thus we may write for the transformation between two times 1/J1 equals TL/J. 156. Here T will, in general, be complex. Successive transformations through GH. And steps with similar differences can then be expressed as T. So that we obtain 157. Because OFTHE linearity OFTHE wave equation, WECAN, in general, add trans formations with suitable coefficients to obtain new solutions of the wave equation. Thus we could have 158. But THE possibilities are much richer than this. BCAU's WE co-ULD bring in transformations that do not commute. For example, if Ta and T8 are two such transformations we could have 159. Quantum theory and the implicate onler 365. 88 Well 88 more complex combinations. It is clear that at least abstractly we can form an algebra in this way. Thus far we have given only the algebra of transformations, which in quantum mechanics is called the Heisenberg algebra, see Frescura and Hi. Lay 5,6. This algebra can be completed by bringing in a projection over A P, Z, Z. In this way, as we shall see, we can tie up with the ideas of Step 7 and Gel MANN and HA relate. To simplify the discussion, let us consider an operator P1, Z0, as O, which at a given time T projects out everything but a cubic region of size as O centered at the point ZO. At any other time, TH's operator has the form P1 equals E IH 1 1 to 1 P 1 E IH 1 1, where EIH I is the green S function between T and T. Let us now give a more detailed expression for P1. We write 1510 1511, where T/I Z0, Z is a wave function that is constant in a region of size az, centered at z0 and 0 outside. Clearly this wave function defines the projection operator that we want T. We then obtain n, a, underscore, ih, t, t, 1, dash, ih, 1 1 to 1, r1, 1 z, o, uz, e plus za, 1 5 1 2. It is evident that the mere fact that we have an algebra is what enables us to express the properties of quantum interference. Such interference is not described by adding projection operators. Rather, to do the COR response to what is called Forman Ga mixed state. Quantum interference is implied by a further property of the algebra, not present in algebras of the type that describe the ink drop model. This new property involves linear superposition over both indices of the projection operators, z and z, separately. Operations car are ed out on each one of THSA cores p on 2. What are chi-d, in mathematical terms, ideals 6. Operations from the left generate a left ideal, while those from the right generate a right ideal. Transformations of projection operators such as 1510 involve both ideals together in a symmetric way. It is clear that the new projection operators at the time t can be written as p z0 az o equals cent z t t l slash z t t 1513. So that what W as initially a pure state remains SO after tran S formation. This means that the law of motion does not involve the superposition of projection operators, but rather, the superposition on the left and right. 366 The undivided universe. Ideals which imply contributions to the wave functions, z, 1, z, ev. Evidently it is this feature that makes P088able the properties of quantum interference. For example, if the wave functions in 1511 correspond to wave packets of width they are 0, these will start to spread, at first slowly, and then more rapidly when t is positive e. Sooner or later wave functions from packets that were originally in different regions will overlap, and then we will have interferenc e. On the other hand, when t is negative, we can look at this situation as a packet which was originally spread out and which then converges to the region r0, aro. In this case all the parts of the original packet ultimately come together and interfere to produce a wave function that is constant in the region x0, ax0, and 0 outside. If we recall the description relating the green-s function to the implicate order in section 15. 3, we can see that the projection operators of Stapp and Gell-Mann and Hartle really develop according to the implicate order. An operator which corresponds to a well-defined region at the time t, corresponds to an enfoldment of this region at all other time s. Their hi stories are therefore, in a sense, always present at any moment. But at any given time t, only some are unfolded. It is evident that the effective assumption of these authors is that any event is actual only at the moment at which it is unfolded. Nevertheless it is always present whether unfolded or no t. In our example we have thus far been thinking of the wave function of a single particle. But suppose that there are many particles. At the time t equals 0 we should then write the projection operator of the n1h particle as 1514. Here 1 and ln operate on all the particles other than n, and where 1 operates on the left ideal and ln operates on the right ideal. When the above is transformed by the green-s function, Not only will the wave packet spread out as in the one particle case, but it will start to entangle with all the other particles. So we have an implicate order in the WH-hole configuration space of the n particles. 4 times in THE distant pati. The whole universe is thus in some way correlated in its enfold me nts. As time passes, these correlations begin to disentangle and the wave functions begin to converge on the region, xon, axon, belonging to the n1h particle, while it becomes a constant as a function of the coordinates of the other particles. After th is the spreading and re-enfoldment process starts to take place again. An important point here is that if there is sufficient entanglement, THEN, sooner or later, Pn, will begin to approach commutation with P.0 in THE. Models of Stapp and Gelman and H. Aritel, IT will therefore be consistent. To assume that projection operators at moderately different times WILLCOR. Quantum theory and the implicate order 367. Respond to mutually compatible actual events. This will make it possible to give the history a real content as objective and independent of observers. 15.8 A Hilbert space model of the trajectories in our interpretation of quantum mechanics. We are now ready to extend the model of a particle in our interpretation, so that it can be included within the framework of H. Hilbert space. We shall see that this model has certain similarities with the models of Stapp and Gelman and Hartle, though there are important differences that we shall bring out as we go along. We shall begin by returning to our Dr. model of a particle as given in section 1.5.4. We can now relate this to the extension of our AP approach beyond the domain of current quantum theory as suggested in Chap. Ter 1.4, Sect Ion 1.4.6. We proposed there that the stochastic trajectories in are interpreted on can be thought of as arising from some random process, with a certain free flight time that is related to the Planck timmy. So what we now suggest is to give up the idea that the particle has a continuous existence and to suppose instead that it is more like our ink droplet model, which is continually unfolding and re-enfolding. The time between these processes should be of the order of this mean free time. Successive droplets will have a random distribution. However, there will be a system at ICTR end in this distribution, so that the differences Bzn in successive positions will imply a systematic average drift velocity, as well as an osmotic velocity. This will have to be such as to correspond to the velocities assumed in our stochastic model given in chapter 1-2. This model has certain features that are qualitatively right, but it does not readily fit in with quantum mechanical concepts. We therefore now propose a further new idea. Is to replace the converging and diverging droplets by converging and diverging quantum mechanical waves. In this way our concept of the particle is now included within the implicate order as a particular form in H. Hilbert space. To see what the similarities are between our mod L and D that of Stapp and Gelman and H. Aritel, let us recall THAT as shown in the previous section 1.5.7. The projection operators of Gelman and DH Aritel 8 are also particular cases of the implicate order. The key difference is THIS. Their projection operators correspond to waves that converge on extended regions and then diverge. On the other hand, OURs converge to a point and then diverge. To see how the two approaches are related, we can consider a projection operator P, Z0, Z, and let the range of Z approach 0. It's clear that both SETSOF operators are contained WITHI and this FRM work. 368 The Divided Universe. Gell-Mann and Hartle propose actual histories which consist of a sequence of projection operators P, Z0, Z, in which Z is large enough to describe an essentially CL 8.88 Eichel type development of actual events. Our proposal is to consider a sequence of actual events forming a trajectory, which is essentially quantum mechanical. So in some sense we have quantum mechanical histories and they have classical histories. The advantages of our approach have been discussed earlier throughout this book, but here we recall two of them. First, there is no sharp distinction of classical and quantum levels. The CL 8.88 Eichel level arises naturally without further 8.88 UMP. In a gradual way as the quantum potential becomes negligible. On the other hand, in the approach of Gell-Mann and Hartle, we have simply to 8.88 UME such a distinction of classical and quantum levels without having, as yet, a clear criterion for what are the limits of the CL 8.88 Eichel level. Secondly, our approach gives a simple and fairly clear account of quantum processes as well as providing an intuitive understanding of all the transformations of the theory in terms of the implicate order. On the other hand, in their approach, the individual quantum process cannot be described and therefore there is no intuitive understanding of what it means. The dependence of the points to which the various successive waves converge on some sort of systematic drift velocity and osmotic velocity provides an explanation of the inertia of the particle. It is this dependence which also guarantees that a particle will not enter a region of zero wave function and will not leave its channel once it enters. In this way definite results can be preserved at the manifest level, which includes the observable outcomes of measurements. The notion of a particle with permanent identity has now been replaced by that of a particle with no permanent identity. Rather, its basic elements are constantly forming and dissolving in succession over times much longer than that between successive wave formations. The whole process approximates a trajectory, which may however be engaged in a stochastic process. For shorter times the notion of a trajectory dissolves away and some entirely new concepts will be needed which we shall discuss. Further on, we shall give an example of these in terms of incoming and outgoing waves. 1.5.9a An example OFT are ejectories arising from wave st ruptures. In order to illustrate the ideas developed in the previous section, we shall now give a specific example of trajectories arising from wave structures. 2. Simplify the discussion, we consider a particle always moving at the speed of light but with stochastic variations in direction, so THATWHAVEAKIND of zigzag path in space-time whose mean velocity will evidently be less than Chu antum theory until the implicate order 36q. See when we go over to the wave model, the endpoints of each line of the zigzag will be the points towards which our waves converge and from which they then diverge. It seems natural to assume that these waves also move at the speed of light, so that to each point P of convergence and divergence there is an incoming and outgoing light cone. The trajectories in question will then corresp to a suitable sequence of such light cones. This sort of structure of trajectories can be clarified with the idea of the theory of the H-spherical geometry of Lie and Klein, see Klein 9. To relate the light cones to THIS geometry, we first consider any convenient hyperplane, say t equals 0. Each light cone intersects this hyperplane in a sphere. Those light cones whose vertices HAVET0 will be defined to produce spheres of positive radius r equals t. The light cones whose vertices Have T0 will also produce spheres, but these will be assigned negative radii. So there is a 1 correspondence between light cones and their intersections with any hyperplane T equals const. What Li and Kline proposed was an interesting way of parameterizing THSA spheres. To obtain their parameterization, let us first write the equation of a sphere. X, A, 2 plus, Y, B, 2 plus, Z, C, 2 equals R2, 1 5 1 5. Where the coordinates OF the center are, A, B, C, and the radius is R. Equation 1515 reduces to x2 plus y2 plus z2, 2, ax plus by plus cz, equals r2. A. 2, b2, c2. 1516. We now regard the sphere as parameterized by the five quantities A equals x1, b equals x2, c equals x3, r equals x4 and but. These parameters are related by. We introduce homogeneous coordinates by writing x6, x5 equals x6 plus x5 and x equals x6 plus x5. The condition 1517 reduces to 2x2 x2 x2 v2 x2 to 0 x6 to 5 4 plus I plus 2 plus 3 1517 1518. The six parameters we have introduced in addition to equation 1518 now parameterize the sphere. 370 TLAE undivided uni verse. Figure 1.5. 4. Light cones on one light ray X. The advantage of this parameterization is THAT, the conformal invariance of the description is now evident. For equation 1518 implies THE invariance to 6-dimensional pseudo-orthogonal transformations which are easily seen to be isomorphic to the conformal group E. By distinguishing a light cone at infinity, we see A and reduce this to the point and see a regroup, and this may be, for example, done by defining this light cone THRU. The relationship 1519. 1 can readily show that the condition for two spheres to come into contact, i.e. to touch each other at single point and have a common tangent, plane, is 1520. Where x, a, and dy refer respectively to the spheres I and question. One can also see THAT if two spheres are in contact, then the vertices of their corresponding light cones are connected by a null ray, see figure 154. We now proceed to show how the trajectories are described in terms of these spheres. First of all, consider a sphere of radius r corresponding to a light cone whose vertex is I and the future at t equals r. Now consider a sphere of radius r corresponding to a light cone with vertex at t equals r. Suppose the QVAN tumtli or arul UAE imli 1E1 or 371. P. Figure 1.5. Light ray as po int of contact, p, of spheres. Two spheres are to be in contact as shown in figure 1.5. Between them lie other spheres with the same po int of conta CTP and with intermediate radii. All of these correspond to light cones with a null ray in common. But further spheres of La rigor radii lie beyond the outer sphere, going to a sphere of infinite radius which represents a plane wave. Beyond this lie spheres of negative radii corresponding to the light cones whose vertices have negative values of t, see figure 156. As the radius approaches zero from either positive or negative direction, we approach the point P. So a point is a sphere of zero radius. Let us now consider our trajectory starting from a sphere of zero radius, representing a light cone with vertex at t equals 0. The first step in our trajectory, see figure 157, is represented by the point of contact P and a sphere of radius r. The corresponding null ray is in the direction of the radius of the sphere at the point P. The next null ray will be represented by a larger sphere contacting the first sphere at the PO and Q. The next null ray will correspond to a still larger sphere contacting the second sphere at yet another point R. This procedure is to be continued indefinitely so that we obtain a complete description of the zigzag trajectory. The key point here is that we have described our trajectory entirely in terms of waveforms at any given time. It is easy to show that this description is conformal Ly invariant. For every transformation that must turn spheres into spheres, A and D, if we restrict ourselves to satisfying 1519, we will have only Poincare invariance. But now we see the meaning. Figure 156, illustration of spheres with positive and negative radii. Of these TRA-NS formations without explicit reference to time. For example, in a time displacement, FLT, the radius of each sphere changes by FLT. In a Lorentz transformation, however, the radii and centers change together so that initially concentric spheres cease to be concentric. From what we have been saying, it follows that our trajectory is now ri in an implicate order. As this order unfolds in TIME, the radii of the spheres corresponding to incoming waves decrease while those responding to outgoing waves increase. The entire trajectory is now shown as a kind of enfolded geometric structure whose meaning can be seen all at once as a chain of successively contacting spheres. The LAW of development is implicit in THISSTRUCTURE. This way of looking at the subject is close to what is implied by Feynman's approach as well as to the Huygens principle. Feynman, too, describes his trajectories as a sequence of points in time. We describe them as sequences of spheres all enfolded at a given time. The Lagrangian is thus, in R a property of the implicate order which holds at any given moment. And as seen in section 158, backward tracks in time are replaced by tracks in which the implication parameter is decreasing. In our mode L, the implication parameter is just the radius of the sphere. Thus in Fig. 156, we could have the radii of SP Harris decrease for a while and then a figure 157, trajectory in terms of spheres. 374 the undivided univer e increase again. As explained in the previous section, this corresponds to pair production. But now there is no need to have the mysterious notion of backward motion in TIME. The above is a very simple model of the particle in terms of the implicate order. Much more complex models can evidently be developed using, for example, spinors and twistors, but to do this would take us too far outside the scope of this book. 1510 Prespace and the implicate order. In the previous two sections we have proposed how the notion of a continuous trajectory can be replaced by that of a succession of waves, each converging to a point, and how this succession can be seen as a structure in the implicate order. However, the equivalence of this model to a particle is limited, because for times shorter than that between successive waves, the idea of a particle is no longer relevant. It seems natural to suppose THAT, as we have suggested earlier, the critical time in this regard is the Planck time. For such intervals the ordinary notions of space-time and the structure of matter will in any case probably break down because of quantum fluctuations of the metrical phi LD. Indeed, the notion of measurability of space-time in the usual way could hardly be expected to be applicable under such conditions. Rather we may anticipate that the implicate order would become the dominant and fundamental concept here. We have thus far seen throughout this book how it is possible, not only for the manifest level of ordinary experience, but also the quantum level underlying it, to emerge from a still deeper implicate level in which the classical Cartesian notions of form, order, and structure have more or less dissolved. Indeed, it was implicit in the previous two sections that such ideas, underlying our classical notions of space-time and measure, would have to arise as limiting cases of this deeper implicate order. In many ways, this suggestion is close to one that has been under consideration recently by physicists, i.e. that of pre-space. 10. The difference is that we want to go much further than has generally been contemplated in the discussion of pre-space and to propose more definite lines along which we could actually inquire into developing an overall mathematical formulation of these ideas. We have space in TH's book only for a brief sketch of our proposal s. A number of preliminary papers on this subject have already been published, 1.1, 1.2, and further work is proceeding. The principal current difficulty in the attempt to make theoretical physical ICS coherent is the notion of a mathematical point in space-time without extension or duration. This has been very useful as an abstraction, but we feel that there is a great deal of evidence, some of which we have discussed in this book, that this notion has reached its limits of validity and 119 Fulnius. The idea of beginning with an extended region has indeed been long in the air and has been explored by many people. 1.3. Indeed both Stapp 7 and Gell-Mann and Hartle, 8 have at least implicitly begun with this notion by considering projection operators that cover regions. As a point of departure, let us therefore begin by considering integrals of fields over regions. These may be the ordinary fields, like the electromagnetic field, or they may be quantum fields represented by the wave function. To simplify the discussion, we restrict ourselves to a set of scalar fields phi. Let1 colon denote any particular total configuration of The field. Different values of the index p then denote different total configurations. We further consider a set of regions R, and we define the integral of 1 colon over such a region as f equals cent j jr 1521. The above types of integral have been extensively studied in algebraic topology 1.4 and they are called p-sets. These p-sets may include integrals of vectors, tensors etc. over regions of various dimensionalities. One of the main concepts of the theory is that these p-sets can be put together to describe the composition of regions into larger regions, and that this can be comprehended within an appropriate algebra. In this algebra, boundary relationships can be expressed as a discrete structure of matrix elements and the entire content of typical physical equations, such as Laplace's equation, Maxwell's equations, etc., can be replaced by purely algebraic relationships among the p-sets. All of this has been done classically, but we are now exploring how the can be extended to a quantum context. The crucial point that is relevant for our purposes is that these algebraic relationships are invariant under two closely related transformations. 15.22 and 1523. or the two together give 1524. The similarity of the above to the transformations of quantum theory is evident. Thus, 1522 describes a transformation in which the field in one region is exploded into the whole space, or ELSE I'm plot ED from the WH whole space into any one region. It therefore corresponds to a wave, WH now. 376 The undivided universe comes in, not to a point, but to a region. It is therefore simply an extension of the implicate order to a theory in which we do not need to assume dimensionless points. The equations, 15.23, however describe a transformation in which the regions are either than the fields are exploded or imploded. There is a complete symmetry between the implicate order as applied to fields and the implicate order applied to regions. This symmetry is similar to that between points and planes in projective geometry or to that of any element, and its dual in ordinary geometry. It is different in that it is far more general and comprehensive in its possibilities. This symmetry gives another intuitive image of the quantum mechanical symmetry in Hilbert space and of the symmetry of the bra and the ket of Dirac. As the invariant is a scalar product of a bra and a ket, so here the invariant P set is the scalar product of a field and a region. Indeed, from this symmetry it becomes clear that there is ultimately no distinction between the fields and space-time itself. EACH is a dual description of the other physical quantities will then be invariants which can be interpreted as relations between fields or between regions. In general these relationships will be non-local. Locality must be a SPE. Chale case. HOW then can we define locality? To do this, we must have an explicate order, i.e. one in which the elements are outside of each other and yet cover the whole space. A simple illustrative example of this would be a set of square elements in contact in such a way as to make up a SQUARE grid. To express their local contact, we can define a contact matrix C, J, which is 0 when the elements ij are not in contact and unity when they are. In this example, correspond ing to each specific region R, C, J would have a certain four elements that were not 0, and these elements would define the neighbors of the region R. EACH value of J would also define a direction from which could be built a line ordered according to the index J. W with similar differences between successive elements. But the whole theory must be invariant to an explosive transformation, i.e. an enfoldment into the implicate order. When this is done, the elements C, I will no longer have the simple structure of zeros and ones described above, but will be very complex. Yet they are in some sense implicitly describing the same order. Moreover, if we simultaneously transform the field P in a dual way, then the quantity EF remains invariant, i.e. EF equals R. P equals 1 cent / J R R11 1525. The above is a kind of generalization of the invariance that arises in general relativity, quantum theory and the implicate order. 377. Given a set of contact matrices, C11, we can ask whether or not it could be transformed completely into an explicate order of Cauchy. Need not be a simple square lattice. Nevertheless, 11 more generally, after the transformation each index I must be non-zero for a relatively small number of indices J. It is not even necessary, however, that the pattern be the 118111a. For all indices I. Chan GES in the pattern may, for example, correspond to dislocations in the lattice. Structures of the above general kind will be called locally connected. If there exists a transformation that reduces a given matrix, Ci, to a locally connected matrix, Cj, we shall say Cj is in essence locally connected even though it appears to be non-local in the particular representation that we have chos. An interesting question arises if THR is no matrix Ci which is locally connected. A similar question arises in general relativity when the metric tensor cannot be made diagonal over the whole space. In this case we have a new property called curvature. If Cj cannot be transformed into a locally connected matrix, this means that we have a space which may be locally explicate but which gradually unfolds as we move along the locally ordered lines. To picture this we can say that W wherever you are you may represent this as an ordinary local space but that there will be a horizon in which this space dissolves into an implicate order. Such a universe would not have a definite boundary, but would simply fade into something that does not manifest to us beyond its horizon. Nor would it have a beginning or an end, but rather it would similarly fade in the distant past and in the distant future. Yet, to anyone that was beyond our horizon, everything would be as definite, or indefinite, as it is to us. That is to say, there is a kind of relativity of the implicate order. Some new mathematical concept corresponding to curvature would have to be developed to express more precisely the distinction between an irreducibly implicate order and an that could be transformed as a whole into an explicate order. Another interesting example of an irreducibly implicate order is one that could not be put in explicate form locally, but that could be approximately explicate on the larger scale. That is to say, the Sig matrices could not be reduced to some canonical form implying only local contact. This would mean, in general, that the non-zero elements of the contact matrix would spread out over whatever parameters with which we try to label the regions constituting our space. This would of course imply a general non-local contact between elements and would mean the ordinary IDE as OF space, as constituted of low Ca leasable elements while LD no longer Ho LD. So processes that were associated with what we now call the Planck length while LDHAVE to be described in what is an essentially quantum mechanical kind of space, in which Cartesian notions of order would not even arise. Neve RTHLS the 378 that undivided event. C. Matrices might have such properties that large sets of elements could be grouped together and that a transformation could be found in which these groups would have a simple contact matrix of a local nature that would give rise to an explicate order. In such a theory an ordinary geometrizable space could emerge in the LRG, while it had no meaning in the SMLL. Indeed, these very words large and small l would be somewhat misleading, since measure could prevail only in relation to the elements that are grouped together to give rise to a local contact matrix implying an explicate order. We have been discussing how explicate orders, or approximations to such orders, could emerge from a ground that was irreducibly implicate as a whole. This is an example of how an explicate order arises as a particular case of the implicate order. We have here distinguished this case by requiring certain properties of the contact matrix. A similar procedure has already been explored in ordinary geometry through the Klein-Erle and GER. Program 1.5. Thus if we begin with projective geometry as our most general concept we can obtain affine geometry as a particular case by distinguishing a plane at infinity. To obtain ordinary metric geometry, we merely have to distinguish a certain quadric on this plane and call this the circle at infinity. But from our starting point, even projective geometry is very special. Our first step is to obtain a simple explicate order without which the idea of geometry itself would have very little significance. We do this by distinguishing a particular implicate order as the explicate order. But this is possible only if the contact matrix ha a suitable form. From here on, we could try to go further in defining the equivalent to points, lines, planes, etc. in terms of p-sets, and thus we would distinguish a particular case of the explicate order, i.e. one that is geometrizable as a whole. From here we could go on to projective affine and d-metric geometries by further distinctions. If this were done, then the whole of geometry would be invariant to enfoldment transformations in the implicate order. We could then say that the order of space, and ultimately of tim fit out of a deeper implicate order of pre-space. Moreover, this pre-space would have a structure that was inherently conformable to the laws of the quantum theory. We would thus be free of the present incoherence of trying to force quantum laws into a framework of a Cartesian order that is really only suitable for classical mechanics. 1.5.1.1 The super implicate order. Thus far we have been considering the implicate order mainly in relation to particle theories, but further interesting insights can be obtained by extending the notion of implicate order to quantum field theories. Quantum Theory and the implicate OER 379. The CL and 88 Eichel-Field, which generally obeys a linear equation, who already been understood in terms of the implicate order, e.g. U in the example of the hologram. But when this field is quantized, a further kind of implicate order is introduced. We shall call this the super implicate order. The super implicate order is related to the implicate order as the implicate order in particle theories is related to the particles. Consider, for example, a particle which classically executes simple harmonic motion. Its equation of motion is linear. 2. mx equals ax. When this theory is quantized by bringing in a wave function at x, r, x, exp, is, x, the equation of motion becomes where 1y2r, q equals 2m, l. As we have seen in earlier chapters, this not only makes the equation non-linear, but also introduces a force that depends on the whole quantum field. And that reflects the activity of information, so that if we have several harmonic oscillators, we also obtain non-locality. Similarly, consider a classical linear field equation. As pointed out in chapter 1.1, when the theory is quantized, we bring in a wave functional t/j equals t/j. Cent I, x equals REXP is. And the field equation becomes where Q is given by 1.32. The wave equation now becomes nonlinear as well as non-local, as happened in the particle theory. The connection between wave and particle theories can be made yet more evident by considering the normal modes of the field theory. If 9T is such a normal mode corresponding to wave number k, then CL asical Ly1T satisfies the harmonic oscillator equation. 380 The undivided universe. All the harmonic oscillators are independent. On quantization, the wave functional can be written as Tj equals Tj Q T equals REXP is. If we develop the field equations along the lines given in chapter 1.1, we obtain where K2A Q plus Q equals A Q, Q, T, Q, Q equals, underscore, L, underscore dot, underscore 82R, 2R8QJ. Each of the oscillators now obeys a nonlinear equation, and it is in general coupled to all the others. As in the particle theory, the implicate order manifests in the activity of the p-particle through the quantum potential. It is clear then that in field theory there is a super-implicate order that manifests in the field variables. The effect of the implicate order on the particle is to make its behavior more wave-like than it would be in classical physics. However, as we have seen in Chapter 1.1, Section 1.1.7, the effect of the super-implicate order on the field variables is to oppose the classical tendency for waves to spread and to cause the wave field to be swept in towards atoms. For example, the variables may now be regarded as the first implicate order. The super-implicate order thus tends to organize the first implicate order into something more p-particle-like than it would be in classical physics. At this point a little reflection shows that the whole idea of implicate order could be extended in a natural way. For if there are two levels of implicate order, why should there not be more? Thus if we regard the super-implicate order as the second level, then we might consider a third level which was related to the second as the second is to the first. That is to say, the third implicate order would organize the second, which would thereby become nonlinear. For example, there might be a tendency for the whole quantum state to collapse into somewhat more definite. Evidently we could go on indefinitely to higher levels of implicate order. Since each is related to the one below, as the one below is related to the one still further below W, we have a sequence of similar differences. In other words, we have an order of implicate orders. Thus far we have considered only a one-way connection of implicate orders in which the higher affects the lower but not the other way round. However, WE could quite readily extend the idea to allow lower orders to affect the higher ones. At present we have very little to guide us as to how to do this, but we have indeed already considered a possibility of this kind. Quantum Theory and the Implicate Order 38.1. In Chapter 1.4, Section 1.4.6. We prop 08 ed there to change Schrödinger's wave equation so as to depend on the particle p08 ions in a way that is similar to what is done in the approach of G. H. Girard I, Rumini and Weber, 1.6. With regard to the position towards which the wave function is made to collapse. As a result of this change, the wave function in our theory will tend to remain loosely associated with the particles, and the empty channels would disappear, so there would be a true relationship between wave function and particle. A similar tendency could be assumed such that all levels of implicate order would tend to be loosely associated with TH08E below. Thus the order of implicate orders would be based on sequences of two-way relationships. To develop such an order of implicate orders would require that we first obtain some notion of the third implicate order. At present there is very little to guide any speculations about this. It is, however, an interesting possibility that may be kept in mind for further exploration. The main suggestion that we have, at present, is that a third implicate order would require a superwave functional. This would imply that the wave functional is spread over a range of possibilities. But the notion of a density matrix can be thought of as implying the same sort of thing, i.e. a statistical spread over wave functions or over wave functionals. If the density matrix were thus connected to the superwave function L, this would mean, for example, that a state of thermal equilibrium spreading over a range of energies is actually a reflection of some new property that flows out of the superwave. Functional. Another possible area in which the super-implicate order may be relevant is in consciousness, as will be brought out in the next section of this chapter. 1.5. 1.2 The implicate order and consciousness. Several physicists have already suggested that quantum mechanics and consciousness are closely related, and that the understanding of the quantum formalism requires that ultimately we bring in consciousness in some role or other, e.g. Wigner, 1.7, Everett 1.8, and Squires, 1.9. Throughout this book it has been our position that the quantum theory itself can be understood without bringing in consciousness, and that as far as research in physics is concerned, at least in the present general period, this is probably the best approach. However, the intuition that consciousness and quantum theory are in some sense related seems to be a good one, and for this reason, we feel that it is appropriate to include in this book a discussion of what this relationship might be. Our proposal in this regard is that the basic relationship of quantum theory and consciousness is that they have the implicate order in common. For an extensive discussion of this approach, see Bohm, 20. The essential features of the implicate order are, as we have seen, that the whole universe is in some way enfolded in everything, and that each thing is enfolded in the whole. However, under typical conditions of ordinary experience, there is a great deal of relative independence of things, so that they may be abstracted as separately existent, outside of each other, and only externally related. However, more fundamentally, the enfoldment relationship is active and essential to what each thing is, so that it is internally related to the whole, and therefore to everything else. Nevertheless, the explicate order, which dominates ordinary common sense experience as well as classical physics, appears to stand by itself. But actually this is only an approximation, and it cannot be properly understood apart from its ground in the primary reality of the implicate order, i.e. the hollow movement. All things found in the explicate order emerge from the hollow movement and ultimately fall back into it. They endure only for some time, and while they last, their existence is sustained in a constant process of unfoldment and re-enfoldment, which gives rise to their relatively stable and independent forms in the explicate order. It takes only a little reflection to see that a similar sort of description will apply even more directly and obviously to consciousness, with its constant flow of evanescent thoughts, feelings, desires, urges, and impulses. All of these flow into and out of each other and, in a certain sense, enfold each other, as, for example, we may say that one thought is implicit in another, noting that this word literally means enfolded. A very clear illustrative example of this enfoldment can be seen by considering what takes place when one is listening to music. At a given moment, a certain note is being played, but a number of the previous notes are reverberating in consciousness. Close attention will show that it is the simultaneous presence and activity of all these related reverberations that is responsible for the direct and immediately felt sense of movement, flow and continuity, as well as for the apprehension of the general meaning of the music. To hear a set of notes so far apart in time that there is no consciousness of such reverberation will destroy altogether the sense of a whole unbroken living movement that gives meaning and force to what is being heard. The sense of order in the above experience is very similar to what is implied in our model of a particle as a sequence of successive incoming and outgoing waves. Thus in section 1.5.9, we saw how a particle trajectory could be expressed at a given moment in terms of an order of spherical waves that are present at that moment. The outgoing waves would correspond to our reverberations, while The incoming waves would correspond to anticipa ions WHCH are also evidently present Li 110. To the muic. The essential POM 1s that the whole movement is contained in Thilway at any given moment. Of course not all of it is conscious at any given moment, and a great deal may be unconscious. But even that which is unconscious and vaguely anticipatory may contain a whole movement. The most striking example of this is Mozart saying that the whole composition came to him almost in a flash, and that from there on he was simply able to play it or to write it. Thus the whole was unfolded rather as the sequence of spheres is unfolded in our model. Further similar examples can be obtained from visual experiences, e.g. as a series of similar frames in a movie sensed simultaneously can give rise to a feeling of movement. What all this suggests is that our M08T primary experience in consciousness actually is of an implicate order, and our perception of the explicate order is constituted mostly by a series of abstractions from this. To go into all this here would take us too far afield, but an account of it can be found elsewhere, bohm 2:1. To sum up then, in consciousness, as in quantum theory, the explicate order emerges from the implicate order as a relatively stable and self-determined domain and ultimately flows back into the implicate order. The implicate order is not only the ground of perception, but also of the actual process of thought. For thought is based on information contained in the memory. We do not know a great deal of how memory works at present, but it does not seem that it operates through a one-to-one correspondence between, for example, an object and an image stored somewhere in the brain. Rather, what is relevant for thought is the storage of many abstracted items of information, for example, about shape, color, the uses of the object, the various things with which it is associated, etc. Indeed, in our customary use of language we say that a certain content is recollected, thus suggesting that this content is collected together from the whole of memory. The fact that it does seem to come from the whole can be seen with the aid of an elementary example. Thus English nouns ending in ation generally come from verbs ending in at e. Thus rotation comes from rotate. But this rule does not always hold. For example, inclination does not come from inclinate. The crucial point here is that we see and tell immediately that inclinate is not an accepted word, whereas rotate is. This strongly suggests that somehow our recollection is directly from a whole rather than the result of an algorithm for searching the memory in detail. All of this is clearly compatible with the notion that the basic order of the mind is implicate and that the explicate arises as a particular case of this implicate order in much the way that we have suggested in this 384 The Undivided Universe chapter for the quantum theory and for pre-space. So the various items of information that have been stored up may be regarded as somehow enfolded in the brain, and indeed probably in the rest of the nervous system as well as in The muscles and organs. It is clear moreover that this information is basically active rather than passive. We may easily verify this in our subjective experience. Suppose, for example, that on a dark night one encounters some shadows. If the memory contains information that there may be assailants in the neighborhood, this can give rise immediately to a sense of danger, with a whole range of possibilities, fight, flight, etc. This is not what could be called purely a mental process, but includes an involuntary and essentially unconscious process of hormones, heartbeat, and neurochemicals of various kinds, as well as physical tensions and movements. However, if we look again and we see that it is only a shadow that confronts us, thought has a calming effect, and all this activity ceases. Such a response to information is extremely common, e.g. information that X is a friend or enemy, good or bad, etc. More generally, in consciousness, information is seen to be active in all these ways: physically, chemically, electrically, etc. This sort of activity is evidently similar to that which was described in connection with quantum processes involving particles such as electrons, for which the information in The wave function was also active in the movement of the particle. At first sight, however, there may still seem to be a significant difference between these two cases. Thus, in our subjective experience, action can, in some cases at least, be mediated by reflection in conscious thought. On the other hand, in the case of the electron, The action of information is immediate. But actually, even if this happens, the difference is not as great as it might appear to be. For such reflection follows on the suspension of physical action. This gives rise to a train of thought. However, both a suspension of physical action and the resulting train of thought follow immediately from a further kind of active information, implying the need to do this. It seems clear from all this that, at least in the context of the processes of thought, there is a kind of active information that is operating which is in key ways rather similar to that which operates in the action of the quantum potent eel. To clarify what this means in the present context, it is convenient to introduce the notion that consciousness shows or manifests on two sides, which may be called the physical and the mental. Active information can serve as a kind of link or bridge between these two sides. These latter are, however, inseparable, in the sense, for example, that information contained in thought, which we feel to be on the mental side, is at the same time a related neurophysiological, chemical and physical activity, which is cl early. What is meant by the material side of thought? Quantum theory and the implicate on Eldra 385. We have, however, up to the point considered only a small part of the significance of thought. Thus, our thoughts may contain a whole range of information content of different kinds. This may in turn be surveyed by a higher level of mental activity, as if it were a material objectee at which one were looking. Out of this may emerge a yet more subtle level of information, whose meaning is an activity that is able to organize the original set of information into a greater whole. But even more subtle information of this kind can, in turn, be surveyed by a yet more subtle level of mental activity, and at least in principle this can go on indefinitely. Each of these levels may then be seen from both sides. From the mental side, it is a potentially active information content. But from the material side, it is an actual activity that operates to organize the less subtle levels, and the latter serve as the material on which such operation takes place. The proposal is then that a similar relationship holds at indefinitely great levels of subtlety. It is being suggested that this possibility of going beyond any specifiably level of subtlety is the essential feature on which the possibility of intelligence is based. It is interesting in this context to consider again the meaning of the word subtle. As stated in Chapter 8, Section 8. 6, this is rarefied, highly refined, delicate, elusive, indefinable. Its Latin root is subtexera, which means finely woven. This suggests a metaphor for thought as a series of more and more closely woven nets. Each can catch a certain content of a corresponding fineness. The finer nets can not only show up the details of form and structure of what is caught in the coarser nets, they can also hold within them a further content that is implied in the latter. We have thus been led to an extension of the notion of implicate order, in which we have a series of interrelated levels. In these, the more subtle I.E. the more finely woven levels including thought, feeling and physical reactions both unfold and enfold those that are less subtle, i.e. more coarsely woven. In this series, the mental side corresponds, of course, to what is more subtle, and the physical side to what is less subtle. And each mental side in turn becomes a physical side as we move in the direction of greater subtlety. Let us now return to a consideration of the quantum theory. We have already seen that there is a basic similarity between the quantum behavior of a system of electrons, for example, and the behavior of mind. But if we wish to relate mental processes with quantum theory, this similarity will have to be extended. The simplest way of doing this is to use the idea of a series of implicate orders for matter in a way that has already been discussed in the previous section. So we are supposing that, like mental processes, physical processes are also capable of extension to indefinitely great levels of subtlety in a series of implicate orders with two-way relationships. One may then ask, what is the relationship between the physical and the mental processes? The answer that we propose here is that there are not two processes. Rather, it is being suggested that both are essentially the same. This means that that which we experience as mind, in its movement through various levels of subtlety, in a natural way ultimately move the body by reaching the level of the quantum potential and of the dance of the particle S. There is no unbridgeable gap or barrier between any of these levels. Rather, at each stage some kind of information is the bridge. This implies that the quantum potential acting on atomic particles, for example, represents only one stage in the process. The content of our own consciousness is then some part of this overall process. It is thus implied that in some sense a rudimentary mind-like quality is present even at the level of particle physics, and that as we go to subtler levels, this mind-like quality becomes stronger and more developed. Each kind and level of mind may have a relative autonomy and stability. One may describe the essential mode of relationship of all of these as participation, recalling that this word has two b as ic meanings, to partake of and to take part in. Through enfoldment, each relatively autonomous level of mind partakes of the whole to one degree or another. Through this, it partakes of all the others in its gathering of information. And through the activity of this information, it similarly takes part in the whole and in every part. It is in Th's sort of activity that the content of the more subtle and implicate levels is unfolded, e.g. as the movement of the particle unfolds the meaning of the information that is implicit in the quantum field, and as The movement of the body unfolds what is implicit in subtler levels of thought, feeling, etc. For the human being, all of this implies a thoroughgoing wholeness, in which mental and physical sides participate very closely in each other. Likewise, intellect, emotion, and the whole state of the body are in a similar flux of fundamental participation. Thus, there is no real division between mind and matter, psyche, and soma. The common term psychosomatic is in this way seen to be misleading, as it suggests the Cartesian notion of two distinct substances in some kind of interaction. Extending this view, we see that each human being similarly participates in an inseparable way in society and in the planet as a whole. What may be suggested further is that such participation goes on to a greater collective mind, and perhaps ultimately to some yet more comprehensive mind in principle capable of going indefinitely beyond even the human species as a whole. Finally, we may ask how we can understand this theory if the subtle levels are carried to infinity. Does the goal of comprehension constantly recede as we try to do this? We suggest that the appearance of such a recession is in essence just a feature of our language, which tends to give quantum theory and the implicate order. 387. STN. Underscore 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 underscore. Figure 1.5.8. Magnetic poles as abstractions from an overall magnetic field. Too much EMPHSIS to the analytic side of our thought processes. To explain what is meant here, one may consider the analogy of the poles of a magnet, which are likewise a feature of linguistic and intellectual analysis, and have no independent existence outside such analysis. As shown in figure 1.5.8, at every part of a magnet there is a potential pair of north and south poles that overlap each other. But these magnetic poles are actually abstractions, I introduced for convenience of thinking about what is going on, while the whole process is a deeper reality and unbroken magnetic field that is present over all space. Similarly, we may for the sake of thinking about the subject, abstract any given level of subtlety out of the unbroken whole of reality and focus our attention on it. At each such level, there will be a mental pole and a physical pole. Thus, as we have already implied, even an electron has at least a rudimentary mental pole, represented mathematically by the quantum potential. Vice versa, as we have seen, even subtle mental processes have a physical pole. But the deeper reality is something beyond either mind or matter, both of which are only aspects that serve as terms for analysis. These can contribute to our understanding of what is happening. See Marshall 22, for an account of an idea having important similarities with what has been proposed here. He, too, uses the notion of a general quantum reality as a basis for the bodily and mental realms, considered as inseparable sides or aspects. But he proposes to explain this from the quantum theory as it now stands in its usual interpretation. However, we have here used the ontological interpretation of the quantum theory with its additional concepts of particle trajectories and active information, and have assumed that ultimately the relationship of mental and material sides can be understood only by 388 the undivided universe, but are in no sense separate substances in interaction. Nor are we reducing one pole to a mere function or aspect of the other, e.g. as is done in materialism and in idealism. The key point is, however, that before the advent of the quantum theory, our knowledge of matter as gained from the study of physics would have led us to deny that it could have a mental pole, which would enable it to participate with mind in the relationship that has been described here. We can now say that this knowledge of matter, as well as of mind, has changed in such a way as to support the approach that has been described here. To pursue this approach further might perhaps enable us to extend our knowledge of both poles into new domains. 1.5.1.3 Further extension to an overall approach. What we have done here opens up the possibility of an overall approach that encompasses all aspects of objective nature and of our subjective experience. E.g. as an observer and a thinker. To develop such an approach, we first note that not only inanimate nature, but also living nature, is to be understood in terms of the implicate order. Consider a tree, for example, which grows from a seed. Actually, the seed makes a negligible contribution to the material substance of the plant and to the energy needed to make it grow. The substance comes from the air, water, and soil, while the energy comes from the sun. In the absence of a seed, all these move in an implicate order of a relatively low level of subtlety, based, for example, on the order of the constituent particles. This brings about the constant recreation of inanimate matter in various forms. However, through THE information contained in the DNA molecule, the overall process is subtly altered so that it produces a living tree instead. All the streams of matter and energy, which had hitherto developed in an unorganized way, now begin to bring substance and energy to the plant, which grows and eventually decays to fall back into inanimate matter. At no stage is there a break in this process. For example, one would not wish to say that an inanimate molecule of carbon dioxide enters the tree and suddenly becomes a living, or that the oxygen molecule suddenly dies when it leaves the tree. Rather, life is eternally enfolded in matter and more deeply in the underlying ground of a generalist hollow movement as is mind and consciousness. Under suitable conditions, all of these unfold and extending the scheme beyond the domain in which the current quantum theory is valid. For other recent attempts to consider the mind-matter relation in the light of the quantum theory, see Penrose, 23 and Lockwood, 24. For a discussion of the notions of active information and implicate order by a number of authors, see Pulkiainen 25. Quantum theory and the implicate order 389. Evolved to become a manifest in ever higher stages of organization. The notion of a separate organism is clearly an abstraction, as is also its boundary. Underlying all this is unbroken wholeness, even though our civilization has developed in such a way as to strongly emphasize the separation into parts. In this whole process, it is clear that the observer, along with his thoughts, is contained in an inseparable way. For example, the general theories of physics, including the very one we are proposing here, are an extension of this process. What such a theory produces is a kind of reflection of reality as a whole, as explained in Chapter 1.4, Section 1.4. 1. This provides another aspect or appearance of the whole. We may usefully regard this appearance as a kind of mirror through which reality is perceived. Classical physics provided a mirror that reflected only the objective structure of the human being who was the observer. There is no room in this scheme for his mental process, which is thus regarded as separate or as a mere epiphenomenon of the objective processes. As we have seen throughout this book, however, quantum physics interpreted ontologically and extended in a natural way makes possible a reflection even of the subtle mental aspects of the observer. Thus, through this mirror the observer sees himself both physically and mentally in the larger setting of the universe as a whole. There is no need, therefore, to regard the observer as basically separate from what he sees, nor to reduce him to an epiphenomenon of the objective process. Indeed, the notion of separateness is an abstraction and an approximation valid for only certain limited purposes. More broadly, one could say that through the human being, the universe is making a mirror to observe itself, or vice versa. The universe could be regarded as continuous with the body of the human being. After his latter, like the plant, gets all its substance and energy from the universe and eventually falls back into it. Evidently the human being could not exist without this context, which has very misleadingly been called an environment. Although the implicate order is a theory of the whole, it is in no sense a theory of everything, or to put it differently, we do not expect any mirror to provide a complete and perfect reflection of reality as a whole. Every mirror abstracts only some features of the world and reflects them only to a limited degree of accuracy, as well as from a limite perspective. We emphasize again that physical theories share in this sort of limit as much as all other forms of knowledge, for our thought is always a limited abstraction from the indefinitely great subtlety of the implicate order as a whole. We can always extend it, but then it will always still be limited. And beyond these limits, there is always indefinitely more that has not been grasped in thought. At the very least, the above is what would be implied by our proposal. 390 THEU undivided uni verse. Of an order of ever-increasing orders of subtle tie in the implicate order. But probably the whole scheme of the implicate order will be found to be limited to, and will eventually have to be contained in some yet more comprehensive idea. More generally, we are not asserting finality for any of the ideas that we propose here. All proposals are points of departure for exploration. Eventually some of them may be developed so far that we may take them as working hypotheses. But in principle we will be ready to modify them or even to drop them whenever we find evidence for doing this. This applies even to the very idea that we are discussing at this moment. We suggest that the approach outlined above is more coherent than one in which we either tacitly or explicitly take specified features of our ideas as finally fixed and absolutely true. In particular we would say here that certain features of theories that have attempted to cover both mind and matter, for example, those proposed by Everett 1.8, and by Gell-Mann and Hartle 8, do imply that mind is a rather limited sort of system, that could be completely covered, for example, by the notion of an information gathering and utilizing system, IGUS. No doubt mind is capable of doing this sort of thing. But a little observation shows that it is much richer in its capabilities. In particular, if a human being is nothing more than such a system, he is effectively reduced to a kind of machine. How then would we understand creativity? Perhaps we could say it is an illusion brought about by our not having complete knowledge of how the machine works. But we can ask, how can it be known that this is all that we are? Thus, in the time of Newton, people compared everything including living beings to a clockwork, and at later times the brain and nervous system were compared to a telephone exchange. It is now being compared to a supercomputer. In each age people use the latest technological developments as models for the me and d. Very probably, in another century or so, the whole notion of computers will be seen as rather limited and perhaps even as outmoded as 19th century machines are now thought to be. Doubtless we will then have a still more intricate machine with which one could compare the mind if one chose to do so. This whole approach seems to be effected with irreducible contingency. There is really no necessity for it at all. We are therefore free, if we so choose, to explore the broader approach to mind and matter, and therefore to the whole of reality, that we have been discussing here and throughout the rest of the book.